Welcome to this training on inverter technology. Our goal is to make these classes as simple and easy to understand as possible. To accomplish this, we will include real-time plots, graphs, and live measurement samples. We are sure that you will find these classes very interesting and you will learn a lot. Inverter technology is completely based on electronics. This means that air conditioning technicians must now understand how electricity works within circuits. Before, we only needed to know two conductors, a line and a neutral. We connected a device or a motor and it worked. But now, with inverter technology, we must understand the entire path of electricity within the circuit. We are no longer satisfied with only line and neutral 110 volts, 127 volts, 220 volts. Now we need to understand the entire path of electricity within a circuit. Only then can we understand the inverter technology that is completely based on electronics. The bad thing is that this means that we must specialize in this subject, electronics. But the good thing is that we will also understand what conventional electronic boards are. This will allow us to have a deeper and more complete knowledge of how electronic systems work. Let's start by doing this analysis and understanding well what this is about. A question that we always ask when we start with our live classes, in this case they are recorded, is, what is electricity? Well, some student always answers us that electricity is the flow of electrons, and that's perfect. Whenever we talk about electricity, we are talking about the flow of electrons. A comparison that we often do in order to fully understand how electricity works is to compare it with water. And with this example, we are going to make several points of comparison. For example, let's imagine that we have this circuit. We have a water tank with water and pressure. We are going to put an easy to identify color. Now let's imagine that we have a conductor, and also through this pipe that is going to transport the water we have some resistors that make it more difficult for the water to pass through. This comparison will help us a lot to understand electricity. If we talk about having a water tank with a certain level of water, this will indicate how much water pressure I have in the circuit. We are going to draw here as if they were electrons exerting certain pressure on a circuit. The pressure of water in electricity is what we measure with voltage or tension. If we compare it to water, this would then be the pressure. On the one hand, we have what the water pressure is, as part of the comparison to better understand it. If we continue analyzing the circuit, we have more parameters to take into account, such as the flow or amount of water or electrons that are going to flow through a conduit. This depends on the voltage, but it also depends on the width of the duct. If it is wider, more water will flow. If there is more pressure, more water will circulate. The amount of electrons circulating in a circuit would be in electricity. The amperage, the current, or intensity. If we compare it to water again, we would be talking about the flow. Well, and one more parameter that we are going to analyze with this comparison is a certain part of the circuit that is going to exert a certain resistance to the passage of electrons. The water here is going to have a little more trouble going through the nature of the pipe that we are drawing. In electricity, this is the resistance that we measure in ohms. The higher ohms, the higher resistance. The lower the ohms, the lower the resistance. If we compare it to water, this would be a resistance to the passage of water. Anything that exerts some resistance. We are going to do this comparison between water and electricity very often because it helps a lot to understand how electrons work in an electronic circuit, and we have to understand it well in order to understand inverter technology. Perfect. We are going to add other variants because with this alone, we are not going to understand all the electronics. We are going to understand something that we call, I am going to write here so that it can be seen clearly, alternating current. And direct current. It will be essential that we understand the difference between alternating and direct current because that is what the inverter system is about. Now I will explain a little more. We are going to delete this then. And we will explain what alternating current and direct current are, fundamental details to understand any inverter circuit. Well, precisely, inverter or investor refers to this process. Actually, any electronic board that they are dealing with, these electronic boards, what they do is convert alternating current, AC, into direct current, DC, an inverter circuit to be able to run an engine. Instead of directly injecting alternating current as we did in the conventional system, what it will do is convert it into direct current and then convert it back to alternating current. That is, something is converted and that conversion is inverted again, hence its name inverter system. The motor will work with alternating current in both systems, in the conventional and in the inverter. The difference will be that the conventional motor will work with the alternating current provided by the electric company, but an inverter system will work with an alternating current that will be generated or created electronically and modified. That is the big difference between a conventional system and an inverter system. When this conversion into investment occurs, we call it an inverter system. Well, now the question is this: what is alternating current and what is direct current? If we said that it was the flow of electricity electrons, this difference will be in how the electrons circulate in a circuit. What do we mean? Now let's talk about direct current. Simply, we can draw it this way. A tank with water pressure, and the water circulating in only one direction. This would be direct current. Now, alternating current is a bit more complex, and that's what we're going to talk about now. Let's first look at alternating current. We analyze it in depth and see other parameters to take into account, and then we are going to talk about direct current again, which is the simplest. Let's continue comparing it with water to understand it. Imagine a water tank, a circuit, and another water tank, and there we stay. Now, imagine a water pressure a little larger on one side and a little smaller on the other side. When I pour water into this pipe, what is going to start to happen is that the electrons are going to circulate to that side to produce an equalization of the pressures. Then, the electrons are going to push there. And what if I had a system that constantly causes the water pressure to never be the same, but instead constantly stays with one tank fuller than the other? Well, if you had a system that could do this, the water would flow back and forth constantly. And this is alternating current. So that you understand, this is the electricity that you have in the outlets at home. This would represent the neutral, and this would represent the line. When you plug in a device, one side has more electrons than the other, then there is a circulation of electrons in one direction. Now, the electric company with its motors constantly is just doing that. These tanks never equal. It constantly has one more full, the other more full, the other more full, the other more full. So, the electrons are going to go back and forth constantly. It is true, it is better to use direct current for everything, but this alternating current can be transported long distances with thinner conductors or cables without losing pressure. For this reason, alternating current is used to transfer electricity. If we wanted to move electrons in only one direction, we would need very thick cables, and even then we would still lose pressure. That is why alternating current is used. Our electronic boards, all the electronic board, including cell phone chargers, transform it into direct current in order to use it. Very good. Now there are more parameters to take into account. On the one hand, we have the tension, measured in voltage. We also have the amperage, which depends on the driver and the pressure. In addition, we have to consider the resistance to the passage of electrons when this circuit is powered. But there is a more important data to take into account. How many times do the electrons go to one side and to the other? This data is the frequency. This frequency is what we measure with hertz. In your home electricity, these hertz are 50 or 60, depending on the country where you are. What does this mean? That the electrons are going to go to one side and to the other 50 or 60 times per second. And these times per second are hertz. Now that we understand what alternating current is, we are going to draw it in another way, in a more electronic way, to understand it better. We are going to do a cleaning of our electronic blackboard. And we will draw the electrical conductors. Here we would have the neutral and the line, and here we plug in a circuit in this case. The electrons start to circulate to one side. But in the next moment in time, they would already start to circulate to the other side. They constantly do this back and forth, and they do it 50 or 60 times per second. This represents alternating current. A symbol that is also used to represent alternating current is this wave. Let's see if we improve a bit. It is used to symbolize alternating current. Because the electrons enter from one side and the other. Now, if we want to draw the direct current, as I told you, it is much easier. In this case, we have a negative pole and a positive pole. Where do the electrons come in? I always ask the same question in live classes. Many times many answer that it is positive, but no, electrons are the negative charge of an atom and enter through the negative pole. A clear example of direct current is a battery. A battery represents direct current, while the electricity we have in our homes represents alternating current. Direct current naturally has no frequency, so that its frequency is zero. What is it called? We can find it as DC, or we can also find it as CC, or with its symbol. Like this. In this case, a question I want to answer, if you have it in your mind, is, why doesn't the negative wire electrocute me when I touch it? Let's remember that this negative wire is charged with electrons, and this one has a lack of electrons. My body and the Earth have the same amount of electrons. Then the neutral wire. What does it mean? If I touch the neutral wire and touch the wall, I won't be electrocuted because it is neutral. The difference in electrons, the amount of voltage between the wall, the floor, my body, and this neutral wire, is the same, therefore no electrons will circulate inside me. On the other hand, if in this case the line, I am electrocuted because there are holes here, that is, there are missing electrons. When I touch the wall or the floor and I touch the line cable, the electrons circulate from the wall towards me and from me towards the line cable, and that is where this circulation of electrons burns me inside and electrocutes me. One detail to keep in mind is that if I am not touching the wall or the floor, if I am insulated with rubber or another insulating material, I can touch the line wire or the neutral wire and neither of them will hurt me. Absolutely nothing, because there will be no circulation of electrons. Now if I touch both at the same time, yes, of course I get electrocuted. This explanation is so that you know why the wire charged with electrons does not electrocute me. Let's go ahead. We had said that in electronics we need to convert alternating current into direct current. Yes, every electronic board, to begin with, converts alternating current into direct current. Afterwards, the inverter converts the direct current back to alternating current, but that comes later. The first process. This conversion, how is it produced? What is it called? What elements produce it? That's what we're going to be talking about from now on. So that you know the name of this conversion, we call this process rectification. It is the process in which we change alternating current to direct current. We are going to explain how this is produced inside a platelet. Comparing it with water, you will understand it perfectly. Let's move on. Well, very good. So, to understand the rectification process in our water comparison circuit, we have to add one more element. And this is, many of you surely know, a check valve or a non-return valve. Surely many who study through these videos know what a non-return valve is. For those who don't know her, I'm going to draw her and try to explain her as best as possible. So, imagine we have a component in a water pipe that has an internal shape, more or less like this. What's going on here? If we inject water from this side, the water will be able to pass because it has places through which to do so. However, if we inject water from the other side, it will not be able to pass because the plug or internal core will be placed here and will prevent the passage of water. So, a check valve allows the passage of water in a direction and prevents passage in the opposite direction. This represents a component that we have in electricity and produces the same effect, and it is the diode. So that you can see what a diode is like, I am going to show you. It is a component that we clearly see a gray strip on one side and the other side is broader and black, with a number that indicates The different characteristics of the diode. But, well, there is a difference on one side and on the other. So, these diodes with the electrons are going to be exactly that. Here we could see what they look like. What I'm going to do now is draw them here so we can see them in comparison to our check valve. This would be a diode, with the side that has the stripe thinner allowing the passage of electrons and the other side does not allow the passage of electrons. Its symbol is represented in this way to be able to understand it, also taking it to the symbols. A diode produces this effect. It allows electrons to pass on one side and does not allow them to pass on the other side. This is the necessary element to convert alternating current into direct current, producing the rectification, too, that we are looking for and needing in all electronic board. Diodes have different characteristics, such as the voltage they support, which is the voltage of the electrons. Another characteristic is the amperage that they support, the amount of electrons that can pass before they break, and the opening and closing speed of this check valve, because it has a speed limit. We're going to talk about that throughout the training, but first we're going to understand how a diode works. If you want to investigate a little more about how these components work internally, of course they don't have a moving component like a check valve, they are actually components that are altered. I'll leave it here for you to look for later. It is not a practical topic that you will need, that is why it is not explained here, but equally, for those who like to investigate, they can search the internet or Wikipedia, which is a good and very reliable page within everything. You can search about the contamination of silicon and germanium. You can search the internet to find out how diodes work internally at the atomic level. Well, that's up to you. I leave them as homework if you wish. I am going to show you in practice how these diodes work. We will always have these components located in this position. One more detail to take into account is that on this side we have the cathode and on this side we have the anode, so that you know what each side of the diode is called. If we inject electrons through the cathode, the electrons pass. If we inject electrons through the anode, the electrons do not pass. That is what we are going to do to test its correct functioning. I am going to run this. We are going to turn on the lights and do the measurement. If we place our multimeter in the diode position, you will find here the symbol of a diode. This is the position that will allow us to make that measurement. Notice that these multimeters in each of the positions have several functions. For example, this position has 4 different functions. When we place it, it is the white function. I will explain how this works because it is the one that I am going to recommend, this Unity brand multimeter, which is a very good brand if we want to go to the remaining functions. Later we will analyze one by one. For now only diode, we have to press the blue key, so we press. There we see that we change to the function of diodes. And pay attention to this detail, the data that will mark us on the screen will now produce a resultant voltage, that is, in volts. The multimeter will measure the voltage drop produced by the internal function of the diode, and thus we will check its operation and its status. Always before using a multimeter, it is important to make sure that it is in good condition by touching both ends. Okay. What do we do now? We are going to let electrons pass in one direction and in the other. The electrons always come from the negative side, that is, from the common multimeter, and the other side, the red one, is the positive one that will receive the electrons. We are going to polarize it in such a way that the electrons pass through. The voltage drop that we obtain is 0.597 or 0.6 volts. This voltage drop is correct for one of these two diodes. They produce a voltage drop of 0.6 volts due to their internal composition, that is, their way of working. If we invert these cables, it should show us OL. This tells us that the electrons are not passing back and forth, and that's what we're looking for in a diode. So this diode is in good condition. Of course, this diode is new, as seen here. But in this way its operation is proven. What we just did was to polarize it, or injecting electrons, in two different ways. It is important that these terms are memorized, names that we are going to write here. What we just did was polarize it. When we injected electrons from the cathode, from the side where they pass, we polarized it in direct. And when we injected electrons from the other side, what we did was polarized it in reverse. This component, the diode, will help us convert alternating current into direct current. They will understand it in a very simple way, and they will find it on all plates. However, this rectification process is frequently damaged due to direct contact with alternating current, be it 110V, 220V, or 127V, which is constantly fluctuating, and power can be cut off and restored. Therefore, these components are often damaged quite a bit. Next, we will explain how this rectification occurs. Okay, let's clean up our electronic whiteboard. And now we are going to talk about full wave rectification. What do we mean? Don't worry, they will understand very well. Now let's talk about full wave rectification. With 4 diodes, we are going to transform alternating current to direct current. Let's see if our graph turns out well. More or less it has come out. It was not so neat. I am going to improve it a little. I like it a little more perfect there. We are going to have an alternating current input, and here we have a direct current output, and look how it does it. It is very easy to understand. You know, what we have here are electrons entering here and coming out here. But in the next moment in time, the electrons enter here and come out here. All the time this is fluctuating because it is alternating current. Now we are located at a moment in time. At this moment in time, suppose that the electrons are entering on this side and leaving on this side. When entering with the electrons, we find these 2 electron check valves. If you pay attention, on this side the electrons will not be able to pass because they are encountering a diode in reverse. Then the electrons will be able to pass through this side. Arriving at this point, the electrons will no longer be able to pass through this diode because it is in reverse again, and they will come out on this side. At the moment that the electrons enter here, they will circulate towards here and they will go here, converting this side as negative. Now, the next moment in time when the electrons come in through this other side, what happens? At this point, we also find ourselves with a diode in reverse and another diode in direct. The electrons will be able to pass through the diode that is in direct, and at this point exactly the same thing happens again. They meet again with another diode and inversely, and the only way out of the electrons is through this path. Notice that we don't care if we enter here or here. Thanks to this configuration, which is called full wave rectification, thanks to this diode configuration, the electrons will always be entering the circuit through here. What does it mean? That they will go through the entire circuit that they have to feed, and the output will always be on this side. This always makes the other pole positive. So, just as a full wave rectifier works, when you find 4 diodes on a board, how am I going to show you now? We are always producing this effect. We are trying to rectify. Let's see it like this. Look, here we have 4 diodes and here 4 diodes. Here are 2 rectifiers. A detail, you see them all placed in the same position, but the tracks behind the plate, let's say that they are finished accommodating so that they are always in this configuration. We are going to see another different board. Here we have an inverter system board. Look here, it has the 4 diodes. There is a 5th that I will explain later what it is for. There we have the 4 that are 1, 2, 3, 4, which are placed in a different way. They are not in a rhombus, but it does not matter. The tracks end up accommodating so that they are in this configuration. And these are the wave rectifier circuits complete. Full wave rectification with 4 diodes. Generally, when they are circuits for boards, the diode model used is the 1N4007. We are now going to explain one more and fundamental component of all full wave rectification, which is a capacitor, and with this we are also going to delve into what capacitors are, but I am not referring to the capacitors that we have found up to now in conventional air conditioning, but I mean these capacitors that are mounted on these plates, and that are the largest capacitors that we find in the inverter circuits in the outdoor unit. We are also going to explain how these work and how their state is controlled. Let's stick with that topic. Going on to the next topic, we are going to explain how a capacitor works. If we are going to compare a capacitor to a water circuit, it would be something like the following. Inside a circuit, it would be a water storage, so what's the matter? What good is it to us? Imagine that here we have a water push. And from here we have an exit. What would happen if we have water pressure here? For a moment it stops and then it continues, it stops and continues again. Well, if this were a direct pipe, this cut would directly affect the output. But what happens if we have a place where we have water stored? This cut on this side will not be felt because the same pressure that is stored at this point, even if the water injection here is cut off for a few very brief moments on this side, I will have an almost constant flow thanks to this storage. And that is the function of the capacitors. And why do we need it? Because in alternating current we have this cut in the pressure of the electrons in their tension. Why does that happen? We had said a moment ago that the symbol for alternating current was this. If we draw alternating current on a graph, in a line, we will draw it as follows. What does this tell us? That the electrons enter from one side and from the other, from one side and from the other, from one side and from the other, and this happens, we are going to put it with another color. Between this point and this one. This it happens 50 or 60 times per second, which is the frequency. This circulation of electrons to one side and to the other produces an opposite effect on us. Imagine that you have one electrical conductor and another, and here you have the circuit. The electrons are going to go there. But at the moment when which the electrons are going to change direction, at that moment they stop. To better understand it, we can compare it to the circulation of a car. Imagine that we are with a car moving from one wall to another. So we go to one side, we arrive here, we reverse gear and we go to the other, and we go there and we go here, and we constantly do this, putting it in reverse and first, reverse and first. At the moment of reaching the limit of the route, exactly at this moment, at what speed do I find myself with my car? At this moment I am at 0 kilometers per hour because I have to stop to start turning to the other side. The same thing happens with the electrons, exactly the same at the moment of changing direction. Meaning will be found with these points, which represents 0 volts. And that's where we're going to stop. We don't have any more electron push. All these points are called zero crossing. What happens when I transform alternating current into direct current? Notice what happens when alternating current is converted to direct current. Let's move on to the other chart. So they push the electrons. All perfect. They circulate here. They push electrons, everything perfect and up to here, and it comes out. They push and it comes out. Now, in the moments that I pass through 0, what happens in this continuous current is a push and a cut, a push and a cut, a push and a short. The cuts are short, but an electronic circuit in these cuts that are 100 per second would end up resetting this circuit 100 times per second because they are 100 or 120 depending on the frequency you have. How is this resolved? That's where a filter capacitor is placed. On this full wave rectification, on this full wave diode bridge. We call this area rectification. And this capacitor, filtering. On this side we enter with a voltage like this, sinusoidal, alternating, and at the output of this rectification we have this wave that if it goes to the other side we recover it, we take it to our side, then we have this. "100 times per second we return to 0, but thanks to this last capacitor, what we do is the following, that return to 0 no longer exists. And we maintain it. We can keep it, it doesn't go back to 0 thanks to the capacitor function. As a result we have a constant current, even continuous. That is the function of the last capacitor, to maintain the charge and when it reaches 0 to keep it above filtering it and to have a uniform and continuous current. In practice, I don't know if it has happened, but there are air conditioners that when we turn them on make the startup beep that we all know, but sometimes when we want to turn on what happens is that the equipment turns off. It restarts. Or maybe it restarts multiple times. It's like someone energizes it and will de-energize it again. Many times that problem is caused by a defect in the capacitor. The capacitors cannot be damped, so this filtering is constant, the voltage drops. And the microprocessors reset. That's how it is in inverters, in conventional ones, in all electronic circuits, filter capacitors are fundamental. We are going to measure these capacitors, and we are going to see how they are placed on the same plate. I'll show you below. For example, in this case, let's get a little closer. Here we have the 4 diodes that are rectifying. And if we look, here we already have a negative side and a positive side. Notice that we have a negative side. Generally, when converting direct current, the thickest track is the light green one, thicker. As you can see, there is copper here. They are conductors. Generally, the thick track is the negative and the thinnest track is the positive. If we turn the plate over, we see that this is the case, and that this electrolytic capacitor has its negative side well marked. It is always the line side. Even on the board it is well marked. Here, for example, with white. Here is another capacitor, but I already removed it. This side is the negative side. Note that it is the thick side. This is well marked on the board. These capacitors cannot be flipped, because capacitors are two metal strips or two bonded metal plates separated by an internal material that attracts electrons. In the case of these capacitors, they are a chemical that is prepared to receive electrons from one side and not from the other. If we put them upside down, they can explode. That's why they have a cut above. If they explode, they do not explode towards the plate, but rather they explode upwards and do not damage other components. With this, I want to tell you that when you replace it, be very careful and do not place it upside down. And whenever you work with electronics that work with eye protection, anything that jumps can hurt us. Try to have some glasses to work with electronics. They can scratch very quickly, so you always have to keep them in a place where they don't get scratched. These scratch very quickly. It is obvious that these elements cannot be made of glass for greater security, and you have to take great care of them. We are going to see all this in a circuit, in a sample circuit, and we are going to do, as I told you a moment ago, the measurement of the capacitors. To measure capacitors, we need a multimeter that has the ability to measure capacitors. In this case, this tester, notice that in the same position that we have used today, we have this symbol that is for capacitor. If we press the blue button, we go to diode, and if we press here again, we go to the beep function so that it sounds when there is continuity. And if we press again, we are reaching the capacitor position, and it is always indicated with a letter F because the capacitance measurement of electrons is measured in farads. Now there is a residual capacitance of 10.5 nanofarads. It is negligible and it is from the multimeter. It is something to not pay attention to. Now we'll measure a capacitor. This capacitor that we have here in this sample circuit, it's 22 microfarads. Let's try. No matter the polarity, you can try one side and the other. We let it charge, and there we already have 21.13 microfarads. We are going to press the hold button of the multimeter, thus we save the data. These electronic components have a tolerance of plus or minus 10%. I mean, if it's 22 microfarads, we could have more than 10%, which would be 2.2 more or 2.2 less. It's a little less than 22, but it's in an acceptable range. Up to 20, 19.5 could go, and it would be fine, and this capacitor is fine. This one is fine now. Another measurement that we do in the capacitors is to control their continuity, which precisely or does not have to have continuity, or if it is within an already installed circuit, the continuity must be high, the resistance, as in this case of 10 megaohms or 10 million ohms caused by other components in the surrounding circuit. With this, I also show you that any measurement we make on the board can confuse you with other components that surround it. For example, we will measure this circuit. In this case, we are going to control the diodes and the capacitor. We are going to go to the diode. Perfect. Perfect. Perfect and perfect. For diodes in direct, we are going to test them in reverse. Note that it gives us data, but it is not the fault of the diode, it is the fault of the components that surround it. That's why it may also be that some measurements are a bit strange on the board, but believe me that little by little you will get used to it and you will realize what unusual measurements are worrying about and what unusual measurements are normal. Little by little, with so many measures that we are going to do, they will get used to it. Let's see this capacitor. we have a 1000 microfarad capacitor. We are going to wear down the tracks a bit. Let's remember that these plates are completely varnished and sometimes it is a bit difficult to make the measurements, but what we will do is scratch the tracks a little. Leave the copper in sight. Let's see, we leave the copper in sight and we can now make the measurements. We are measuring this capacitor, which are these same tracks or conductors. Let's measure the capacity and see what state this capacitor is in. We let it charge. We give it a moment. We hope it does. We keep waiting. And it marks OL, that is, it went out of range. Yes, the multimeter does not have the capacity to measure the capacity of this capacitor, but that is not true either, because this multimeter has the capacity to measure up to 200,000 microfarads, but it is 1000, but it seems that a surrounding component sends us a bad reading and is indicating that it is out of range. In this case, we have two options. If we suspect that the problem is the capacitor, one option we can do is unsolder one of the two connectors, lift it. Later in the soldering class, we will see how to do it quickly. And what we do is measure with one of the connectors. It can be measured like this, if the measurement is strange or if they suspect that the problem is that. So far we understood what full wave rectification would be in an electronic board of any type. This process, in inverter technology, is more delicate and fundamental. The difference with a normal electronic board and that of an inverter circuit is that the voltage that we are rectifying for a normal electronic board is only the DC current, which is used for its circuit processor to measure the temperature of the sensors and that alone. But in an inverter system, we have to do this rectification to feed fans and motors. For this reason, this same circuit is larger. And for this reason, in inverters you find large capacitors, those that are going to filter all that voltage that is going to feed the motors, and also the rectifier that tends to get pretty ruined. We are going to talk about that later. Let's continue. In an inverter system you will have a rectifier circuit with 4 diodes, but in a different format. The format of those 4 diodes will be encapsulated. For what reason? Because they consume much more amperage, they get hot, and this format is appropriate to place a heat sink like the one we are seeing here. You have this rectifier at this point. There are the 4 diodes. Notice that 3 connectors are closer together and others are further apart. This is placed like this, but on the other side the connectors are reversed. Here is something interesting, something that I really like to explain. This is quite ruined and it is inside the plate. Something that I like that students can become is to do several tests with the board connected to the equipment and without having to completely disassemble it. If you have disassembled any inverter equipment or if you did not, it does not matter. You will know that when we disassemble an outdoor unit, this part is almost visible to us. That means that we have the possibility of measuring the rectifier, and that is very interesting because it gets damaged a lot. This rectifier, with this format, has, in its 2 internal connectors, the input of alternating current, and at its 2 ends the output of direct current. The one that is furthest away is positive. How is its operation controlled? If you think about it, it is very simple. You already know what is inside here for encapsulated diodes that are together, and we already know how our rectifier circuit is configured. As we look at this, we are going to control this encapsulated rectifier. I'm going to zoom in and light a little more. at the inputs of alternating current, we are going to find two different diodes at the negative and positive output. If I go to the negative from alternating currents, I will always be finding a direct polarized diode from alternating currents to negative, and the same goes to happen with this circuit. From alternating to negative, I always have to find a direct bias diode. These diodes produce less voltage drop because they are bigger, that is, they have more capacity to pass more amps. That's why they are bigger and the voltage drop is less. Here I have two diodes in good condition, but if I invert these wires, it has to do the opposite. It doesn't have to let the electrons through. And that is happening. Now we go from alternating current to positive current. From the alternating to the positive, the electrons do not pass. And if I do the other way around, from the positive to the alternating, in that case, if the electrons are going to pass. And the same would happen the other way around. We will go to the positive and to the alternating electrons pass, and the opposite of alternating to positive, the electrons do not pass. This rectifier is in good condition, and you can do the same measurement on your inverter board. For the moment of the fifth diode, do not worry because I will explain later what it's for. We're not there yet. Don't pay attention to it for now. Now we are going to do the same measurement on our inverter board. Let's remember that these boards are varnished. It is not that we are going to support the multimeter and measure. Sometimes you have to spend a little tin or copper. When there are small holes, and these, it also gives us the possibility of making measurements. Let's measure from alternating current to negative. See if you can see it here, and from the other alternating current to negative, then from alternating current to positive. Now we will invert the cables. No. 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 No, this diode bridge is in good condition. We did exactly the same measurement as the board measurement. You know what is inside this diode rectifier, and you know how to measure it without having to disassemble all the equipment. That is my idea in all the training, that you have this knowledge. Make good diagnoses without removing or disassembling all the pieces of equipment. We have reached the end of the section on the full wave bridge rectifier. Now we will continue with the next topics. To understand a little better how direct current and alternating current work, we are going to do it in two graphs. We are going to draw how alternating current would look like over time, and in another graph how direct current would look like. Whenever we make a graph, this variable is time, and this is going to be voltage. That means that the line is going to represent 0 volts. Sinusoidal alternating current, which is provided by the power company, is created by motors and is drawn this way. The direct current has to be maintained only on one side of the line. That means that the electrons enter through only one side, and it can be represented as follows: a constant line, which perhaps maintains a constant voltage, for example, 311 volts. Later we will explain why we give that value. Alternating current is drawn like this through time because electrons go in one way and go in the other, go in one way and go in the other. Remember our full wave rectifier. What he did is convert this alternating current into direct current, and it is a full wave because the entire wave recovers. That is, this wave that came from the other conductor leaves here, and we recover it upwards. And thanks to the filter capacitor, we already maintain it, and we do not let it return to 0. That is why it is called a full wave rectifier. Now what we are going to do are some measurements with an oscilloscope, a tool that they are going to need to work with inverter technology. This is the one that we recommend. It is bought on AliExpress and it reaches any part of the world. It is not from a well-known brand, but it is of good quality in the world. We are going to use it to measure what we are talking about, alternating current and direct current. In a moment, we are going to make some measurements of the circuit that we have as a sample with the oscilloscope. But first I have to explain something about the voltages or the data that we are going to find when making the measurements. Something very important to keep in mind that will help them open their minds to inverter technology. This voltage that I put here as an example is a real voltage, and it is the real voltage if you have 220 volts that you have in your home voltage. And why? When we propose to measure alternating current with a multimeter, that is to say AC, in reality what the multimeter is going to be is to measure an average that is approximately by this point. At this point you have 220 volts. It can also be 110 or 127, depending on what voltage you have. The voltage that you are seeing with the multimeter is at this point. This wave and this push of electrons is constantly going up and down. If it were a water pipe, it would be difficult to measure the pressure. Let's look at the comparison of water again to understand better. Now imagine that we have a tank with a conduit and we have it circulating with a certain amount of water. If we cover up here, knowing how much water pressure there is here is not difficult because we have a fixed, constant pressure. But now, let's imagine we have this. I'm going to erase the blackboard. Imagine that we have this, and what the water constantly does is change its level from one side to the other, from one side to the other constantly. What is the problem? Control the water pressure, but since we do not have exact data, we have to see it through an average, and that is exactly what the multimeter does when we want to measure alternating current. It is not a real voltage that is there, but rather average, and it is for that reason we will find a value that is at this point. If we want to know the maximum that there is, in the line that we are measuring 220, if we want to know the maximum voltage that is reached at each peak, we have to multiply the voltage by 1.41, which is a fixed factor or a constant, which we are going to use to solve or know the peak of a sinusoidal voltage of 220. This voltage, R, M, S. The voltage that we are going to get with this count, which is almost 311, this is the peak voltage, and these are the peak voltages. And if we want to know how much voltage there is between this point and this point, that voltage is also used and we are going to need it. We have to multiply it by 2 and we are going to have 600. Since it is almost 311, we are going to have 321 of voltage. These are always peak-to-peak voltages. 621. All these data that are new to you, I'm going to mark it with color to better identify it. Wait a minute. All these voltages, which are new to many, are all voltages that we have to get used to. If there are 110, they have to change this data to 110 or 127. All this is managed with an inverter. In fact, if you have already disassembled inverter equipment, you will have seen that motor compressors tell us that they work with 310 DC as long as you have 220. And why do they work with 310 DC? Because when we rectify the alternating current, 310 automatically reaches me, and with that the compressor works, then it converts it to alternating current again, that is left for later. But it will work with a DC of 310. This section can be a bit difficult to understand. I recommend that you review it again and reflect on what you have seen. To make it easier to understand, we will now see how it works with the oscilloscope. One more detail, so that you take into account this voltage R, M, S, or the average. In all sinusoidal waves, to know the peak, that is multiplied by 1.41, which is the square root of 2. One detail that I wanted to say is that this voltage is not an invention, but that this voltage, to understand it, would be as follows. What the multimeter does when it has a sinusoidal wave is calculate how much power there is in total. And if this were a direct current, how much would it be equivalent to? It would be equivalent to 220 volts. We are going to be reaching 310. Because the capacitor is going to be raising the voltage a little more, it is going to be filtering. But if at this power it were converted directly into direct current, it would equal the voltage, RMS. Now we will leave theoretical explanations and drawings aside, and we will move on to make measurements with the oscilloscope. Well, now we are ready to make these measurements. What I am going to do now is also briefly explain how we are going to use the oscilloscopes. Always remember to do any electronic test with protective glasses and with well-insulated shoes. We have to connect or energize this in a circuit that has fuses. Remember, that is very important. We are going to load it. And once we have our circuit energized, we will be turning it on. And we are going to make our first measurement with a multimeter. By the way, also for those who do not know how to use the multimeter, we will also be practicing. First, we are going to measure the AC current. We measure it on this side at the input, and we are effectively finding 213 volts. Now we are going to change DC, and we are going to measure at the output. At the exit, we have 296. Note that we did not have 220, we had 213, a little less, and at the exit we have 296. This is because at the entrance there are fewer. That is why we do not find 310, and also because the capacitor may be a little discharged, and we are going to corroborate that. We are going to corroborate these numbers with the calculator. So, if we had 220 volts, we had to have 310. But since we had a little less, 213, we would have to have 300 and a little discharge the capacitor. And that's fine, we are correct. We are having here now 298 volts. It is very good. There is nothing that raises the voltage. What we have is a rectification and filtering that it allows our attention to drop to 0. Now we will see this with the oscilloscope. Oscilloscopes have a test lead that is different from a multimeter. These oscilloscopes have no polarity. I can put them negative or positive without getting damaged. They don't have polarity, it's battery powered. So we have it set up. Then I am going to explain step by step how it is used and what each function is for. But the most important thing I want you to memorize is that if you are going to measure voltages of more than 30 volts, remember to switch it to 10x, because in this case, I activate a resistor in here so that the full voltage does not reach the oscilloscope. That is the most important thing, so that it does not burn. When they do that switching, they also have to notify the multimeter. Notice that here, it has a button in which we are going to notify it that we are going to change it to 10x. Remembering that is the most important thing. We are going to measure alternating current first. We then place it, and we are going to measure the alternating current input, and we find, sorry, it was not seen now, and we find here, I am going to take it out and put it back to see again. And there we find the sine wave. Notice the values, pay attention. Peak voltage 308, 312, peak to peak voltage 612, 620. RMS voltage, which is what until now you knew that there was tension, almost 220. Okay, now it has risen a little bit. See, these are the voltages that you already know, 220 and 50 Hz. But there are also these voltages that we now have to know for electronics. They are in the line, they are in the voltage, but only an oscilloscope shows us what happens through time. It can show us. So now we are going to measure the direct current at the output of the capacitor. We control after the capacitor and see what we find. With a line, simply with a line, 0 of frequency, 300 RMS, and 300 peak voltage is nothing else. It's just a line, and that's it. This is what direct current is. Simply electrons entering from one side. 0 frequency. Here you are seeing how this rectification is produced. Now we will talk about the fifth diode. Regarding the fifth diode, its function is to have a point where I can control the voltage, but without being affected by the capacitor. Remember that what was happening here was a sinusoidal wave. We are going to graph it here. Remember that here we had a sinusoidal wave, and as soon as we pass the filter and the capacitor, we already have direct current. But what I need for certain functions of the platelets, which we are going to go deeper into later, is a part that allows me to measure this effect, and that I can control how many times it falls to 0. A certain electronic circuit, so to speak intelligent on the board, needs to know at what moments in time we are falling to 0. But thanks to the capacitor that no longer exists, I actually lose it. I lose it and it is cleaned. So what the diode does is that, at a certain point in the tracks, the effect of the capacitor does not affect. I am going to show you directly. This is still direct current, but not filtered. On one side we have one side of the capacitor, and on the other side, we are going to measure here before the diode, and look what we have here. There it is. This is a bit higher up, but well, the oscilloscope adjusts it so that it looks better on me. But look at what we have. We have the waves rectified to one side, but without filtering. So from that point the microprocessor can observe at what moment in time it crosses 0. If you look more closely here, notice that we have a peak attention of 300. From peak to peak it is also 300 because the electrons do not, they go the other way, and the frequency is 100 Hz. Because it falls to 0 100 times. Twice the frequency of alternating current. If you had 60 Hz, it will fall to 0 120 times. And that is the function of the fifth diode. It is to leave us an area to measure for two functions. I'm going to give you a brief preview. On the one hand, to make a fan or fan work, and on the other hand, to correct the PFC, the power factor. When we want to correct the power factor, there we need a division between the effect of the capacitor and detect this. But we are going to see that later. The idea now was to show you how this circuit works and how it is measured with a multimeter and how it is measured with oscilloscopes. One more important detail: whenever you work like this, take into account that the capacitors, if they are not in a closed circuit, remain charged. In this case, I am going to de-energize. And I am going to make a small short circuit so that you can see the spark that is produced, to see if we can observe it. Let's zoom in a bit. There it seems to have been seen. I clarify that this is not discharged in this way because the capacitor can be damaged, but I did it for you as a sample so that you can see that you have to be careful. Look at this capacitor and notice how big it is. The size of my thumb only. Just imagine with big capacitors it's more dangerous, so be careful with that. Here we can see the burn that it produced in the metal. To continue with our training, we are going to be talking, after having seen such an important topic, how to know how electricity works. We are going to be analyzing the different parts of an electronic board. We can say that every electronic board is divided into two main and fundamental parts. One that is damaged more, one that is damaged less, one a little more robust, and another one a little more delicate. What are these two areas? We are talking about the source area and the control area. What do we mean by this source area and control area? Source area, we say, any part of a board that is dedicated to prepare the voltage or prepare the flow of electrons in such a way that all the rest of the plate can use it. I repeat, prepare the voltage and the circulation of electrons so that the control zone can now use it. In the source part, we have already analyzed a very important area, which is diodes and capacitors. We have already been talking about the four rectifying diodes, the fifth division diode, the capacitors, which in this case are two. Now we are going to follow this circuit and understand it, but that is not the only thing that is involved in a source area. In the source zone there are more components, and that is what we are going to analyze now. This is the most robust part, and it is the one that gets the most damage because it is in direct contact with the line voltage. One good thing about this part is that most spare parts are available without any problem, so that is an advantage. Also, but what other component can we find in the source zone? We will start from where the electricity enters, that is, from where the line enters and from where the neutral enters in an electronic board. We will see it in the following electronic board of a conventional equipment. A component that you will find in any electronic board, especially the most expensive ones, such as air conditioning, refrigerators, and washing machines. They will find a fuse and a varistor. Inside this little box, there is a component that usually explodes when it reacts, and that is why it is covered with this plastic. But inside it we find a varistor. How does a fuse and varistor work? They are a circuit as a whole, which what they do is protect the electronic board against high voltage. We are going to draw it in this graph to understand it a little better. We are going to make some graphs to understand. Until now what we have been seeing was the part of the circuit that is in charge of rectifying the voltage. That is, we were talking about the 4-diode rectifier and the filter capacitor. But this is not where electricity enters a board. There are still components before, and something that you are going to find. Precisely is a varistor. And a fuse. Here, then, we have our AC voltage, which can be 220 or 110 or 127, and here you will find a fuse and a varistor. Whenever something is placed in continuity with one of the two conductors, it is said that this is placed in series. And whenever something is placed in such a way that it joins the two conductors, we always speak of line and neutral. We say that it is placed in parallel. Very good, now, it's better. How do these two components work? Well, it is a very simple way of working. This is a varistor, In other words, it is a resistance or a variable resistor. The resistance value of this component varies depending on something. In the case of varistors, it varies in function to voltage that it detects at each of its extremes. Let's look here. Here we have a varistor with 385. These varistors are generally used when there are voltages of 220, but the voltage of 220, as we have already seen, is actually 310. What happens then? When the voltage approaches 385, what the varistor does is let the electrons pass. We are going to draw them that way we understand it. It lets the electrons pass. It detects more voltage. It lets the electrons pass because its resistance drops, and since so many electrons pass, what the flow rate increases, and they exceed the value of this fuse, which could be due to example 315 amps. What happens then? That fuse opens. The varistor makes a short circuit, and when the fuse opens, the circuit is completely protected, the circuit is no longer closed, and it is de-energized. This is a protection against high voltage. If the voltage rises to perhaps 265 volts and alternating voltage are ms, that's when it's going to trigger the varistor, it shorts and it's going to explode. If you pay attention, the varistors are a ceramic and two wires that touch. Of course, each one has different values depending on the point where it is working. These are 471, these are 385. And if you have 110 volts or 127, of course the value will be different. When replacing them, you have to get the one that is identical to the one that the circuit originally had. But how do we know that it is in good condition? This is easy because the component has to be open, so to speak. It doesn't have to produce continuity. We put the multimeter in continuity, we will measure its connectors, and the result has to be open line or several megohms, perhaps 10, 20 megohms, or open line as in this case. This is in good condition. You will find it in blue or yellow. Regarding the fuse, which is also part of this circuit, the fuse has to have direct continuity. We can put the multimeter in the sound function so that it sounds when continuity is made, and there just has to be continuity. If it is going to be replaced, it must be replaced with one of the same voltage and the same amperage as the one it originally had. Here we can see the values of the fuse printed on the electronic board. One more detail to take into account. Some think that since the board has a protection against high voltage, so the high voltage problem would be solved and I will never have problems with the board. Actually, it is not so. It is not an absolute protection against high voltage. Why? Because actually this varistor has a response time. The response time is from 5 to 20 nanoseconds. For us, this is an insignificant amount of time. It is instantaneous, but if lightning were to strike, it is a short time since lightning can burn other components. I mean lightning, an electrical discharge from a storm, it can burn other components, and the varistor will not react in time. Take into account that a definitive protection so that a circuit is not affected at all by what happens on the line is a UPS, uninterruptible power supply system. This definitively protects a piece of equipment. It is a device or component that it is added in the electrical installations. If they want, they can investigate. Although it is a definitive protection to all devices, the UPS can be damaged. In reality, there is no definitive solution for line voltage problems. Here we were able to analyze how a protection circuit against high voltage, varistor, and fuse work along the circuit of an inverter board. 2 are also going to find other varistors and other fuses. So it is good that from now on you know how it is the operation of these components. Well, we are going to continue advancing, and we are going to explain another component that you will also find in the source area. We are going to locate it in this area, and we are going to draw it here. This component is the transformer. Its function is to reduce the voltage. In order to work, it needs to have alternating current. A transformer, if we disassembled it, would be several plates in the form of E and in the form of I, glued one above the other, in which there is a copper winding, which makes a sinusoidal wave, which constantly makes the electrons go from one side to the other. It magnetizes the core, and that magnetism excites the secondary coil. Primary and secondary. And makes the electrons come out the other side with a sinusoidal wave, but with different voltage. If we have a 220 volt input here, the output will depend on how the transformer is made. In the air conditioning units, we will generally find a 12 volt output. How does a transformer reduce voltage? We can compare it to water, since in this way we will easily understand it. Imagine the following. Imagine that we have a thin water tube that ends in a thick tube. What happens to the water pressure at this point? If the water pressure at that point is high, the water pressure in this area will be lower due to space issues, because here we have more space for the water to pass through. The same principle of operation has the transformer. High pressure for a thin pipe. When we find a thick pipe, low pressure. That is why the copper winding on the primary side is much finer than the winding on the secondary side, which has to end with low pressure or low voltage. This is important to understand, because now I am going to teach you how to check if it is in good or bad condition but without voltage, because perhaps what you do is inject voltage at this point and measure from this other side, but we are going to do it a safer way. We are going to corroborate it with resistance. Let's grab our transformer and set the multimeter to resistance. In resistance. And what we are going to do now is control the primary side. The primary side is generally the thickest wires, and the secondary side is the thinnest wires. We will control the primary side. And look that we find. This is an auto-ranging multimeter, so 0.569 kiloohms. We actually take out the comma, we take out the K, which means multiply with by 1,000, and then we have 569 ohms. We are going to confirm the secondary side. And on this secondary side we now have approximately 3 ohms. 3 ohms. What does this tell us? Let's draw it to understand it better. On the primary side, we find 569 ohms. And on the secondary side, we just found 3 ohms. Clearly, the primary winding is much thinner and longer than the secondary. That is why it exerts much more resistance to the passage of electrons, while the secondary side exerts less resistance to the passage of electrons of only 3 ohms. In a transformer that is in good condition, they will find a resistance of between 150 to 600 ohms on the primary side, and on the secondary side, they will find 1 to 5 ohms. Approximately. This is a good way to tell if a transformer is good or not, because you are doing it by measuring the resistance of the coils. If this side, the primary side, gives us L, ISO significant open line, this means that what happened with the transformer is that it cut off, or if it gave us, perhaps, a resistance of 2 ohms. Obviously something is wrong, it's short-circuited, something that is also harmful. If I inject 220 volts with 2 ohms, I will surely make a big spark and it will burn even more. And it would pass the same on the secondary side if I have a very high resistance. Surely something has charred, and if I get L, obviously this coil has been cut. Taking into account the parameters, within all normal, that a transformer brings, you can know if it is in good condition. In this case, L is bad. 2 ohms would be bad. L would be bad. And these are the values we just found in the sample transformer. One more detail regarding the transformer: if they come across a transformer that marks them on the primary side L, if they can change it, they will change it, but if they perhaps do not have the spare part, they have the option of disarming it in this area. And in this part there is a fuse, and since the electronic board has a fuse, you could make a bridge and put it to work again. If this is the problem, the internal fuse, you can disarm here and try that method. Another detail so that you do not get confused: a moment ago I told you that the primary side was the thinnest winding, and the secondary side was the thickest winding, although visually it is exactly the other way around. But why is the thinnest side actually thicker, and the thicker side internally is thinner? Well, this is a matter of protection for us. Although the winding is much finer on this side, it handles more voltage and could be dangerous if it is bitten by a cable, it gets pinched, or it gets in contact. Instead, on this side it handles 12 or 24 volts. We don't need to put such thick cables to protect people, but internally it's exactly the other way around, remember. A thinner pipe with high voltage flows into a thicker pipe, from which the voltage is lowered by decantation. The transformer, another important piece in the source area. A detail to remember: transformers only work with alternating current. It is an important detail to take into account for other issues that we are going to discuss later. They also have another way to test it. If you already see that the resistance is correct, it is to inject voltage on the primary side and measure the voltage on the secondary side. This is always with alternating current. Measurements with the multimeter in DC current not. We change the AC option. Excellent. This is what it has to do with the transformer. Now let's go a little further and talk about other components that we are going to find in the source zone. I'm going to clean the tablet. And we are also going to talk about other components that are part of the source zone, that are always close to the rectifier and the filter. Excellent. We continue. So moving forward, we are going to clean up. Perfect. Very good. Very good now, yes, perfect. We are missing something here. We have not yet arrived, but now we are going to talk about what we found after the rectifier and the filter. What are we going to find in this area? Good. In many plates you will find here with a component called 7805. So, you will find this as follows. You will find the component here, and it has its number clearly marked, 7805. It receives a voltage and direct current, and what the component does is allow an output with a constant voltage of 5 volts. This 05 is indicating that the output voltage is 5. It can also be found 7818 and 7812, to take into account that they can also be found with different values. But their function is the same: to produce a regulated voltage output, precisely its name of voltage regulator. Let's remember something. We are entering here with 220 volts in alternating current. We are going through a fuse and a varistor that does not change in electricity, only going to protect against high voltage. We are going to go through other components that we are going to talk about in a while that do not modify electricity either, but this transformer will modify it. Of the 220 alternating current that we are receiving, I use 220 as an example, but it can also be 110 or 127. After the transformer, get 12 volts in alternating current. We are going to go through the rectifier and the filter. Remember that here what we are going to obtain, it is not a voltage of 12 volts, we are actually going to have a higher voltage, due to the fact that we are now going to have the peak voltage. Remember, if we do 12 times 1.41, we are going to receive almost 17 volts. At this point then we are going to have 17 volts, but in direct current. With these 17, positive pole and negative pole, we are going to enter the 7805, whose left terminal is positive input. The one in the middle is negative and the right is positive output. And we are going to leave with 5 volts. Finally, they will also find a small filter capacitor to maintain these 5 volts so that when required it does not drop. They will also find that capacitor here. At this point, we are finishing with the source zone. So here we can name all this as a source, and we are going to add one more detail. Conventional source, because later we are going to move on to a more complex one. Well, how does this device work? 7805. In the case of this component, 7805, which is what you are seeing here. The brand can be different, it doesn't matter. What is important is the central pattern. What this component needs to receive a voltage. A moment. I am going to write you here so that you can be clear about it. He needs to receive a voltage of between 7 to 37 volts. Whenever he receives this voltage, can produce an output of 5. These are characteristic of the component. In this sample circuit, we are getting 17. It is within the range that the component needs to deliver a constant 5 volts. If we have a 7812, at the input it has to be greater. The input has to be from 18 to 50 volts. In this case, the component can deliver 12 volts. regulated. These they are data of the component. In our circuit, this 7805 is receiving 17 continuously. Correct to be able to produce 5. I am going to show them with a board. For example, in this case, here we have a bridge rectifier, of which 2 diodes are no longer there. Here we have a filter capacitor. And here we have then the 7805, and we see it clearly 7805. And after the output, here we have the last capacitor. So, these components are the final ones in the source zone. The voltage regulators can be 7805. Or also, they can be found with 7812. And at this very moment, I am going to show you an image of plates that 7812 have. If you give me a moment, I will show them to you so that you can recognize them when I touch them. Pay attention, this board has the 7812 and 7805. It has both. On the one hand, it is getting 12 regulated volts, and from it, it will feed the 7805 and get 5 regulated. These are older plates of better quality, with more protections. Finer their way of working had more components. Today, they try to get components to that everything is cheaper as everything is true. This is the plate that we were looking at, a fairly old plate, and here it is 7812 and 7812. Very well, so this is the component that you are going to have at the end of the source. How it is controlled? Well, this component is controlled by energizing it. If I wanted to control it and see that it works well, what I would have to do is make the board work. Check between the middle and the left side, which is the input. And if I get between 7 and 30 and 7 in direct current, between the center and the output, I have to have 5 volts constantly. If the board still does not work even if we have 5, try or check the capacitor. It may also be that it is devalued, worn out, burst, exploded, and that because of it the 5 volts are not constant. Remember that. Remember that many circuits are powered from these 5 volts, not only the microprocessor, the sensors, fan rotation sensors, and several more circuits. Well, this is what it has to do with the 7805. Later on, we are going to do a test with this sample board, and we are going to be powering and controlling the inputs and outputs. So let's take a good look at how it works in operation precisely with voltage. But we cannot measure this component without voltage. The way to measure and control is by feeding it, because it is a circuit within it. It is not just a component. So far we have talked about voltage regulator. To continue with our training, now what I am going to talk about is about the components found in this part of the circuit. We still need to explain. This area is an important area. And by the way, they are going to learn several things, also very important in inverter technology. So we are going to clean our tablet. I am going to do a cleaning. And we are going to continue talking about these components, which are filters, low pass, or filters, double PY, or noise filters. And their configuration is as follows. We will be finding a coil in series, another coil in series, a capacitor in parallel, and another capacitor in parallel. And this is the area we are going from to be talking What is this zone? What does it mean? What does it do? What is its function? It does not modify the current, since we are not in a part that modifies the current. What do I mean? That on this side we are, with 220 AC. And on this side also, the current does not change. But what this component does, these four components, is not allow anything that happens on this side of the line to affect the electrical installation of the home. That is, anything that happens here with the circulation of electrons, any modification that we give, does not pass to this side thanks to this low pass filter. And how does this filter work? To understand, we are going to be talking about how everything that is winding and everything that is capacitors works. But first I am going to show you physically like this they also recognize it. And if they have any platelets and they are observing, that they can identify them. Let's observe this plate. In this case here we have two windings in toroidal shapes. It is called like that because of the format they have. And two capacitors are very low capacity capacitors. Here we have the coils, the line input and the neutral input. That is, these are in series, and these two are in parallel with the line and the neutral. Well, what is the function they fulfill or how do they work? We had said that capacitors store electrons. Then, if we had said that capacitors store electrons as if they were a buoy or a ball of water in the path of a pipe, when we talk about coils, precisely we can say that it is the opposite. A coil would be something like this. Let's see if we get the drawing. We are talking about a motor pump. What it will do then is that when water enters in the capacitors, it is stored in this area, and a moment later, it comes out a little late through the other hole. But in the case of the motor pump, when the water is entering here, this motor speeds up the circulation of water. It delays. This advances. And that is the function in electrons of the capacitors, and the coils exactly the opposite effect. This delays, and this pushes. Then, to pass it clean again. Let's imagine that we have the following circuit of water. If we compare it with water, we have a water storage. And here we have. Now I will try to draw better. There is a motor pump. At this point, even though the water that I entered perhaps has certain frequencies, that is, imagine that water enters but is cut off. Enters but it is cut. It enters and it is cut. It enters and it is cut. There are some cuts or fluctuations in the water supply, thanks to the fact that we have stored a lot of water here. And here we have a pump that will be absorbing and pushing it. On this side we can have a constant supply. Something like this would be a cistern system, for example, that is placed in places where we need good pressure of water, and that is constant. In the same way it happens in electricity, when we have many modifications in the flow of electrons. Until now we are seeing a board or a conventional source that the oldest inverters had it. Today inverters do not have this type of sources. What do I mean by this? That these are very simple sources, and even so they modify the circulation of electrons quite a bit, so that all this does not affect the line and other household appliances, or so that the much more complex inverter sources do not affect the household appliances. These low-pass filters are placed, which do not allow those, so to speak, high frequencies pass to the other side. That is the function of these low-pass filters. And with what I am explaining to you about how capacitors work and how coils work, we are also getting quite a bit ahead in a topic in inverter that we are going to deepen much more. What is an inverter circuit component that I am going to show you now, so that you keep in mind that we are going to deal with a little later? What are the reactors? The reactors in the inverter equipment that you will find are sometimes on the motor side, and sometimes you will also find them mounted on the board. These reactors fulfill a similar function between large capacitors and reactors. They fulfill that function, and we will talk about that later. But you already know how coils work when they are in series, and you know how capacitors also work. What effects do they produce in the circulation of electrons? Let's go back to the topic we were mentioning a moment ago. We're going to continue talking about our filter, because it has this format, a format like that. How are they going to see now? Because it has this configuration format on the board. It is usually called a double pi filter, precisely because of the Greek letter pi, and because of the shape of that letter. They saw that the Greek letter is like this, and it would look like a double pi, since it is inverted on both sides. So it is called that way, double pi filter. But it is a low-pass filter. I really know that it only allows low frequencies to pass through, but not high frequencies. We are going to write it down here. And it is also called a noise filter. It is the same as U2. They are found in washing machines. Many times where electricity enters the washing machines, there they have a component similar to a capacitor, and inside that they also have filters. So that what happens with those motors with coils does not affect other household appliances. Now comes the question, how do we test its state? How do we know if it is good or bad? In the case of coils, it's continuity. If I measure with the multimeter, the continuity must be 0, 0. It must pass electricity directly. In the case of capacitors, the line must be open OL. But what happens in a circuit like this? Keep in mind that if you are going to test these components inside the board, and if you give continuity between this and this point, or if you want to measure this and this capacitor, what the multimeter will mark is the resistance of the transformer coil. Keep in mind that if we measure between this and this point, in reality what the multimeter will do is pass the electrons through here and mark the resistance of this primary coil transformer. Keep in mind this detail because it can give us a confusing data. But if we remove the capacitor, the resistance must be OL, it must be an open line. Let's see it on the board. To be able to make the measurements that correspond, we find a coil. On this board, we place our multimeter in resistance mode. And then, always scraping a little bit of the varnish, we test, and there we have 0, 0. These are the coils. Now, if we measure the capacitors that are placed at these points, we can move away a little and measure up to here, where there is a soldered part without varnish. We have 3 or 4 megohms, 25 or less is fine. This is not the result of the capacitor, but rather of the other components that surround it. The important thing is that we do not have 0, 0 because we are measuring at the ends of the capacitors, which are the line and the neutral. If we have 0, 0, when we energize the board, there will be a short circuit. One last detail to keep in mind on these filters. Let's look at another board that also has some filters, but only has one coil and one capacitor. If a coil gets damaged, what I can do is to make a bridge to skip that coil. Of course, this is just to test the board. Once we deliver the board to the customer, we have to put it back together, of course. But you can make a bridge and test the board. In the case of capacitors, when I remove them and see that they are damaged, what I do is not leave them installed and test the board without the capacitor. To see it here again, if you find damage to the coil, what I will do is a bridge so that the board continues to work. And if you find damage to the capacitor, what I will do is remove it and test the board without the capacitor. And before delivering to the customer, of course, look for a replacement, look for a similar coil with similar characteristics, and also look for a capacitor with similar characteristics. Everything is printed on the board. In the case of capacitors, you need to look for their capacitance value and their value in farads. In the case of coils, you can look for a similar one that has the same wire diameter. This is important because the electric current that will flow through the coil depends on the wire diameter. The value of the capacitors is printed on the capacitor. In this case, we are seeing a 0.22 microfarad capacitor and 275 volts of alternating current. So you can look for a replacement. In the case of coils, you should look for a coil with physically similar characteristics. You cannot put this coil in place of this one because it is in the circuit and supports much more electric current or electron flow due to the thickness it has. So you should pay attention to that detail. You should place a similar coil when you make a replacement, but to test, you can remove it directly. We will continue to talk about coils and capacitors a little later when we go much deeper into inverter technology, but until this moment we have a fairly general overview of everything that is a conventional source. So, to give a brief summary, in a conventional power supply we have the electron input, high voltage protection, some components for filtering, voltage reduction and rectification, the last voltage regulators, which will be creating a regulated and constant voltage for us. An additional element that can be found is a resistance. If you find any resistance, the function is to slightly dampen the voltage that feeds the 7805. You may find some resistance in that area, such as the one I will show you now. This is a large resistance. We will talk about resistances later. how to measure their values, and how to replace them. Very well, so far we have covered this conventional power supply. We will continue to advance with slightly more complex topics. Up to this point, we have been talking about conventional power supplies. However, in inverter technology, we generally find more complex power supplies, switched mode power supplies. What do we mean by that? We refer to systems that transform electricity, modify it, and leave it ready to work. But they are more complex and more efficient. Basically, this change was made for the following reason. We are going to open a new board and start talking about switched mode power supplies. The main reason is that here we have less hysteresis losses. We will not complicate ourselves too much explaining this because it is not relevant, but to explain it in a simple way, you remember that these transformers were always heating up. Always heating up. If you touched them, they were always hot. This is due to hysteresis loss, a resistance that iron exerts on the circulation of electrons, to say it in a simple way. Today, these switched mode power supplies do not have hysteresis losses because the material with which the transformer is made is no longer iron, but ferrite. And that helps us in this aspect of not having hysteresis losses. In addition, another reason why manufacturers started creating these switched mode power supplies is that they also save on materials, because now the transformers are much smaller. Those large and heavy transformers are no longer available today, and what we have is this. In a complex power supply, notice that we have the transformer the size of how many? Not even an inch. They are more complex. For us they may complicate us a little more, but they can be understood very well in any case. Now, let's gradually understand how they work. Today, we do not have the same circuit that we had analyzed. We do not have the same thing in a switched mode power supply. We have the components, but in a different order, and that is what we want now. In a switched mode power supply, we will have a voltage input, a fuse, a varistor, a double pi filter. You already know how all this works. After that, we go directly to that component that you already know how it works. A rectifier and a filter. The big difference is here. In a conventional power supply, we go to a transformer, we reduce the voltage, and then we go to the rectifier. That's why we enter with 12 and we come out with 17 in direct current. In a switched mode power supply, we go directly to the rectifier with 220 volts in alternating current, or 110 or 127. And we come out with a rectified of 310, 155 or 180. Be careful with these switched mode power supplies, because since you are already seeing that we are working with very high voltage, we have to be more careful when working with these power supplies. That is why these capacitors, the diodes, are not. They are usually the same 1N4007, but these capacitors are yes of more voltage, because they store much more electron power. Pay attention to this detail. In the next module, I'll explain capacitors and their characteristics, but right now, I'll continue explaining switched mode power supplies. So, what are we going to find now? We'll find a small gate. There's a detail that I don't know if you've already noticed or observed. I told you that any transformer has to work with alternating current, so the question is, if we had an alternating current of 50 or 60 Hz here, and we still have to go to a transformer, why would we rectify it and end up with 0 Hz? If we need alternating current for this transformer to be able to reduce the voltage. Indeed, as these ferrite transformers are so efficient and do not store heat, or do not prevent electrons from flowing from one side to the other, we can do the following. Instead of giving it 50 or 60 Hz, we take it to 0. And with this switch or gate, we take it back up again, but now with much higher frequency to be able to have much more output power in a much smaller place. So, at this point, thanks to this switch or gate, you'll find a frequency of 90 to 140 kHz. What do I mean by kilohertz? 90 kHz are 90,000 Hz. Imagine that the electrons are excited from one side to the other at that speed per second, very quickly. In a much smaller space, the same power can be supplied from the other side. That's the goal of switched mode power supplies. But how does this happen? How does all this effect happen? Let's look at it this way to understand it. We have a flow of electrons here, which pushes towards here and an output towards there, because this is direct current. With this component that is a gate that opens and closes commanded by another circuit, which we will discuss later, this component that opens and closes, what it will do is send electrons and let them stop passing. It sends electrons, they stop passing, it sends electrons, they stop passing. But what happens? When I send electrons from this side and make them stop passing, the electrons charged in the coil, they will circulate towards this side, crossing this bridge that you have here. This bridge is a diode. It allows them to pass to this side, but not to this. So I let them pass and they circulate towards this side. I cut the flow of electrons. The electrons that are charged in the coil, or that the coil is generating at that moment, as we discussed today, and that every coil generates electricity or pushes electrons, these electrons that are here push them to the opposite side and they are discharged through the diode. Thanks to that, you constantly have inputs, outputs, inputs, outputs of electrons, and a kind of alternating current is produced, but with a very high frequency, a frequency of 90,000 to 140,000 times per second. And that same thing comes out from the other side, but now yes, with a reduced voltage. On the other side, we don't have 310 anymore, but on the other side of this transformer we'll have 5 volts, always with a current, always with an alternating current, but with a very high frequency, which is no longer a sinusoidal and rather square this alternating current. It no longer has that sinusoidal format, but it doesn't matter, it's the same. As these transformers are so efficient, they allow manufacturers to put more outputs. They can have an output of 5, they can have another of 12, they can have another of 15, because they are very efficient, they work very well, and with so much speed, you can create what you want from the other side. All this allows these transformers. A component that they avoid putting is the 7805, because they can have several output voltages directly. The 5 volts are created directly after the transformer. This is very interesting. This detail is very interesting to understand and understand how they save money in other ways. Now, the question is the following. We want to see this component. We want to see it. We want to see the transformer on a board, and we'll see it now. In this video, we will see how switched mode power supplies work on boards. We will use the example of a board from an inverter kit from Goodweather or Panavox, as they use the same board. Let's take a look and get used to tracing the tracks on the board. We're going to pay more attention and zoom in a bit. With a lot of patience, we're going to trace the electricity or the electron circuits inside the board. We can see that there are 2 power lines, the line and the neutral. On one side, we have a coil, and on the other side, we have another coil. At this point, we have a capacitor, and at this point, we have another capacitor. These are the filter capacitors, and the coils also perform the same filtering function. If we continue along the path, we will go to this point. Now let's skip the fuse. We can see that the fuse and the varistor are a little far from the low-pass filter, but they are still the same components. Here we have the line. We skip the fuse. This is the fuse symbol. We see it here. And here we have the varistor. As you can see, it is stored in this plastic. Here it tells us its voltage. If we continue to travel, we can see that here we only have bridges to be able to jump this track. These would be the W28 and W29 bridges. Following the path, we find a small thermal resistor that protects against any high temperature in the area, but simply the electrons pass. At this point, we find the 4 diodes. These 4 that are here that I have marked in black are the 4 diodes that produce rectification. From here, we jump with this to here, and with this to here, and with this to this point, and with this other to this last end. We will see how the diodes are configured from neutral and from the line. Let's see who 2 diodes we find from each side. Notice that we find a diode in reverse, another in direct, the other in reverse, and the other in direct. These are the ones that will produce the rectification. Then, from the side of the positive, which is this point that we have here, we will find the 5th diode. As I told you, it makes a division between the effect of the capacitor and the unbuffered rectification. From this intermediate point, before the 5th diode, is where a sample will be taken to this circuit, which I will explain later, which is the zero crossing detection. From here the sample is taken. If we jump to the last diode, the 5th, here we have in parallel a capacitor to which some last noise filtering coils have been placed. It is very appropriate to place them in this area. Here we have another capacitor. In reality, what this manufacturer has done is to place 2 10 microfarad capacitors instead of one of 20 or 22, but has placed 2 of 10. Now, what do we find after? One of the 2 ends, or the positive, will go directly to the transformer. This is a repaired board, so you are seeing all these details. It will go to the transformer, the negative will pass through this component, and then it will go to the transformer. This component is the key that will be pulsing 90,000 to 140,000 times per second. The number of times it pulses will be fixed and constant, depending on the model of this component. These components have an 8-pin format of which generally 7 are used. For example, here we can see a different model. These components have their input and output on opposite sides, and the rest are different signals that it will receive. Not to know how many times it will pulse, because that will be given to it by the same component. It is a fixed pulse. This transistor and this integrated circuit have a fixed pulse, but if there is something that will vary in the way it pulses, we will talk about it in a moment. How do we check the operation of this component that often burns out? This component, this switch, is a MOSFET transistor. If we compare it with water, it is a gate valve that allows water to flow and blocks it. It is simply that, receiving a signal to be able to open and close. The voltage it has to receive is approximately 15 volts. Then it opens, lets the electrons pass, cuts the passage, the electrons return, and through the return diodes is where the turn to the other side is produced, and the alternating current of the primary side of the transformer is created. Advantages and disadvantages of this source when repairing: it has many components and is not like a conventional power supply. This makes it more complex to repair, but it also gives it some advantages. The transformer almost never breaks. The other components, such as the switch and the diodes, are easy to find. This is another advantage because it makes repair more economical. So, how do you test the operation of this component that I mentioned a moment ago? We'll see. To test this MOSFET transistor, we will be analyzing it in the following way. We can observe in the circuit where the negative input is, and we can see the output to the transformer, which are usually the thickest tracks. When we have identified it, we need to put our multimeter in resistance mode and test between this input and this output. The resistance must be high. As we can see here, it must show us megohms, very high kiloohms, or megohms also, as in this case. Look, it looks a bit bad because of the light. Now yes, megohms must be showing us. It has to go up and down, it has to be varying. In this case we have it in good condition, not only because of the component itself, but also because of all the components that are surrounded. This is the approximate value of a power supply in good condition. If it shows us OL in this case, something would be defective. Or if it shows us 00, direct continuity, surely something is wrong and the power supply will not work. This is because a transformer, if this switch is stuck, will receive direct current and will not work directly. This is an approximate value that a MOSFET transistor must indicate to us. If we had a switch outside the board and wanted to test its operation, we would have to do the following. We will grab the component, and we need to know its characteristics. Look, in this case, let's see if we can see it. Here we have one LN364PN. Here we can see one, but we are going to see a different model. This one I like more, it looks much better. TNY264PN, that's the number that's going to matter to us. Gradually, you will get used to it and you will know which code identifies them. The one at the top is simply a factory code, the one at the bottom is also a serial code, but the patent that indicates how this component is made up inside is TNY264PN. That is what you will be looking for on the internet. An electronics technician has to have access to the internet all the time today because many things that we are going to be analyzing we have to look for information on the internet. We will put TNY264PN in the Google search. This way we will have data about our component. We can go directly to images and we will have a drawing of how it is formed. Well, in the connections that have the letter S, this is source, there is where the negative will enter, where the electrons will enter. And at the gate D, that is the drain or output to the transformer. We grab our component. Look that we have a mark or guide that is always in electronic components of this format. Next to that point is the number 1. That is the bypass, and we will talk about it in a moment. The 2 and 3 are the same, they are the source. The 4 is the enable. 8 and 7 are different data. 1, 2, 3, 4, the 5 is the drain, 6 is not there, 7 and 8. Look that the 6 is not there. Well, what we have to test are 2 and 3 together with 5. So, let's do that test now to see how our component is. There we can see the number. Here we have 2 and 3, and there we have 5. Look, that 2 and 3 are in direct continuity. We had just seen that 2 and 3 were exactly the same. And between 2 and 3 and 5, 10 megohms, 11 megohms. This component is in good condition. 13 megohms, we are very well. As we could see, this is the way to test this component that is damaged quite a bit. If it is damaged, the best thing to do is to test all the components that surround it in the power supply, test them, and if everything is correct, replace it. If you cannot find the exact replacement, an adaptation can be made as we did on this board, but it is quite complex. You have to look at many more parameters, you have to cut tracks and make connections. That may be left for later, when you are more trained in electronics. But many times, or most of the time, we can replace it directly. In the case of this board, the original component was a Q100, a component I had never seen before. When it was damaged, we could not find a replacement anywhere. So we adapted a Viper 22A, which is universal and can be adapted with a little work. So we were able to make it work. But sometime later, in one of the classes, we discussed what had happened to me, and a student sent us the link where it was already on sale on AliExpress. Today, even the same one that we had not found can be obtained for replacement. These are details to consider with regard to switch mode power supplies. Of course, once this switch fails, you need to test the components around it. You need to take the time to test the diodes, which will be part of that return of electrons to create the alternating current. We need to test the resistors, which we still need to analyze so that you understand how they are measured. We need to test these opto-couplers that we still need to analyze, and the capacitors that are surrounding the switch. These capacitors surround the switch and are part of the enable to activate or excite the transformer coil. Once we have tested them, we can come up with a solution to the problem if it is failing. In the next video, we will see the circuit of a switch. Next, we will see a brief circuit, so that you can see it in terms of electronic circuits and know how one of these switching power supplies is formed. I will show you as an example a TNY264. Here we have a TNY264. As you can see, we have several components that form this area of the power supply. We have a negative and a positive. This comes from the capacitors. From here we activate the source drain switch, we flow down to the transformer, and on the other side the current with reduced voltage is created. It is rectified again because remember that here we have alternating current. We will now talk about how the direct current is created again, and also about this very important detail in switching power supplies, about the possibility they have to regulate the power that enters the transformer to be able to deliver only the power that is used in the output. Let's see it. Let's go back to our diagram. Now comes a question. If we had alternating current, we transformed it to direct current to create an alternating current of much higher frequency. Now we pass through this ferrite transformer with alternating current, but with less voltage. Now how do we transform this back to rectified current again? Because to make the board work we need direct current. Well, this is done through a single diode. You remember that in a conventional power supply, or here in this rectification, we had the sinusoidal voltage. We rectified by bringing this wave up, and there we had a full wave rectification. After that, after the transformer, we will not do a full wave rectification, but we will do a half wave rectification. So what does that mean? What we will do at this point is the following. A single diode is placed, which is the one you will be finding. I want to show it to you on the board. You will be finding it at this point. One moment, I will show it to you. And with this single diode, we make a rectification. How is this produced? Imagine that these two will represent alternating current, and these two will also represent alternating current, but of different voltage. These two will be creating 12 volts, and these two will be creating 5 volts. So, what happens? Let's see. The electrons will enter here and enter here, and enter here and enter here, because this is alternating current with two different voltages. When the electrons enter here, this diode allows them to exit, but when the electrons want to enter here, this diode prevents them from passing. So, the electrons pass, stop, pass, stop. And the same thing happens with this one that produces the 12 volts. The electrons enter, pass, stop, pass, stop. As a result, in these circuits that are the circuits that will be powered with 12 volts and with 5, the electrons will always circulate in one direction. As a result, instead of having an alternating voltage that recovers the entire wave, we do not recover the entire wave in this case. In this case, what we do is, we lose half of the wave directly due to the blocking that this diode produces. As a result, we are losing half a wave and we only have half recovered. The other is lost, but it doesn't matter. Why doesn't it matter to us? Because only by placing a capacitor at these points, only by placing a capacitor here, and another capacitor, between this and this, with only these two capacitors between this point and this, and between this and this, we can already keep the filtered current. We are not afraid that the voltage will drop so much since they are far from one crest to the other because the capacitor is charged. Remember that this happens 140,000 times per second. That is, a load from the capacitor to the next load is so fast that the capacitor does not discharge. So it doesn't matter that we don't recover this middle wave. We don't need it because this is so fast that we won't need it. This is a half-wave rectification, and this is the last filtering with capacitors, and there it ends. Having here already 5 volts, and here we have 12 volts. An important detail about these diodes, they are not normal diodes. Remember that they are like passkeys. They have to allow electrons to pass, cut, allow, and cut. Remember that this is very fast, 90,000, 140,000 times per second. That's why, instead of normal diodes, what you'll find at this point are Schottky diodes, superfast diodes. One moment, this part is complicated. They are not normal diodes. Their symbol is a little different from that of normal diodes. There they are. These are the diodes that are placed in that place. They are measured in the same way as diodes. We have to test with the multimeter from one side to the other, just like the previous diodes, but bearing in mind that they are different. They are superfast diodes. I'm going to show you all this on a board to see if we can follow up. Look, here we have been observing this board so far, and we were able to see we power the transformer, we go to the other side, and from this other side we now have a negative, which is usually the largest track, which is the one that is represented with G and D. And look that here we have one and the other positive. Here is a diode and here is another diode. This diode is in the 12-volt zone and this diode, evidently, in the 5-volt zone. Look, here we have a jumper, and it tells us that this is the 5-volt zone. In general, these boards have checkpoint. If we measure voltage between G and D and 5 volts, here we would have to have direct current, and between G and D and 12 we would have 12-volt direct current to know that the power supply works well. And we can also see the diodes on the other side. Here we observe two superfast and the capacitors, the last filter capacitors. Very well, here then we have the end of the switched power supply. I'll clean up the whiteboard a bit. This switched mode power supply is a bit more complex, so there are some things we still need to analyze. Let's clean up our whiteboard and leave it free so we can understand some parameters. Excellent. What is the circuit that opens and closes this gate? This circuit is composed of some more components. Sometimes, one of those components is an extra winding inside the same transformer that delivers 15 volts to power this switch. Sometimes, it directly takes the 310 volts through a resistor. You will find all of those components surrounding the transformer and the switch. But what regulates this? Because there is something that is regulated here, it is not only opening and closing. What is regulated here is what we know as PWM. Pulse width modulation. What does this mean? You will remember that we had a constant alternating current here, which is given by the voltage of 50 to 60 Hz. But in this case we pass to 0, and then we pass to an alternating voltage, but already created by the switch. This speed is already given by the switch. It is fixed, but what we will vary is the pulse width. What does this mean? To understand it, let's draw PWM now. Now we will draw pulses in this area. The idea is that each of these points is almost at the same distance. This means that each pulse is at the same distance and speed. But what I can do is vary the width. Let's see if I can draw it and it turns out well. We would get up to there. Each of these pulses starts exactly at the same distance of time from one another, but what I am varying is the width of the electrons entering on one side and the width of the electrons entering on the other. This can be done by a switched mode power supply, and what regulates is the width of the wave that goes up. The switched mode power supply knows that on the other side of a half-wave rectification and the wave below is lost, so if more power is needed it makes the top wave wider, and if less power is needed it makes the top wave narrower. So, through a notice that the switched mode power supply has at this point, through an element that is warning or communicating from this side to this, it is informing the switch if more or less electricity is being consumed. Then it tells him how wide he has to pulse, the speed of it. But what is going to vary is the pulse width, the width of the wave that goes up, that is the one that is used. If it is being used less at that moment, it delivers less. If it is used more, it delivers more, but it delivers what is used so that through the transformer, it does not get excited and the voltage is lost afterwards. This is something that a conventional power supply cannot do. There is no communication. We cannot vary the pulse width because the transformer works directly with 220 volts, 50 Hz, or 60. And this is the advantage of a switched mode power supply. Of course, this implies that there are many more components that can break. The PWM circuit is a bit of a complex circuit, but this is what we find ourselves with. We have to learn it and we have to understand it. So, how does this communication take place? That is the question that I will explain. This happens through an optocoupler, and we will talk about it in the next video. In this video, we will talk about optocouplers. The component that you are seeing here, which I have in my hand, are quite universal optocouplers, so to speak. They can be used for almost anything. They are PC817S. How is it formed inside? It is very easy to understand. We are going to diagram and draw it right now. This component, as its name itself says, is an optical coupler. What does it mean? That it produces an optical coupling, that is, there is light inside it. This is our component. When we energize this diode, which this diode is an LED, I don't know if you knew, but LEDs, LED lights, in reality are diodes, only that in their internal excitation, instead of only blocking the passage of electrons, which they do, they also produce light there. When we excite this diode, we inject a voltage of approximately 1.5 to 3 volts. At this moment, this LED turns on, emits light, and from this side where we have a photosensitive circuit, it then activates and lets the electrons pass. I turn on this light, and from this side it lets the electrons pass. Why do we have this component so complex, so to speak, to carry out this notice from one side to the other? Think about the following. In this area of the board, we are already almost in contact with the control area with the microprocessor, delicate areas, and on this side of the board we are talking about that we have high voltages. These voltages, which are affected by the electric company if it has any problems, can damage a microprocessor. So, to warn from one side to the other how much is being consumed and how much the pulse width has to vary, an optocoupler is used precisely. This component allows that by means of a light it is informed from one side to the other, not being able to affect electrically what happens, neither from one side nor from the other. Precisely, this component has an internal barrier, that is, it has an internal dielectric, an insulation against electricity, a galvanic insulation of 5,000 volts. What does it mean? If for some reason 5,000 volts are injected from this side, nothing happens absolutely, and from this side the same, they communicate only through a light. This component is very interesting because we will find it several times in inverter technology. At least they will have 6 on all the boards. Excuse me, you will find 5, or rather 6 in some, depending on the type of fan you have. We will see it in practice and learn how to test this component. We will zoom in and illuminate. On the side where it has the point, we always have the LED that illuminates, And where the point is, we have the positive side of the LED, the positive side. Let's test with the multimeter to see if it is in good condition or not. We will place the multimeter in LED position and measure. Open line, perfect. And if we invert, we will have the voltage drop of the LED. The voltage drop of the LED is 1.05 volts. LED diodes have a voltage drop of a little more than 1 volt, generally, so this LED is perfect. On the other side, we would have open line, because now the LED is off. There is no continuity here. This is perfect. What would happen if we turn on that LED? We will test it with the necessary elements. We will use some special test leads. These test leads that we will be recommending can be purchased, and in the class that we talk about tools, I will explain a little more. There we have the part of the optocoupler that has to be bridged when the LED is turned on. We will connect this to the multimeter now. There we are. Now we are going to turn on that LED. How are we going to turn it on? We will do it with a small button cell. In this case, I have the CR2032 model. Remember that these batteries on the whiter side have their symbol or plus sign well marked. This is the positive. Notice that if we put in continuity, what will appear on the screen? There we have 20 ohms, and there it falls to 0. When the internal LED is turned on, continuity is produced on the other side. It is not a 0 to 0 continuity because in reality it is a photoreceiving circuit. It is not a direct bridge or a contact. That is why it always has some resistance, but it is very low, only 20 ohms. In this case, this optocoupler is working perfectly. If you want to see how it is made inside, I will show you one disassembled. This is how they are made inside. On one side it has the LED, and on the other side the photoreceiving circuit. This is how they communicate internally and can be turned on as we are seeing now. This is the dielectric material, the insulating material. If we energize it, we will see how the light turns on. But in this case it will be difficult because with the camera that we are making these recordings, it is a slightly more advanced camera and does not see infrared lights. But with any cell phone, perhaps Samsung or Xiaomi brand, you could see this light, just like you see the light of a remote control, just like that, they are infrared lights. With optocouplers, we will be talking about a circuit that is zero crossing detection, a very important circuit in electronic boards. To help you understand what zero crossing detection is for example, in air conditioning it serves to regulate the speed of the internal fan. When you have that normal AC fan with a blue capacitor on the board or a gray one, this zero crossing detection through an optocoupler serves to identify and make it change its speeds. But when we talk about forcers fans, we will be detailing its operation a little more. For now, what I will explain is zero crossing detection, which is a part of the board that I mentioned to you when we were tracking tracks. It works as follows. Again, we have to redraw our famous rectifier. Alternating current. Direct current. And here we have the capacitor. But remember that at this point we will have a fifth diode placed, as it was in the sample circuit. Do you remember? Here we have a fifth diode, as we had in this sample circuit. It is placed as follows. This will be negative and this will be positive. And here is where you will find it. Of course, there are 4 more diodes. At this point, taking as a comparison the negative the electron input, between these 2 points we will have the unfiltered rectification, as we could see in the class that we did the measurement with the oscilloscope. What does this point allow us to do? Let's observe. I will mark with a different color so we can notice it. We will go out from here, jump this, and we will go to a lead. We will jump from this point to here. We pass here and then we go back to the lead. And on this side, we will have a phototransistor. What is this? Precisely the optocoupler. Remember that on this side we are having this. What does it mean? That every time electrons are sent, they will pass through the lead and the lead will turn on. And 100 times per second or 120 depending on its frequency, that lead will turn off. That is, during all this time this lead remains on. By here the electrons pass. When this lead turns off, the electrons here stop passing. And what is on the other side? On the other side we will find the following. On the one hand we will go to the negative or G and D. And on the other hand we will go directly to the microprocessor, the integrated circuit. And here we go to 5 volts that are already generated by the circuit for everything we have already learned. These 5 volts will come to the microprocessor as long as they cannot go to the negative and a short circuit is produced. In reality, the short circuit does not occur because there is a resistance that may be 1 kilo ohms. We will talk about resistances later. Whenever this is on, the 5 volts will be diverted to the negative. But whenever this lead turns off, this is cut off and these 5 volts enter the microprocessor. It turns off. 5 enter. It turns on. The 5 volts are diverted. As a result of this, exactly at the same time, the microprocessor will receive a pulse of 5 volts, exactly at the same time, that is, here. The microprocessor now knows when the alternating current is crossing 0 of 220, 50 Hz or 110, 60 Hz, whatever, but they know what times cross 0 thanks to this detection. And why do we put an optocoupler? The idea is that what happens here does not damage the delicate circuit of the microprocessor, so that is why an optocoupler is also used, to be able to make a very powerful electrical insulation for any problem that may be in the line. This is how it works. One more detail that we are missing is that at this point, from the positive, we will have a large resistance, because precisely if we are not injecting 300 volts to the lead, then we will have a large resistance that can be of 150 kilo ohms, for example. We will see all this on the board now to be able to identify this circuit. If this does not work, for example, it may be that the AC fan stops working. I will show you this same thing on the board. Let's observe and follow up here. From this point, where we have this sample, notice that from here we will go to here, with a high value resistance. In this case it is this. And then we go directly to an optocoupler. This coupler, looked at on this side, is the lead. We can see it down here. Generally on the motherboard where this point is indicated, it indicates the number 1 of the optocoupler, the positive of the lead. This other one that is to inform the switched mode power supply about how much the pulse width has to vary, the lead is placed on the delicate side. In this case, the lead is placed on the side where the zero crossing is generated. That is, when we have to inform the consumption from the microprocessor area, the consumption is informed from the delicate area from where the microprocessor is towards this side. And when we have to warn of the zero crossing from the side of the alternating voltage towards the microprocessor, the lead is placed precisely upside down. We have 2 optocouplers, but in the opposite position. And if we wanted to measure it here, inside the board, we can also do it. We can test the LEDs at these points to see if they are in good condition. One detail that we are going to explain now is about capacitors. When we have to replace them, there are 2 important data that are exactly the ones that are printed on the capacitor, and we have to take into account when buying a replacement. These values, we have to respect different parameters. For example, let's explain about these ones that we have here. The manufacturer usually places capacitors that support a voltage 25% higher than the one that will normally work. What does this mean? You already know that in this area we have 220 volts in alternating current, but in reality the peak voltage to which it reaches is 310 volts. 25% more, we will multiply it by 1.25, and we are talking about 387 volts. The next value of capacitors, next standard value, is the value that the manufacturer will be placing. In this case, it can be seen that they have obtained 450 volts, so they have put 450 volt capacitors. In terms of capacity, when we are in areas of source that comes after rectification, which will fulfill their filtering function, the capacity must be equal or greater than the one we are seeing on the original board, because the more capacity it has, the better, the more it will filter. But there is a point at which physically the capacitor will not fit. In this case we have 2 of 10 microfarads. If I wanted to put twice the capacity of these capacitors by physical space, they will not fit me, but they will work well anyway. So, when we are in the filtering stage, we will place capacitors with voltage equal or higher than the one it originally has, and with respect to the capacity it must be equal or higher. Now, when we are in other parts of the board, such as for example in more delicate areas, including the switched mode power supply, from the capacitor that feeds the switch, in all other cases we already have to respect the values of the capacitor in terms of capacity, because if they absorb too much capacity it will not have remaining electrons to be able to deliver to the appliance they have to feed. For example, in this case, in the case of this capacitor, which feeds the switch, we have to respect its capacity very well. If we put it of greater capacity, the source will not work. Here we have a 50 volt 4.7 microfarad capacitor. Except in the filtering area, in the rest of the areas we have to respect the capacitor values to make the replacements. We always have to take into account those parameters. So, understanding this, we are also knowing the following. I will show you an external board so that you can see how these capacitors are. Look at this. These are 420 volt capacitors, but they are 100 microfarads. This filtering of the external board, like this rectification, which is produced with the rectifier, then a filtering is done to feed even the compressor and the fans. The capacitors are of more capacity to maintain the filtering of the wave, but they are bigger. Clearly it can be seen. This would work on this board, but physically it will not fit. Now, if I put this one here of less capacity, it will not work for me because it will not keep the wave. it will drop to 0 and it will not be able to feed the compressor properly. These data have to be taken into account when replacing the capacitors. These are the parameters that we will be following to make the correct replacements. We are going to talk now about a part of the circuit that you will find in an inverter board, and this part is why many say that it is essential that we have a ground wire in inverter air conditioners. What do we mean by ground? The third wire of the electrical installation that has a connection to a spike. And why do many say that it is essential that inverter air conditioners have a ground wire? This is one of those reasons. To begin with, I will tell you that an inverter air conditioner can operate without any problem even if it does not have a ground wire. You can record that in your mind and do not forget it. An inverter unit will operate without any problem even if it does not have a ground wire, just like any other appliance. The most important function of the ground wire is the protection of people. In another of the modules of this course, it is clearly explained how the ground wire works together with a circuit breaker to never allow a person to be electrocuted with an appliance. But inverter boards also have an additional feature. Inverter electronic boards have a connection to themselves from the ground wire, but this is no longer for the protection of people. Although the equipment will still operate the same even if there is no ground wire, but I will explain why this is and also other components that are surrounding it. Well, I will make a diagram and then follow up on the tracks of these external electronic boards. This ground wire can also be found in the interior boards mounted on the board. We had said that at the entrance of the electricity, we had on one side a fuse and a varistor. Here's where the ground wire comes into play. In inverter units, we are going to give ourselves a little more space so we can draw it well. In inverter units, what we will have now is a slightly more complex circuit, always alternating current, and then we go to all the components that you already know, double pie filter, then comes the rectifier, etc. But in inverter units, we no longer have this, but something a bit more sophisticated and of better quality that does not allow the voltage to enter into a short circuit and the fuse blows. But it tries to divert this power whenever there is high voltage, excess of high voltage. It tries to divert it to the ground wire so that the circuit breaker trips. So what you will find is, we will not have this varistor here joining the two, but a varistor here. And here another varistor. Here we are going to go to a fuse. And here is where we are going to go to the ground wire. Here the circuit continues and everything else, but what is the purpose of this? If we have normal voltage positive and negative, they continue their path and feed the equipment. But if we have excess voltage, it will be diverted through one of the two varistors. We will jump this fuse, we will cross it, and we will go through the ground wire and the circuit breaker will trip. The circuit breaker will do is to trip and de-energize the equipment, thanks to this circuit. This protects it against high voltage. The system is good, well done. This that you are seeing here is a... I will put it in a different color and write it here. It is a vacuum device that does not allow any high voltage, or better said, does not allow any discharge from any other appliance to enter the inverter board. If another appliance is short-circuited, or better said, is grounded, that to enter through the equipment to the board, and so that this does not happen here, there is a vacuum device. This device allows the passage of electrons to that side. Whenever from this side it detects a very high voltage, a kind of lightning or spark is produced inside and it is diverted. When there is very high voltage in one of the two, line and neutral, it diverts through the varistors and goes through the vacuum device to the ground wire, and the circuit breaker trips. Well, this vacuum device and this circuit we are seeing here, of course the fuse is always there to act, but in reality the idea is that the fuse does not act and that this works and the equipment is de-energized in that voltage surge. The system is good, well thought out. It is not definitive and absolute, but it is a good system. Now we will see it on the electronic board directly. Look that here we have an inverter board, and here we are seeing the varistors. Span class equals QL cursor, and we are seeing here the vacuum device / span. In this video, we will follow the same circuits that we just explained on an inverter electronic board. So, observe that here we have the fuse. I'll zoom in so we can see it. Here we have the fuse, the two varistors. Here we have the vacuum device that I just mentioned. Here is the output to the physical ground, and this is the protective circuit. We will see it from the other side and follow the tracks. Here we have the varistors, the ground channel, and the vacuum device at this point. At this point we have the vacuum device, and here we have the varistors. This is the reason why it is said that we must have ground yes or yes in an inverter equipment. So, is it true that it is necessary? Yes, it is necessary because it protects against high voltage. It is not mandatory, the equipment will work the same. Keep this in mind to explain to customers. Ground has always been for protection of people and, in the case of inverters, it also protects electronic boards. This would be the explanation. Let's see this on an LG board. On this LG board, the reality is that it does not have a vacuum device. The LG board is a bit more rustic. It does not have as good quality as other boards, but LG has a good reputation. It does not need to do things so well already by fame it can sell. We have the varistors, and here is where ground is connected on channel 1, and here we have the fuse. Remember this important detail to be able to explain to customers about grounding. Perfect. Having explained this topic well, let's move on to do follow-ups on the outer plates so that you can now identify or understand how electricity travels through electronic plates. That's what we're going to try to do, gradually understanding all the circuits. You are seeing an inverter electronic plate here. Now I'll zoom in a bit. Starting on this side, I'd better turn it over because the words are written backwards. At this point here we have the line and the neutral. Here we have communication or signal. We'll talk more about that later. The line will go through a fuse and continue its journey, line and neutral. Here we have the varistors, here the ground discharge. The ground discharge also has a small connection with some capacitors that also do stabilization or final filtering. You can also see some small capacitors of this format on this side. We reach this point, cross from one side to the other the toroidal coils of the filter. We have some final capacitors again. Here we cross a small contact relay. Here we have a filtering capacitor for low capacity, capacitors, and finally with the two in the middle we reach the rectifier input, the alternating current input of the rectifier, and at both ends we already come out with rectified voltage. If we ignore some things that we have here in the middle, which I will explain later, we will then reach the filtering capacitors. Rectification, and here we have filtering done with capacitors, 8 of 100, they are 800 microfarads that are filtering this area. This that I just skipped is what we are going to talk about next, which is the power factor correction circuit, or PFC. We will talk about that later. We will do the same on the LG plate. I'm going to take it out of here. Well, here we have neutral and line. We cross a fuse. Yes, this is the fuse. Here we go towards the capacitors and the ground derivation we have here in this area, then to a winding and another winding. Look how these LG low-pass filter coils are a little smaller. Here we have a filtering capacitor too. It doesn't have two but only one. It's not double pi format. We continue our journey crossing a small fuse more, and what we do here is skip a component that is connected in these two cables, which is part of the PFC circuit that we are going to talk about next. This component produces a union of the two cables simply, but if we continue along the route we find alternating voltage or alternating voltage input of the rectifier. Here we can see the rectifier. And if we look at the rectified output, here we have negative that follows this route and goes towards here. And here we have the positive that comes towards here and reaches this end, and what do we have here? At this point we have the capacitor. In this case, this LG has only one capacitor of 680 microfarads, and here is where voltage is filtered. So here you have source zone of outdoor unit, but their source does not end. Remember that now we must go to switched source. These plates have switched sources. It is true, this filtering, this voltage of 310, if you have 220, it will go to the motor. We will explain that later. We still have to go through more components, but this will also go to the switched source. And if you observe, here we have the positive and here we have the negative. Look at the negative. We reach this side of this component and skip to the other side. This component of 7, remember that it was the switch. There we have the switch, and then we come to the ferrite transformer, to the coil of the ferrite transformer, and the positive. These arrows are only jumpers, that's why there is the letter J. It goes straight to it, to the transformer. I'm going to show you these jumpers on the other side. There you have it. Very well, we cross the transformer, and on the other side of the transformer, if we follow tracks, notice that we are going to find a diode here. There, I show it to you. Notice that we are seeing all this from above. What do I mean? That without disassembling almost anything from the air conditioner, all this is exposed to us, and you will be able to make all these visualizations. Here we have evidently an output from the transformer. It crosses a diode that must be half-wave rectification. We follow tracks, continue, and here we have this checkpoint of 15 volts. Between this point 15 volts and this one that says GND, I must have 15 volts. So this transformer has an output of 15 on one side. If we go towards another side, let's go towards here. Evidently this is negative. It is negative because it says GND, it is wider. Notice that this is all united towards here. It is united to all this is negative, and I have to find positive of 5 volts. If we go towards this side, we cross a component that is half-wave rectification diode. We come towards here, and we are entering this component of 3. Evidently this must be a 7805 because on this side that I know is output, notice that we are going exactly towards this point, which is a checkpoint of 5 volts. Evidently about 12 or 15 will enter here as well and regulates for 5. I'm going to show it to you on the other side, and we're going to identify these two half-wave rectification diodes. So here we have everything we just mentioned. Half-wave rectifiers, here we have filtering capacitors, and here we have 7805. There it is clearly visible. Well, as soon as I disassemble a unit, I don't have access to this part of the plate, but if I have access to the other side, and little by little you will become familiar with all this and will be able to do your tests from here. In fact, we are going to do some measurements in the following classes, and the idea is that you can also do them. My idea is always the same, that you can diagnose an inverter circuit without disassembling all equipment or disassembling as little as possible. With this we are finishing with what is source zone. Shall we go with the other plate? This electronic plate, after capacitors, I also have to go towards switcher. This electronic plate is more complex because it has tracks on both sides, but still I will have many test points on this side. Notice that here there are a lot of checkpoint of 0.6 volts, of 1.8 checkpoint of 15 volts. Here I have another checkpoint of 12. What I don't see here is switcher. Here it's not visible because it's mounted on other side like a device that mounts without crossing plate. Transformer does crossplate and we'll see it on other side. In this case, in this plate, maybe it's necessary to disassemble a little more to make these measurements. But here we have the capacitors, the switch, the components that surround the switched power supply, and some electrical resistance. Those are diodes that do not cross. They are mounted superficially SMD. Here we have the opto-coupler. Here we have the transformer, and on the other side half-wave rectifier circuit that has the mounted diode and the last capacitors. Here we are reaching the end of the source of the outdoor unit. Any problem in the source area, the electronic plate directly does not work because this is what prepares the voltage to power the microprocessor that commands everything else, that warns us of error codes, etc. Everything we've been seeing, the rectifier, capacitors, and switched source are part of source that powers control zone. In the previous video, we mentioned that in the circuit of the source we have some additional components that are connected with these two cables. The additional component that is inside the circuit of the source, but we can say that it is not the same as the circuit of the source, but rather it is in the middle of the control zone. This is the PFC circuit. The PFC circuit is composed visually. You will be able to identify it quickly in inverter equipment because what you will see is a reactor. This component is not a transformer, What it does is let electrons pass through it and come out, nothing more. What is its function? What problems does it bring in inverter? Well, if this component is in bad condition, the problem is not that the source stops working, but that it will mark some kind of error, such as overcurrent error of the equipment itself. You will always find this component near the motor compressor. I will show you an image so you can see where it is. You will find it here, near the motor compressor. If you don't see it, it is very likely that it is on the electronic board. It can also be mounted on the electronic board. Here we have it near the motor compressor, here we have the fan, and here we have it mounted on the board. The question now is, where is it placed? What problems does it present? How is it measured? What is its purpose? That's what I want you to understand most, what this component is for. It's key to being able to identify problems and understand how things work. I'll talk about that now. Perhaps you have heard about power factor. For example, when in a factory we have many motors, these are the windings of the motors that I want to draw here. What is done is to place a capacitor bank to compensate for power factor. Why? Because coils and capacitors alter electron flow, and this has something to do with low-pass filter circuit or double-pie filter circuit that we had been analyzing in previous modules. It has a lot to do because coils and capacitors function exactly opposite. You will remember that this represented, if we compare it with water, like a cistern, and this could be compared to a centrifugal water pressure pump. Well, what problems can these components cause in electricity? Surely you will remember that sinusoidal wave or electricity provided by electric company is a sinusoidal wave. So if we place many capacitors, what happens is that voltage lags behind. What does that mean? With respect to normal passing voltage, voltage delivered by electric company, due to capacitor charging, I am actually out of time and am over here. Let's see if I can draw it. I'll be around here approximately. I'm out of time. Now if we place motors or coils, I make voltage advance. So thanks to these motors or coils, I'm out of time again, but in other direction advanced. Either voltage advances or load lags behind can also be called. It can be mentioned both ways. Same capacitor lags behind voltage or advances load. It can be said both ways. My way of explaining it is that capacitor lags behind voltage and coils advance it. What happens with this? What happens when we place motors and capacitors? If I only place motors, imagine that we only place motors. Let's erase red representing capacitors. At some point in time, let's assume a moment in time for example here. Imagine what happens when the line voltage is pushing electrons to one side, to one cable, because these are altering the time. At that moment, these will be pushing electrons to the opposite side. So there are certain moments in time, I repeat, there are certain moments in time, that is from here to here, where the coils push to one side and electricity to the other. Here we are fine because we are on the same side. But here again, if it hurts us again. You see that it is towards one side and towards another, always from this line I mean, which is voltage 0. There are moments then in time when the voltage is pushing to one side and the coils to the other. What do I do to compensate for this? What is done is to place capacitors. So what I do is delay the voltage a bit that was advanced by the coils, and then what I do is equalize this line and this line, I take it to that side, and we tend to equalize it exactly. There it went too far. So what do? We will want to equalize it. I'll see if I can do it this way. It doesn't let me, it doesn't matter. What we do is move back and equalize again. Now this that we are seeing here, this problem of push and our coils pushing to the other side, is a problem of power factor. What does this mean? In reality, I don't pay for it on my electricity bill. This is a waste or an extra force that I make the company that provides electricity do. What I do then is that my power factor is be down because of all the motors I am placing. What does power factor mean? For example, if they deliver 1000 watts of power, which are what I am consuming, I am taking advantage of little, I am taking advantage of 0.5. The power factor is always between 0 and 1. I am taking advantage of 0.5. That means that I am only taking advantage of 500 watts of power provided by the electric company for 1000 they are sending me. This is not paid on the electricity bill, but it hurts the company that provides electricity. That's why when in a factory there are many coils and no capacitors have been placed, in this case a fine is made to those factories. Well, if I place capacitors, I correct this power factor, and what I do is raise it. Then maybe I raise it, and from 500 watts they deliver me, I will be able to take advantage of 0.7, the power factor. Factor is always a number within a multiplication. It says factor. The power factor will be 0.7, so I reach 700 better thanks to capacitors. But placing capacitors, unless it's a computerized capacitor bank, aren't safe because it really depends a lot on how many machines are turned on at that moment. If I place capacitors taking into account all motors turned on, when some motors aren't turned on, I'll run the line to the other side. In the end, again, I'll alter power factor. So placing capacitors isn't safest, but always help. If I have many capacitors in one place, my power factor is also altered, but what I have to do to compensate is to place coils. And that's exactly what happens in inverter, exactly the opposite of what happens in a factory. In inverter technology, as I have to filter voltages for high consumption, I have many capacitors that delay the voltage. So what is used to fix the phase shift in power factor? Well, what I place are reactors. The manufacturer places reactors that correct the power factor. That's why the reactor, although many call it coil, transformer, is actually a reactor. It is part of the PFC circuit correction of power factor. The capacitors are capacitive reactive loads, and coils are inductive reactive loads. If I have inductive loads, I have to place capacitive ones. If I have capacitive ones, I have to place inductive ones to correct power factor, which is this number. I have to raise it. The ideal is that it be 1. If they deliver 1000 watts and the power factor is 1, if I correct it exactly, I am taking advantage of all the watts they deliver me. It's hard to get to 1, but you can. Well, all these components, such as coils and capacitors, used as PFC, are called passive PFC. In all these parts of the course there are many new names, but you have the videos to review as many times as you want. Do it looking at boards, observing, review it well, because this is important to be able to make good diagnoses in inverter. If you don't understand how each component of the circuit works, it will get very complicated for you, this new thing, but little by little you will understand. Why is it called passive PFC? Because it is precisely passive. If I place a coil to compensate for capacitor work, that coil is a fixed correction, not a correction that adjusts all the time. So with this passive PFC, we will try to correct this power factor, and I will be able to reach 0.7 at most. So to improve this even more, what an inverter circuit will do, at least the most sophisticated ones, and for example all in Europe, will have an active PFC. There will be an electronic circuit that takes care of making this correction, helping the reactor, so to speak. Actually the other way around. The reactor helps a little the active circuit so that it doesn't force so much. Now we will see what we mean by this. We will see a diagram and also see it on the same electronic board in the next video. In this video, we will see a small diagram, very simple, and analyze how a PFC circuit is formed, which is always inside the source. Here we have it. It is quite drawn due to the previous training, but we are going to clean our board and be able to guide ourselves with this diagram. This is a diagram of a basic circuit with passive and active PFC, typical in an inverter system. There are parts that you know very well, such as, you know, the rectifier bridge, and you also know the capacitors very well. These are the rectifier bridges, and this represents the large capacitors in an inverse circuit. What will you find here? Here you are seeing that we have this coil. This is exactly the reactor. Notice that it is placed at the output of the positive of the direct current, which is then filtered with the capacitor. The negative goes straight. In the positive channel you will also find a fifth diode. Its function is also to divide what happens here from what happens here, as it happened to detect zero crossing, but now for something different. You will have this division of the fifth diode so that what happens on this side, the voltage or wave that is on this side, be different from this side, and a computerized circuit that is this one that is here, can control and finish adjusting the power factor. Capacitors delay voltage, coils advance it, so it starts to adjust. But since an inverter system works faster or slower depending on the need, we will be using an active and computerized PFC circuit to finish adjusting the power factor and reach a power factor of 98. So if they deliver 1000 watts to me, if I were using 1000 watts, I would take advantage of 980 thanks to active PFC. How does it do it? Notice that this active PFC, that this component is inside the microprocessor, has a sample of this and a sample of this. And in turn it has a sample of this and a sample of this. Obviously it has resistances because it is high voltage, so it has large resistances to be able to detect a lower value but still see the wave. It has a fifth diode to divide from one side and another so it can measure zones separately, and what it also has is a MOSFET, perhaps the main component of an active PFC. which is a transistor that can transport high amperage. It's like a water valve in electricity, just like a water valve in water lets electrons pass through. So what's it going to do? He's going to know if electrons are going that way or that way, and he also knows if they're going there or there because of the capacitor effect. He also knows what happens on the line. He knows if electrons go one way or another. If at any moment he detects that electrons are coming here and from this side they are coming here, what he's going to do is drive through the MOSFET so they go the other way. So if at any moment electrons collide, he diverts them and allows them to go towards the corresponding side in the incoming voltage. Thanks to that, there's never that electron collision. There's never that, as I told you about being in different times and one pushing one way and another pushing another way. It doesn't happen, or almost doesn't happen. That's how an active PFC circuit works. It's very efficient. It's a great system, but it's a delicate system because this MOSFET transistor, notice that this MOSFET transistor is constantly short-circuiting. That makes this component heat up quite a bit. This diode is a diode that is transporting many electrons because after here comes the switched source and motor compressor. It supports a lot of amperage. Everything heats up a lot and tends to burn out. That's why the circuit is good, but it gets damaged quite often, so we have to learn to check them. Now we will see all this on the electronic board, making the corresponding measurements. We will see it in the next video. As I said, we will see how to control a reactor, how to measure it, and how to know if it is in good condition. With regard to reactors, you have seen in the circuit that the only thing they do or have to do is to let the electrons pass, only producing a small modification in the time in which they will travel. Therefore, a reactor has to let the electrons pass almost freely. It does not have to have resistance to the passage of the same. If it starts to have resistance, we will have problems in an inverter electronic circuit, and those are the cases in which, for example, we have overcurrent errors. So if you have overcurrent error or even low voltage, check the reactor. If you have a low voltage error, I refer to although the voltage is in good condition, we place the multimeter in resistance and the resistance has to be almost 0.6. Notice that the multimeter only has 0.3, then 0.5, 0.4, almost 0 in its resistance, so it has to be. And obviously towards its housing it has to be open, completely open. There must be no continuity. Any defect in this causes us errors in the systems, errors that the board does not know how to say. What do I mean? These are the type of errors that the board will not say reactor error. You have to understand it, because you understand the operation. And of course, any technician looks here and finds a resistance perhaps of 2 or 3 ohms and says, well, this is fine, it has continuity, but 2 ohms is too much, there has to be less. And there is the problem. If this becomes faulty, it can be due to several reasons. For example, it got wet and went into a short circuit. Or for example, another error. Here there are solders between copper and metal. This solder can be carbonized, so in this case you have to clean it well. When we talk about welding, you will learn how to do these cleanings and how to solder again and how to use this year of good quality to put these parts back together. This is in sight in this model, but in some models it is hidden and I will show it to you. In this model those connections are hidden. Here you have to disassemble that paper and solder again those unions between copper and iron. In case you have to replace it, The value that you have to see and take into account are the millihenry and the ampere. These are the values to take into account. The millihenry have to be as similar as possible, and the amperage has to be equal or higher. The larger the equipment, the thicker the copper filaments will be. Well, this in the case of the reactor, which is the simplest component to check, but we also have the fifth diode and we also have the transformer. So now, in the next video, we will see how to do these measurements. As I said before, we will see how measurements are made on the diode and the MOSFET transistor. First, let's see where they are placed. Remember that we will find the reactor on the positive side. Also, the fifth diode and the MOSFET transistor will be joining the positive and negative. It will be in parallel. We will do some follow-ups. Over here we have alternating current, direct current output. The positive will reach L2. Whenever there is L, there is a coil or an inductance. We go through to L1. These are these two cables. This is where the reactor is placed. Continuing our tour, notice that here we have the positive and here we have the negative. This indicates to us on the board that this is the negative pole. And here is where we have the report that will give or the activation, which is given through the microprocessor to be able to activate and produce that bypass short circuit. Moving on, we don't see the tracks because they are on the other side. We have here the positive and here we come out of the other side of the diode. This is the fifth diode, transistor and fifth diode. Here we can see them. It's a little dark. I'm going to put on the light. Here we have the diode and here we have the transistor. I'm going to zoom in a bit to see it better. Rectifier, transistor and fifth diode. This IPM component we haven't analyzed yet. Now, how are we going to make measurements on these components? We must remember that here we go towards the positive of the capacitors, around we have the negative, and in the middle are the positives. From the diode we go to the positive. Here we have the active PFC circuit. How are we going to measure these components? We will even be able to measure how it is detecting at this checkpoint the sinusoidal wave. For all these measurements, please pay attention to what I will be showing you. We will see it from here. This is how you measure a transistor. You place a multimeter in resistance and measure between positive and negative, and a transistor's resistance must be in megohms, as we can see here several megohms, 5 or more. It is measured between positive and negative of MOSFET transistor or where short circuit occurs. A resistance similar to what we found in switched source switch. We continue advancing. Make that measurement and I'll let you continue with video. To control a diode is simple because you already know how a diode works. It lets electrons pass one way but not another. This way you control PFC diode. For one side lets pass and for other no. Voltage drop is lower because it is a diode that handles more amperage. So internal components, so to speak, are larger and let electrons pass a little more, so voltage drop is higher than 1N4007. You remember first classes, so its operation is controlled. If a defective dissipator is removed, with these screws and see what code component has. They are super fast high amperage diodes, and other one is high amperage MOSFET transistor, so you have to get exactly same good thing they get. As you could see, this is how it's controlled. Look with oscilloscope, how it oscillates at that checkpoint, or how we can see that circuit working with motor off. Can see it oscillating approximately at 100 Hz, which is number of times it crosses zero. Advancing the video, we will see when the motor starts to work, that's when it activates and starts to indicate at what moments to create that short circuit. There we can see that the PFC circuit is working well. This is also handled by PWM. It is always handled by pulse width. So this is what you will detect if you do a checkpoint on that third terminal of the MOSFET. There you will see a frequency of 100, and when the motor turns on, which is when that PFC has to be activated, there is when you will see a square PWM wave, which creates that short circuit to adjust the power factor. This is how it works. It is interesting to understand how it works. Why? It is difficult to detect when this circuit fails. It is difficult to say, well, the problem is the PFC. One blames anything, the voltage, the motor, the IPM, which is what most people know, but this PFC circuit is there and also tends to fail. Here we can see, on a carrier board with the reactor mounted on the board, you are seeing the rectifier. The transistor is Q, this one. And the one with the letter D is the diode. Detect that there is always some low-value resistance that works as a fuse. These are low-value resistances that let electrons pass through. There is always some resistance like this placed in these areas as a fuse, so keep that in mind. Excellent, so far we have advanced quite a bit. One last detail, on certain electronic boards such as LG, there is no active PFC. As there is no active PFC, they place a reactor to correct power factor a bit and place it here on alternating current at input. Keep in mind that detail if you don't see active PFC. For example, on this LG board I'm going to show you now. If you don't see the active PFC, it's not there because there is only a rectifier and IPM. In this case, they place it on alternating current. There's where they place reactor. Here's where reactor is plugged in. It's placed before. Anyway, there won't be any active PFC that has to control anything. Keep in mind that detail. They place an approximate and let whatever happens happen. Different from other board we were measuring that places reactor, checks how it works, and with active finishes adjusting, but parameters are same. Always have to check they're in good condition, and if those welds have been damaged, redo them. In case reactor is mounted on board, it's very difficult for it to fail. It's very rare, like in case of carrier or Mirage. Span class equals QL cursor. So far we've been looking at reactor, talked about whole PFC circuit, and will continue advancing with stages of electronic board / span. Excellent. Advancing with this training, we have reached a point where we need to see how the path of electrons continues inside an inverter system. Let's pay attention to this detail. At this point, we had a rectification that is not being transformed, as you already know very well, from alternating current to direct current. Do you remember? This was an important transition in any board, and it is called rectification. Because this direct current is going to be consumed a lot, there is a PFC circuit or power factor rectifier, and, of course, to create a filtered DC, we will also have a capacitor. So here we already have a clean DC voltage, ready to be used again. Where are we going now? Well, now we have to keep moving on to the next components. On the one hand, we are going to go to the switched mode power supply, which I have already explained in the previous lessons how it works, what it is for, and how it finishes preparing a lower and regulated voltage so that the microprocessor works. So what we find is the switched mode power supply on the one hand. I'm going to draw it for you. And on the other hand, we find another component. Let's try to make a diagram. With this color better. Let's do rectification. Transform AC to DC. Very good. Afterwards, we will go through a PFC circuit, power factor rectifier. Afterwards, we are going to go on one side towards the switched mode power supply. And on the other side, we are going to go towards the IPM, and that is what we want to start talking about from now on. What is the IPM? Well, the switched mode power supply is the one that will give voltage to all the low voltage components and even the integrated circuit. And the IPM is the one that will prepare the voltage or the one that will finish giving the voltage or electron configuration for the compressor. So, this would be a diagram in broad strokes. The current is rectified, it goes through a PFC, and from there we go to a switched mode power supply, which feeds an integrated circuit. This is the team's computer, the brain. Now, the integrated circuit works together with the IPM to tell it at what speed the compressor has to turn. But look at this detail, how important this is, because previously in a conventional team to feed the compressor we did not go through all this. Before in conventional teams, to feed a compressor, let's see if we get it, we had alternating current, that is the one that comes from home. Now an inverter, the alternating current is not mentioned because it is not useful to us for anything. As soon as it enters you have to rectify it, but previously the alternating current was used. In fact, the alternating current directly went to feed the compressor. And we had on the other hand, rectification. We had the switched mode power supply and we had the integrated circuit. Integrated circuit, I refer to the processor. I'm going to show you, I refer to the microprocessor, the brain that commands everything. Now look how we had an integrated circuit previously, the only thing that is the circuit and will be, in the case of the compressor, was to enable or disable the passage of alternating current to the compressor. Well, the same thing was towards the fans. And the same thing was if each part of the team everything was fed with alternating current, we only rectified for the integrated circuit. But now an inverter, no. Now, a gate, that is the one that commands the integrated circuit and turns on or off. Now an inverter, as we were talking about just now, it is rectified, the power factor is corrected for the entire team completely. In fact, something additional, a preview of something that we will see later, we will also be passing through another IPM to feed the fan, both inside and outside. IPM does not know what it means. Do not worry about this. It is something that we will talk about next because we want to reach with all our journey towards the compressor and towards the fan. But before explaining how the IPM works, I will explain to you how the inverter motors work, because it is essential that you understand how the inverter motors work. Both the gas compressor and the fan work the same. And there, if you are going to easily understand the IPM, what its work is and how the integrated circuit gives it the notice to turn faster or slower. Well, in the next video, I will talk about how inverter motors work. Okay, now I'm going to explain how motors work. To explain this well, I'll need to explain to you how an alternating current motor works, because many people really don't know how it works. It is essential that you understand it well. In turn, this explanation that we are going to give you now will help you a lot to better understand conventional equipment. So far, in conventional motors, we had 3 points to which the motor coils were connected. Any motor of any type, from a ceiling fan to an air conditioning compressor motor, had 3 points, which we called, and still call because they still exist, common point, start point, and run, work, point. The common point is common. So, how do we energize all this? Well, all of this is energized with alternating current. This is energized with one pole, this is energized with another, and from this we will leave and cross a capacitor, and we will feed the start coil, the coil with the most resistance. So, the alternating current flowed through the work coil normally, but through the start coil it flowed through a capacitor. This is a capacitor, the normal capacitor that we find in conventional equipment, which is a phase-shifting capacitor, completely different from the function of a capacitor in inverter. Why does the motor rotate? Well, the motor rotates because what I do is energize at different times. Here I tried to draw some arrows, energize different times one coil and another, towards one side, towards the other, towards one side, towards the other. So, the motor is magnetized inside and a turn is produced. Now, we only have one phase. What does this mean? That the electrons go and come back, go and come back. And we need other times too to be able to start it. If we only energize this coil, the motor would be stuck, still. For you to understand, have you seen when the capacitor is not connected the noise that a motor compressor makes? So, a phase-shifting capacitor is placed, which does what it does is accumulate the electrons here and, in an infinitesimal moment in time, then sends them. And thanks to that, one coil is energized first and the other is energized second. So to speak, it creates two phases at different times, powered by the same, but at different times. This already allows me to have more magnetic fields out of time and the motor starts to rotate. Then I will show a video that will help us to understand it better. But well, until this point we were like this. In fact, the speed of the motor, its way of working, will be given by the manufacturer, which will manufacture its motor according to the alternating current for which it is made to work. If the manufacturer made it for 50 Hz, it has to be fed with 50 because it is made for those times for the turn to be produced. If we feed it with 60 Hz, the coils and the turns will not coincide and it will have excessive consumption or directly the compressor will be stopped. This has to respect both the voltage as the frequency that the manufacturer indicates. You have to respect yes or yes. This is a motor like we were seeing motor compressors, like we were seeing fans. But in inverter this changed. In inverter it is different. Now we no longer have two windings with different resistances, perhaps 3 ohms and 1.8, but now in inverter we have motor compressors that are 3-phase, work with 3 phases. What do we refer to with this? Well, now in inverter what we will have is 3 points also, but with 3 coils exactly the same. If they are going to be 2 ohms, they all have to be 2 ohms. As the resistance decreases, they are larger motors, that is still respected as the conventional one. But now we need to feed these 3 points separately. And here, we are going to send one phase at a time, between these 2 other phases another time, and between these 2 other phases to another time. As a result, we are feeding our motor compressor with current, 3-phase in 3 different times. I make the electrons go towards one side, towards the other, towards the other, towards the other, in different times. Now, how do I do this? The one in charge of creating the electron entry, output, and output is the IPM, Intelligent Power Module. With a direct current feed, it will create an alternating current, but already of 3 phases. And so the motor compressor worked. And as the IPM is the one that creates this 3-phase alternating current, he can change the times. He can make this faster or slower, the alternation between the feeding of one coil towards another. This is the IPM, and, with a video, I will show you how a 3-phase inverter compressor works. Let's move on to that, then, in the next video. Okay, let's see in the next video how these compressors work. Every motor works in the following way. It is fed in a certain way that produces an electromagnet. In fact, if I make electrons pass through a metal as a core, that metal will become a magnet with a positive and negative pole, depending on the side to which the electrons circulate. On one side it will have more electrons, and on the other side it will have less. And that will then create an electromagnet with a positive and negative pole. If I turn the power around, what I do is polarize it in reverse. If I had another magnet, I could attract it with these electromagnets that I am creating through electrons, as we are seeing in the video. This is how any motor works. In an alternating current motor, these times are being given to it by the frequency of the alternating current that enters the home. But a controlled 3-phase motor, such as one of the inverter air conditioners, has 3 points, 1, 2, and 3, through which the electrons enter and make them circulate through the different coils. We will see in this video how it shows us how this rotation is produced. If I make the electrons circulate at different times, I will make it turn faster or slower. And that is what the IPM does. It is doing that circulation of electrons from one side to the other, from one side to the other. In the video you will see in detail how the IPM does this. Although it is simple, the important thing is that you understand how a motor works. Let's see a more complex one. And again we have 3 phases out of phase in time, that is, they do it at different times their entry and exit of electrons. As you could see, this is how a 3-phase motor works. We have 2 ways to configure it. One is like this, which is in the triangle configuration, which has more final speed, but less start torque. And then we have the star configuration, which is in which all the coils are joined at one point, so the circulation is always produced in 2, which is a way to configure that has greater start torque, but lower final speed. 3-phase motors have these 2 ways to be configured. The third cable is left unused. It is the one that is used as the Hall effect sensor, because the third cable has a coil that is not energized. And as this coil works like a motorcycle pump, as we have been talking about, all the coils work like this. What it will do when it is energized, but with a little magnetization, is to finish discharging that magnetization in the cable that is left free. Then, the IPM detects it and can know at what point there is an empty point and know if the motor is or is not rotating properly. The third cable is used as a rotation sensor. Through this video you were able to see how a motor works. Now we will see how this is produced in an IPM to make a motor rotate at a different speed. Let's go to that. So, what is an IPM inverter and how does it work? Let's talk about that right now. Looking at the board, the IPM is the component with the most terminals in an inverter unit. It is located exactly after the capacitors because it is powered by the voltage that the capacitors have filtered. The output of the IPM goes directly to the compressor motor. For example, let's look at this track tracing on this LG board. We have an IPM powered by capacitors. The negative of the rectifier goes to the capacitor. The positive of the rectifier goes to the capacitor, which filters the voltage. After that, we go one way to cross these resistors that work as a fuse, which are resistors with a very low resistive value, and we enter the IPM. On the other side, from the other output of the capacitor, we cross these 4 lines that are jumpers to jump that track, and we are also going to power the IPM. At this point, we have the IPM exactly. In fact, if I show you an IPM, you will clearly see that it is located in that way. This goes, of course, upside down. On one side, we have the connections a little thicker, and on the other side, we have the thinner connections. For now, we are not going to talk about this, but we are going to talk about the thickest. We have a positive and negative supply of the rectified current. In the middle, we then have the 3 outputs that will go to the compressor. We feed with negative and positive, and with 3 outputs we go to those 3 cables that I connected as a test of tests that we will do later. But if we look from the other side of the board, it is the tab where the 3-phase compressor motor is connected. Well, you saw the whole journey that electricity takes on a board to reach a compressor motor. And we still need to understand well how the IPM inverter works. We still have to understand that point well. And now we are going to go to that. Physically, this is the component, which is glued to the heat sink. It always gets very hot when creating that 3-phase current. Now, with a small diagram, we will understand how it creates this 3-phase current. It is very simple, you will understand clearly. Using this diagram, we will understand how an IPM works. The first thing we need to do is to identify the inputs and outputs. We are always talking about electrons. Remember that electrons enter through the negative terminal and exit through the positive terminal. And at this point is where we have the DC power supply of 310 or, depending on its voltage, 155 or 180 volts in DC, which comes rectified and everything prepared to create it in 3-phase. This device will transform the DC current into AC. That is why the IPM, the main component that gives the name to the inverter. Well, at this point we had the input of direct current, but in these 3 points U, V, W, that is how a 3-phase voltage offset is represented with those letters. They are not abbreviations of anything, not even the initials of any word, they simply point to a sequence that we have connected in these 3 points. Well, in those 3 points it is known where the coils are connected. We have a coil here, we have another here, and here we have another. And what we have to do is that between those 3 coils of the compressor motor, let's turn or pass the electrons at different times. We have to make the electrons go in that direction, and we also have to make the electrons go in the opposite direction, and at different times. How does this happen? Well, here we have 6 points that are going to enable 6 electron bypass keys. They open and close, and all this at different times. What happens, for example, if I open this key through a notification at that point, and I also open this one? If I open this and open this, the electrons will enter through here, cross this key, and exit through here. Then, by deduction, they will cross, sorry, I drew this point wrong. By deduction, they will cross the coil that is between U and between W. They will cross this in this sense. Now, what happens if I don't want the electrons to go from U to W, but to go from V to U? Well, that is also simple. What I have to do is, instead of opening this and this, now I have to open this and this. Then the electrons will enter through this side, they will enter through there, the gate that is open. They will cross from W and they will go to U because this is the one that is open to exit. We cross the same coil but towards the opposite side. If I open these two, the electrons enter and exit through here. If I open these two, the electrons enter and exit through here. If I open, for example, this gate and this, what will the electrons do? Well, the electrons will enter through the side that is allowed, and they will exit through the side that is allowed. What coil will they cross? They will cross U to V. So, they will cross U to V. If I want to go from V to U, if you want to go backwards, and well, these two are reversed and open the opposite ones. So, in that case, I open this and this, and the electrons will enter through this point, cross from V to U, and exit through the positive. We always enter through the negative and exit through the positive. That is always the case because there is DC, but I make the electrons pass from U to W, from W to V, from V to U, from U to V. I change their direction by opening synchronously different gates. And this is how the three-phase current is created in an inverter compressor. One important detail is that even the compressor motor is part of the electronic equipment. The compressor motor is part of the electronic equipment because for the circuit to finish working it needs the compressor. This is why in inverter it is so complex, because even the last coil of the compressor is an integral part of the electronic system of the entire electronic circuit of the equipment. That is why we cannot make inventions like placing any compressor, any IPM. Everything is completely synchronized and configured, and everything in order. Now, look at the points that I am going to mark now. Let's see. Let's tidy it up a bit. And we will mark with red the points of the IPM of the thick side. That is, these points that I am going to mark now are the thick side of the IPM, the side that the voltage enters and the strongest voltage leaves. But, what is all this? Well, all these points that come from the microprocessor, a delicate part of the board, are the ones that I am going to mark now with green. They are the notices, so that perhaps the gates open at the time that the microprocessor wants. They are also sampling points of the input of the electrons to the different differentials of the different gates. These gates, in reality, are IGBT. It is a special form of transistor to support high current and high speed. They are also not JVT or MOSFET, in case anyone asks. They are IGBT, and they are powered with 15 volts. We will talk about this later, but I will tell you in advance. They are powered with 15 volts and there opens the gate and lets the electrons pass. I will explain this later. All these green points, and we still have more. We also have here, and look at these are direct samples of U, V, W, and here we have two more. All these green points are these sides. This side, excuse me. It controls how the electrons enter, controls how they exit to the coils, controls the state of the coils, activates the gates, and measures the temperature. It is a complex circuit that is in direct contact with the microprocessor. This is how the IPM works, creating the three-phase alternating current for this three-phase motor to work. Depending on how it opens these gates, at what time it does it, the compressor motor rotates faster or rotates slower. Excellent, this is the circuit here as we see it. Now we will move on to seeing it on the boards, and then we will move on to controlling this component to know how it is measured. One detail that I want to mention before finishing this part, these diodes, how these gates open and close constantly, a spark is produced. These diodes, in this position, consume the spark so that these gates are not damaged quickly. These diodes consume that energy, and they are always placed between the output of the compressor and the negative and positive poles, but of course they are placed in reverse, in direct. We will talk about that later, but that was the component that I needed to explain to you. Now, let's go on to see it on the board and make measurements on the IPM and also on a three-phase inverter compressor motor. So, at this point, what we are going to do is to check the state of an IPM but on the electronic board. For that we have the following images and also a previously recorded video that we will analyze together. Take a look at how this measurement is being done. The first thing we have to detect is which of the poles of the IPM is the positive and which is the negative. Remember that the idea is to control all this with the equipment connected, but without having to disassemble it completely, with the equipment installed without power. You will only see this side of the board. So, we have the capacitors, we have negative and positive pole, and what we are going to do is to search for continuity between the positive pole and the different points of the IPM to find which is the positive. We are going to put the multimeter in continuity position. Keep in mind that this is very well varnished, so you will have to find points where you can make measurements, such as these small perforations. These perforations are to pass with the continuity or with the track from one side to the other of the board. They are perforations that allow us to make measurements. So, we put the multimeter there and in the different points of the IPM to see in which one it gives continuity. We will continue with the video. We see that there is no continuity and there is continuity. Well, there we have identified one of the two poles. We were able to identify the positive or the positive input to the IPM. We continue, we move on to the negative side. We are measuring from the negative of the capacitors and we are going to control on all the different points to see with which one we have continuity. And there we can already see it. It has continuity with the first. So this is the negative input. Very well, what are we going to do now? We are going to put the multimeter in diode position because what we have to do is to control these diodes. Remember that here we were with these diodes connected in parallel to the IGBT, and what we are going to do now is to try from the positive towards U, V, and W. What are we going to be controlling? Well, these must be completely open. There should be no continuity. Usually, when they burn out, they go into short circuit. So we try in diode position. From W to P, we are going to measure this diode, and that will give us a parameter that internally the IPM is in good condition. We will go from W to P, also from V to measure it is diode, and also from U to measure this third diode. We will not control the IGBT at this time, because it has a high resistance, it must be open, and when it burns out, it usually gets stuck. So what we are going to do is to control this diode in parallel to be able to check its state. And the same we will do from negative. We will go towards U with a negative also towards V, and also towards W, checking in diode position the multimeter, always checking the value of this diode that we have here. Well, then let's see how in the video we do just that. The resistance, or rather, the voltage drop of the diodes, will be the same as all the diodes, only it will be a little higher because they are diodes with more electron flow that support more current, so the voltage drop is even lower. Let's continue with that. We advance a little in the video, and notice that we are not measuring from the IPM, we are measuring from the capacitors, towards W. We know that this goes through the IPM, we already know that. So we have then between positive and W, placing the electrons from the positive, we have the voltage drop of a diode. Energizing or sending the electrons from the positive to the W, now from the positive to the V, we also have the voltage drop of a diode and also towards the U. We sent electrons from the positive to U, V, and W, and the voltage drop of a diode appeared. Returning to the diagram, what we did was send electrons from the positive to U, V, and W, and we clearly see that the diodes are placed in direct, the electrons must pass. So far, we are good. We continue advancing, and what we are going to do now is to invert, and we are going to send the electrons from the other side, from the U, V, W. Notice that here we have the negative, and although at first a small data appears, then what happens is that it opens. So it remains open as it should, the electrons do not pass through those three diodes. Well, to this point, from the positive, or rather, from U, V, W to positive, the diodes are in reverse, then we mark OL. Now what we are going to do is to go from the negative, because we also want to test the other three diodes. What we want to do now is to test from the negative to U, V, W to test these three diodes, and with them the three igbts. Now we are going to go to the negative, and sending the electrons from U, V, W should give me a voltage drop. We send electrons from U, V, W to the negative, and the diodes are in direct. We take it well. And now what we are going to do is to invert the cables, and in this case the electrons do not have to pass because we are going to send them from the negative to U, V, W. Now we have an open line. Well, with that we are controlling quite a bit of an IPM. Of course, this is the voltage-free test. We still have the voltage test, but to this point we are quite advanced. We are testing this component that is the IPM, a component that is damaged a lot because it handles a lot of power. We were testing it in this way, in function of diodes and without disassembling, which is key. The idea is that you learn to do those measurements without completely disassembling a board. Well, let's keep going. Here I have an IPM that I wanted to show you. What we tested was the IPM, which goes placed like this, but from the other side. In this case, we have an IKCM15F60GA. This is the model of the component. Don't worry, later we'll talk about how to acquire these components. We'll talk about the price, how to have them shipped to you. So don't worry, we'll talk about it a lot. Excellent, this was the voltage-free test. Well, up to this point then, we have been seeing a fairly simple IPM diagram. But let's see a slightly more complex diagram, which is not actually more complex, it is how a diagram of an IPM really is. In this case we have the same model that we physically have here, it is an IKCM15F60. If we look at it, it is a more complex circuit than what we have been seeing so far. But basically, the power part, obviously, is the same. We will have the 6 IGBT. We will have, from its control circuit, the warnings to those IGBT. These are warnings that will cause them to activate. Every time we press on those points, the IGBT will activate and will let electrons pass. I don't know if I mentioned it, but with 15 volts in direct current is how IGBT are activated to allow current to pass through. And from the other side of the delicate part, well, here's where we have all the control zone. Let's say that all this goes to the microprocessor. And from this side, thicker, well, we have P, U, V, W, and neutral separately, which in the end, inside, are joined together. This is the input of the electrons, so it is a bit more robust and has more terminals. Well, this is an IPM. It is the most complex circuit of an IPM. It is not necessary to understand all this operation of each component that is within its integrated zone to understand how it works. But I do want you to know with this that not all IPMs are the same. Not all of them have the inputs in the same place. So, what you have to understand is that you cannot replace it with just any one. You have to put exactly the same if you do not want to modify the electronic board. Attention to that detail. You have to buy the same one to be able to place it in the place where it corresponds, and that each terminal coincides. Keep that detail in mind. Very well. This is an intelligent power module. Attention that this is an IPM, intelligent power module. It has a complex circuit inside that, in reality, is not the one that is most damaged, but the one that is most damaged is the area that handles the largest amount of electrons. The area that handles the power. This is the area that is most damaged, and that today we already learned to measure. Well, let's see then how this works. But let's see it with the equipment running. We will do the IPM tests, but with voltage. Well, basically, what the IPM creates is an alternating current. How does it create it? Well, we've been talking a lot about how it synchronizes the gates to open. Finally, it ends up creating a three-phase alternating wave. Let's see if we can draw it correctly, as follows. Okay. This is not how it creates it. This is what the motor understands. In reality, what the IPM is going to create are pulses, always of the same height. In reality, it does not create a sinusoidal wave, but rather it creates pulses that the motor eventually understands as sinusoidal waves. So, we're going to draw it like this so we can understand what we're going to see later on the oscilloscope. One detail I want to mention is that the peaks of these waves are always 310, and that is because we have 220 volts. These are always the peaks, even if they don't show up in the drawing. The peaks are always those. And now we're going to erase the sinusoidal wave that is not actually there. And something like this is created. Electrons enter, exit through different paths. The same in another time. And the same in another time, which would represent the red. This is what makes the inverter motor rotate. And this varies in frequency and becomes shorter, wider, shorter, wider. Okay, we're going to see it with the measurement we're going to see now. Look then, measuring with the oscilloscope or working compressor. Let's see if we can see. We're going to place the oscilloscope between two of the points, between V and U. V and W are the same. And we're going to turn it on. We can see how that frequency is starting to be created through pulses. It doesn't look good there, but we're going to press the automatic key and calibrate the time. And we're going to put it in a position where we can see and understand everything we were explaining. We're changing the time that the oscilloscope shows. It looks much better there. We're only seeing one phase because this oscilloscope is only one channel. If we placed it in any of the other forms U, V, W, in any way, we would see the same, but at different times. Notice that the frequency at which it is working is actually almost 1000 Hz. What is commercially said that an inverter works with 15 to 120 Hz? Well, in reality, it is something commercial. In reality, the frequency that the IPM generates is higher and ultimately ends up creating a sinusoidal wave of less frequency. What this is measuring is each pulse. We can see it better there. This cannot be measured with a multimeter. The output of the IPM cannot be measured with a multimeter. I'm going to show you now in a slightly more stable video how the compressor accelerates and decelerates. There we have it running at minimum revolutions. It's a long video, so I'm not going to play it in its entirety. But notice how the time it takes from one wave to the next shortens. We put more cold on the equipment so that it spins faster. We asked for more cold. And notice how it starts to shorten. They start to be closer together. That is, the simulated sinusoidal wave that is created gets closer. And there we would be almost at maximum speed. We are always respecting the RMS voltage. It is always respected because it is an average. Because a simulated sine wave is eventually created. The maximum is 324. We are well at 310, only that there was a little more than 220 at this moment and peak to peak 650. The voltages are always the same. The voltages are the ones that enter through the line of your home, if you go back to the class where we measured the rectifier bridge. The values are the same, only now, through pulses or square signals, we are creating a sine wave that we can modify the time. And then the compressor starts to run slower again. We again make it slow down its speed. There it slows down again, let's see. I don't remember well, but I think we stop it here. We stop it at minimum speed. And now the compressor stops. There we run the time to be able to see better. And there it is off. Well, and there we have the compressor. In fact, no, it hasn't turned off yet. I'm wrong. The compressor is still running. What we are doing is changing the time with the keys of the multimeter of the oscilloscope. We are changing the time. That's what we're doing. But well, the idea was well seen. So, as the compressor running slower has a more distant simulated sine wave, and once we start accelerating we have it much closer together. Well, I'm going to let the video run a little so you can appreciate the acceleration a little more, but in real time. We will see from here, and we will leave a few seconds so that you can observe. The only way to be able to see this is with an oscilloscope. A multimeter does not give me this possibility. A normal multimeter gives me the possibility of measuring direct current or alternating current, but 50 to 60 Hz. Only an oscilloscope gives me the possibility of visualizing and understanding this. And that is why only an oscilloscope is going to give me the possibility of being able to detect, in case of failure, if the problem is the motor or the board. I can only do it with an oscilloscope. This is the work of the intelligent power module. Okay, now let's see how to measure the resistance of the coils of an inverter compressor. We will see it through a video. Let's observe how we place the multimeter in resistance mode. And, as they are three-phase and the phases are electronically offset in an intelligent way, the coils must all be the same. The resistance must always be the same. Here we have 2.3, 2.3, 2.1 ohms. The multimeter always produces a loss. Again we have 2.2, 2.1. And with the third measurement we have to have the same value, 2.2, 2.1. This is a good working inverter compressor. A small detail to keep in mind: if the capacity of the compressor is larger, the resistance is lower, because its windings are thicker and offer less resistance. And the same in reverse: smaller capacity, higher resistance. The data we just saw corresponds to a compressor that works with 310 volts and DC, obviously controlled by IPM, but 12,000 BTU. That is, 12,000 BTU or 3,000 calories, as it is said in other countries. We are talking about approximately 2.2 ohms each in its coils. This is how we check electrically and without voltage that a compressor is in good condition. Of course, we always have to always make a measurement between the coils and the ground. Always make a measurement like this, and it has to show OL. Of course, it should not have a ground discharge. In the following video, we will be discussing how to check if an IPM is in good condition when a motor is in poor condition. When we already know that it does not work with a motor in poor condition, what we most want to identify is to know if the board is still working or not. How do we know if the IPM is working or not working? Of course, we will be measuring the IPM. We will be measuring the diodes. We will be seeing that it is not in short circuit, but we want to see it working. We want to see it acting, to make sure that everything is fine there and to be able to change the motor with peace of mind. Well, it is done in the following way. Let's see then the measurement of IPM with oscilloscope, but without the motor connected. There we clearly see that the motor is disconnected. And we will see the data that they give us in the oscilloscopes, which ensure that that IPM board is working well. Let's play the video and see what happens. It is fast. This measurement is very fast. We energize the equipment, turn on the air conditioner, and a moment will come when the IPM will send electrons. Well, what happens is that the IPM sends electrons on one side only and does not receive them on the other because there is no coil that connects one end of U with a W or V with W. So, it needs the compressor coil to be able to return. We need the coil for the electrons to return, and as it does not have it placed, the electrons will be sent on one side only and will not be able to go to the other. So, what we are going to observe is what we just saw: the electrons push to one side only and then it cuts off. Of course, it is not the full voltage. You will always see a lower RMS, because it sends some pulses to see what happens, and as the motor does not start, it quickly cuts off and marks an error on the board. There we can see that the IPM is in good condition, at least in part. Because I say in part, well, because this same test that we have just done here, we have to do it by testing, first inverting V with U, the poles of the oscilloscope. Then, we have to test in V and W, and in U and W, we have to test the 6 different combinations. In this way, always seeing that the electrons go to one side, we confirm that the IPM is in good condition. One more detail, depending on how you place it, there are 3 configurations that the wave will appear down, and 3 configurations that the wave will appear up because it sends the electrons from the other side. So this is how we check that the IPM is in good condition when we don't have the motor connected, when we already know it is defective. How do we test if we are in doubt that the board does not work? How do we test a compressor without the board to know that it works well? Well, we will see that later in the universal board class. Later, doubts will be cleared up with respect to tests if we have boards and the burned motor, and we do not have a motor if we do not have a board. Little by little I am explaining all this in the training so that there are no doubts in something important, to be able to give a correct diagnosis to customers. We don't want to say that the motor is the problem and once we put the new motor in, the problem is the motor and also the board. We will talk a lot about that. Don't worry. Well, that's it for this class. Very well, at this point, what we want to explain is how the IGBTs are powered with 15 volts, or rather, what is the path of those 15 volts. So, we are going to follow up. This is going to be brief, but the idea is that you can identify and recognize them. There is a component in that area that is often damaged, and when this component is damaged, we have an error in the IPM, but the IPM is not the problem, but the component that is responsible for maintaining those 15 volts constantly. Let's observe it in the following way and see if we can identify it. Let's go this way, leaving the switch mode power supply. Let's zoom in on this area. There it is, here where we have the transformer and the other side of the switch. Starting from here is where we generate the 15 volts. These 15 volts, notice that we even have a checkpoint here. Here we have the 15 volts. They are derived on one side to this point. This is the fan inverter connection socket. We will talk about that later. And notice that these 15 volts follow a path. I went off the camera, sorry. They follow a path and reach these points. These points are for transfers. Through these perforations in the board, the voltage is allowed to pass to the other side of the board when they are double-sided base plates. Now we are going to the other side. Arrived at this point, in this area. Let's see if we can put a little more light. What is done now is to go from here to these points that feed the capacitors. These capacitors that we are seeing here are responsible for maintaining the 15 volts to power the IGBTs. These are the capacitors that maintain those constant 15 volts that will be injected into each IGBT as appropriate. An error or deficiency in these capacitors will cause us to have an IPM, motor, or overcurrent error. We will not have an error on the board that tells us the IGBT power capacitors failed. No, this error we will have to deduce ourselves when the problem is in the motor or IPM area. So, if we control that the IPM is in good condition, we can move on to checking these capacitors, and it may be that we find the problem there. Well, these capacitors are type SMD. This means that they are soldered on one side of the board, they do not pass through to the other side. So, to disassemble them, we have to heat with the soldering iron in this point and in this one. And these capacitors come out. Later, in the soldering practice, we will be explaining how to use solder and a soldering iron. So, don't worry about that. Well, the problem with these capacitors is that they are in different parts of the board. For example, in the case of this board, we can make a measurement of those 15 volts that is located in this checkpoint without disassembling the entire equipment completely. Just by opening the outdoor unit, we already have this area exposed. We can do a test between 15 volts and GND in some checkpoints, and we will see that we have the 15 volts. But to know that those 15 volts do not fall on the IGBT power point is complicated, because our test point is on the other side. So, in these boards, it gets quite complicated. Unless we identify the 15 volt points on the IPM, but for that we would even need to know what model of IPM we have here. So, these capacitors are complicated to check on these types of boards. So, if we suspect that there is this problem, we have to remove the board and test it outside. When we see the test of the complete operation of the equipment, we will be seeing how to measure those 15 volts with the equipment assembled, but in a model that can be reviewed, which is the one I will show you next. We will see the board of an LG inverter and see that the power capacitors of this LG are very visible. In fact, if we look at the board from above, at this point we will already have the test points of those 15 volt capacitors. Clearly there are capacitors here that go directly to power the IPM that is in this area. In this case, we can measure the 15 volts without completely disassembling the equipment, not even taking out the board. And here are the capacitors that keep those 15 volts. Moreover, they are much simpler capacitors. I will now show you a Carrier brand board that is a Medea board installed in a Carrier or Medea unit as well. We will see that those capacitors are even more complicated to check. One moment please. Let's see then a Medea electronic board. Let's see if we find the image where it is clearly visible. There it is. Please observe here. To access these capacitors, we even have to remove the heat sink. This is a board viewed from the bottom but with the heat sink uninstalled. In these models, we even have to uninstall the heat sink. So it's even more complicated. But well, know that it exists. That we have to test their capacity to be correct. And that the best thing is to see if those 15 volts are maintained there or a little less with the equipment in operation. When it is working, a little less than 15 has to be maintained. Well, then know that this is there and that they tend to fail quite a bit. Not only in inverter air conditioning, but also in refrigerators, fridges, or refrigerators. Excellent, having seen this, we will move on to the following topics. Very well, we will continue with our training and from now on we will talk about fans or forcers. In inverter technology we will no longer find only AC fans, like the one we have in hand, but we will also find tri-phase fans or forcers. To summarize, we could say that we will find three different types of forcers. These are AC forcers, which is the one we have been finding in any air conditioner so far and which are also found in inverter technology. We will also find DC and U, V, W forcers, these two being of the same operating mode, only a little different in the way of making them work from the board, but they are exactly the same. They are fans or forcers whose winding is three-phase, just like the compressor motor. Very well, let's start then by talking about the simplest one, which is the AC forcer, which is the one I have in my hand and I will show you right now. This type of fan has an AC power supply. What does this mean? That we will be directly feeding it with 220 volts or 110 or 127. A small phase shift capacitor will be placed. We had already been talking about this when we talked about how an AC motor works. It will have a rotation frequency of 50 or 60 Hz. The manufacturer already made the coils so that with a certain frequency of electron circulation the motor can rotate and function properly. So, It will always work according to the voltage we have on the line and the electricity. The board will only do is somehow send it that voltage. But the voltage of this motor from the board is not sent only through a contact relay, as the fans were previously powered. Now we don't have it. These relays are for working in fans with multiple windings that make them rotate at different speeds. But in the case of these fans, if we glued it with a relay, it would always rotate at maximum speed. So, we need some kind of circuit to be able to make it vary the speed. We are talking about the indoor fan, How is this change in rotation going to be produced? Let's keep in mind or think first of some parameters. What can we not do to vary the speed of this fan? Something we can't do is vary the voltage or frequency. So there we already have two things we can't vary. Because the voltage is already pre-established, that fan, at least the one we just showed, is 220 and the frequency is 50 Hz. If we vary the frequency, it will consume more electricity because the electron circulation will be confused with the rotation. And if we vary the voltage, the same. That winding will demand more electron flow due to the lower voltage and the amperage will rise, and with that the heat of the motor. So, since we can't vary these two data, how would we do the speed in a fan of this type? Well, this is produced through a circuit. The circuit that is used for this is this one that we see here on the board, which is obviously near the area where the fan is connected. This circuit is composed of some resistance, some filter capacitor, a triac and an optocoupler, as well as two power resistors. Optocoupler and triac are the main components. These two can be combined to form an opto-triac, which would fulfill the same function. Now we will explain in detail each of those components. Don't worry. Well, what function do these components perform and how do they vary the speed without modifying either the voltage or the frequency? Let's understand it without any inconvenience. We have a frequency that we cannot vary, neither the voltage nor the frequency. What is that triac going to do? That triac, which is like a kind of electron switch, that triac has a power supply at this point. It was going to let the electrons pass from one side to the other, and also from one side to the other, depending on the moment in which it is powered here. When a voltage is injected at this point, on this surface, the electrons are allowed to pass to one side and to the other. That is a triac. Unlike a transistor, which only allows passage to one side. We will see more about that later. So, when does it activate and deactivate? This is where the board needs the zero crossing detection. At this point, the microprocessor needs to know at what moments in time we cross zero. And that is where the importance of zero crossing detection comes in. These waves are symmetrical in the same way, but well, here it comes out a little more open. Don't pay attention to that. Why do we need zero crossing detection then? What the board is going to do is that, when the zero crossing is detected, the application of voltage to the triac is cut off. So, no voltage will be passed to the fan. It will wait for some milliseconds to pass, and then it will activate it. Then yes, voltage will pass from this point to the fan. All the power of that piece of the wave will be applied to the fan. When it crosses zero, the triac will deactivate again and will wait again for a certain amount of milliseconds that we will say are 3 milliseconds. 3 milliseconds are waited and then the voltage is injected and all this electron power is injected to the fan. When it crosses 0 again, the same thing happens again. The power is cut off. 3 milliseconds are waited, and then we apply the voltage again. If you think about it this way, look that if we talk about 3 milliseconds, here there are not 7. And in total, in a whole cycle, we have 20 milliseconds. According to the 3 plus 7 plus 3 plus 7, we have 20 milliseconds. These 20 milliseconds happen 50 times in a second. This is how the fan speed is regulated. If we wanted it to go slower, if we configure it at a slower speed, well, instead of waiting for 3 milliseconds to pass, it will wait for 7 milliseconds to pass. It will wait for 7. So, it will only apply this power to the fan. When it crosses 0, it cuts off. It waits for 7 milliseconds to arrive, and only 3 milliseconds of time are applied to it. It waits for it to cross 0, it disconnects. It waits 7 and at that moment it applies from when it crosses 0 to wait 3 milliseconds, 5 or 7 milliseconds to turn back on and inject the electrons again. We need zero crossing detection because if not, there will be confusion between one side and the other of the electrons. It crosses 0, and when it activates, they are sent to one side only and then it is cut off. Then they are applied to the other side and then it is cut off. And then they are applied to the other side and then it is cut off. And the electrons go one way and come back, stop and come back. We do not vary the voltage, which remains the same, in this case, a peak voltage of 310. Nor do we vary the frequency, because we are not shrinking or moving away the electron sending. Respecting voltage and frequency, we can have a speed variation by sending less electrons. This is how the speed of an AC fan is regulated. These fans, of course, also need a capacitor to work. They are motors that we have already been analyzing, of alternating current of 220. We would not see the frequency or the voltage. Here are the coils. We will see all this, but we will go on to see it on the board. Well, then we are going to see in the electronic board everything we have been describing about how the fan works and how its speed is regulated. Well, we turn on the light and now, please observe this part of the circuit, of which we have it very clear. Here we have the dephasing capacitor of 1.2 microfarads. This can also be the reason for failures if the fan does not turn well. It is removed and a new one is placed to test it. And we have here the circuit we were mentioning. Well, as this speed is regulated, we need an opto-coupler because the integrated circuit has to tell it at what speed to turn. So, we need an opto to make a dielectric division, that is, so that what happens on this side does not affect the microprocessor and it does not get burned by the high voltages that are handled here. So, let's observe the following. Here are pulses generated at the moments when they have to turn on. The optotriac is powered, which connects from the other side. And there is where then, through this resistor, a low voltage is injected at this point of the triac. And the triac will do a connection. Look at this side. Here we have the line, and here we have the neutral. Here we have the line. And the line will feed this point of the triac. This line will also come here, through this resistor to reduce that voltage a bit. And when this point is connected, thanks to the fact that this light turns on, this terminal of the triac will be fed, which will allow these two to connect, and the middle point of the fan will be fed, which will be the common. At the same time, on the other side, we have the neutral that feeds the working coil, and through the capacitor that is in this rectangle, the starting coil is fed. And this is where the cut and the on are produced, those 100 times per second, constantly. What elements can be damaged if this does not work? Any of these. That's why we're going to check them one by one. In the case of resistors, we will check their resistance value. In the case of the optocoupler, we will be testing the lead and also the other area of the circuit as we have done previously. And in the case of the triac, we will be testing directly that there is no short circuit between the two gates, or rather, between the two sources. Well, then we are going to check it in the following way. We place the multimeter in resistance position and we are going to measure from the side of the triac. We are going to measure it from the other side. We have to have a high resistance of megohms to know that everything is fine. There it is. Let's try it this way. And then we have a very high resistance that even goes to open line at this point. We are fine, we are with open lines. Now, testing towards the one that energizes to activate, we will have a resistance, which is derived from resistors that we have placed here. These resistors are in good condition, 500 ohms and 100 ohms. And here we have the optocoupler, which we have to test its light side and its opposite side. Remember that the light side we will test in diode mode. And there we have the voltage drop of a lead, 1.12 volts of drop. We are going to invert and we have the voltage drop of the diodes that are on the opposite side, forming part of the variable voltage circuit, which are the ones we have in the driver that is the one that will energize it. Very well, this is how we are testing all the components of this voltage variable circuit through the wave cut, based on a zero crossing detection. Any problem in the zero crossing detection, what we will have is a fan error. It will not work, it will mark an error or it will tell us directly the plaquette. If it is more sophisticated, it will tell us zero crossing detection error. This is how the speed of these fans is regulated. This is the way it is done electrically, and we can measure the components without voltage as we are doing now. And we can also measure this with voltage as we are going to do. Well, to measure this with voltage, what we have to do is place between the neutral and the line that is the one that comes from the triac. Between the neutral and the line, we have to place the multimeter in voltage and alternating current, since it is an alternating current of 50 Hz or 60, and this will mark us a certain average voltage. These voltages will vary depending on how many electrons are sent, and what a multimeter will do is to take an average. So, as a result, what we are going to see finally, controlling voltage between this point and this, which remember that here is cut through the triac to this power. Between these 2 points we are going to be finding, in low speed, a voltage of approximately 167 volts. In medium speed, approximately 185 volts. In high speed, approximately 205 volts. Always talking about 220 volts, what a multimeter will do and take an average, and since the wave is being cut, it will believe that the voltage is lower. In reality, the average voltage or the force that is sent to it is lower. This would be the voltage test. Remember that you will find these circuits in conventional ones, in most of them currently, and in inverters you will find them in many, especially those that are 9,000 or 12,000 BTU, or in Frigorias, we are talking about 2,250 or 3,000. Very well, one more component that I want to mention is that, sometimes, instead of an optocoupler that feeds a triac, which allows 220 volts to pass. Here we have an optocoupler and here we have the triac. Here, instead of finding these two components separately, you can find them together. When you find them together, we are talking about an optotriac, and, in that case, we are talking about a component that has a lead on one side, and on the other side we have a gate that allows the passage of 220 volts. They can also be found in this way, and the component encompasses all of this. Always, to be able to identify these components and know how to measure them, remember to look at their patent. In other words, remember to observe the number that it has on its component. In this case, we have a Mach 3021. Well, this is an optocoupler. Perfect, then I will show you a plaquette that has an optotriac. On this plaquette, we are seeing directly a power supply from the microprocessing area, and through these tracks we go directly to this component, which feeds this lead, and on the other side, directly, allows the link of the 220 to power the fan. Notice that directly from the lead, right there is where the 220 pass through and power the fan through this connector. Here we have then an optotriac. Here we have it all together, all assembled. Okay, so far with the way to regulate the speed in these fans. Is there anything else? Yes. How does the electronic board know how fast the fan is spinning? This function is not fulfilled by these three power cables, but by the three additional ones that you often see. They are a Hall effect sensor. Through these three terminals, the board knows how fast the fan is running and sends it more or less electrons through the circuit we just analyzed. In the next video, we will talk about the Hall effect sensor and how it works. Okay, so far we have been talking about AC fans. There is another parameter that we need to take into account, or another part of the fan that is also very important to function properly. In addition to the power cables that we have already been analyzing, as well as their path on the boards, we also have three additional cables that represent the Hall effect sensor. These cables allow the fan to inform the board at what speed it is rotating and whether or not it is rotating properly. It is a kind of sensor. Now we are going to explain how it works, how it is used, and how to make the appropriate measurements. This is important because if a board tells us that a fan is not working, it may be that, although the fan is rotating, the Hall effect sensor is not working. In fact, this is something that is damaged quite often. So, how does this sensor work? In this case, on this fan, we have printed on the side what each of those cables means. On one side, we have the yellow cable, VCC, the brown cable, BRN, which would represent the negative, and gray, output voltage. VCC and BRN are the power supply for this Hall effect sensor. It is powered by 5 volts, and this is the negative. And the one below is the output pulse that will notify the board as the fan rotates. So, let's diagram this and understand how this Hall effect sensor works. In reality, it is not a circuit in itself, or in other words, there is not an electronic circuit inside the fan. It is a kind of magnet that is doped in a certain way that allows for a certain notification. In fact, I will explain a little more now, but to be able to understand it. When we talk about a Hall sensor, we are always talking about a sensor made or created through a modified magnet. It works in the following way. To explain it in a simple way, it works like this. We have a magnet that, on one side, is polarized with what we saw was called G and D, which is the negative, and on the other side, we had seen VCC, which represents the positive. So, the positive enters this magnet and the negative also. Inside this magnet, there is a strip of electrons that are circulating through its center. But what happens? When we pass certain metal through this point, what happens is that the electrons move out of place. Let's say they move to this side and allow a positive pulse to exit from one of the sides. And this third one is the V out, or the output pulse. Okay, we are talking about 5 volts of direct current. Here we have the negative of the 5 volts. And at this point, we will also have 5 volts every time a metal passes by, but these will be through a pulse. Why? Because this metal will pass by here, but this is the fan that is rotating. If we continue to complete this drawing, it would be something like this. Do you understand? As the fan rotates, each time it passes through these metals, it attracts electrons and allows a pulse of 5 to go out through the output. And with this pulse, then, the board knows that the fan is rotating correctly. Well, that's how a Hall sensor works, both in air conditioning and in other circuits. The way it works is the same. By means of a magnet, we produce an output signal. Well, we have to test this circuit because what usually happens? Well, this magnet can break. This area can be filled with metal slag. Let's suppose that it doesn't break, but this area is filled with metal slag, which does not allow the electrons to be attracted when the metal passes. Well, all of that can happen, so we have to do a test. Our test will be the following. We will inject 5 volts and see what comes out from here. And we will do that with an LED. A very important detail that we have to keep in mind before is that the voltage input, the negative, and the output are not always printed on the fan. There are times when we don't know. In this case, we did know that this is the yellow cable, the negative the brown cable, and the output voltage in the gray cable. In this case, we did know which was which, and in fact we have them here with the 3 colors that correspond. But sometimes we don't know which is which. Sometimes, on the board, there is only a diagram of the following way. And it doesn't tell us anything else. Well, in those cases, first we have to go to the original electronic board and be able to identify which cable is which to then test this circuit. We will do that by simulating that. In this case, it would not have indicated us. Well, we will run a little bit of our plan and measure our pieces. Well, this Hall effect sensor is connected at this point, at this terminal, and in this position. To be able to identify which is the positive and the negative, if we did not have the small diagram on the board, the trick is the following. We put the multimeter in beep mode, which makes a beep when there is continuity. So, we go to the 7805, which is the one that generates the 5 volts, to the right point of the 7805, and see which one it has continuity with. Brown. No gray either. Yellow. Yes. There we have continuity with the yellow. What does that mean? That the yellow is the 5-volt power supply to the Hall sensor. Now, we go to the negative of the 7805, which is both the middle point and the case. And we try again. We try the yellow, just in case. No. We try the gray. No. We try the brown. Yes. It is the brown and the positive power supply. And the gray, by deduction, is the return signal. Once the 3 are identified, we take notes, draw them to be able to memorize. Remember that yellow is positive. In this case, I made a small diagram with the colors and everything, so you can do the same too. And let's do the test then with a small test circuit. The test circuit is as follows: a 5-volt power supply, a connection to the hall sensor, an LED, and a resistor so that our LED does not burn out. What are we going to do? Power with 5 volts these points. Here I have a power supply to a transformer, which will reduce it to 12 volts. Those 12 volts, then, will enter a rectifier bridge. They will be rectified and produce 16 volts. And from those 16, I will power a 7805, which is the one that will create the 5 volts to power the hall sensor. So, here I have the 7805 powered with 16 volts in direct current, and at the output I have 5 volts, and at the output I connect the hall effect sensor. We will do the following. Through one of the terminals that will go directly to the fan, to the hall sensor, we will connect the positive. So, we connect this directly to the positive of the hall sensor, which is yellow. On the other hand, we will have a negative, which will be a more common point that will close the circuit with the LED and towards the fan. And on the other hand, we will have one of the 3 cables that will go directly to the resistor and the LED to close the circuit, but this will be connected to the signal, so that each time the hall sensor sends a positive pulse, this goes directly to the LED and can close that circuit and turn it on. Let's do that test. Let's run the board. We won't need it anymore to do this test. And here we have the LED. Well, let's energize the circuit, always with safety glasses, some fuse for any problem that may arise. And we energize. Well, here, as you can see, the LED turns on and off as the fan rotates. There you can see it. We turn off the lights so you can see it better. Well, this indicates that the sensor is working correctly. Of course, when it's going fast, we actually can't observe it, because it's a very fast flicker, but the board, the microprocessor, understands that pulse. So, what do we have to keep in mind? The very important detail to keep in mind is that not all fans are exactly compatible. It may happen that we replace a fan and it is not compatible with the original electronic board, because some very specific models, for example some Samsung models, send more pulses per turn. So to speak, the board doesn't understand the fan, doesn't understand that it's spinning so fast, and it will mark an error. Keep in mind that this can happen. But most are quite similar. They have 3 pulses per turn. Another very important detail, if the hall sensor is not working, the electronic board will turn on the fan at full speed and then cut off and mark a fan error because it does not detect the return pulse. These are very important details. Having understood this, we can now end this video about AC fans. Well, another way we have to measure the Hall effect sensor is through an oscilloscope. If we connect the oscilloscope, it will give us on the screen the pulse that is also feeding the LED. We can also see it on the screen. This is in case we want to make the measurement with the electronic board connected to the equipment. In fact, it is a pulse that is actually very fast. But what we can always do with oscilloscopes is zoom in a little on the screen. There we will see the pulse in detail, as we can see it now. This is also a method that we can use. Remember that the oscilloscope is useful for all of this. Remember that it is a 5-volt voltage, but resulting after having consumed some voltage through the magnet. That is why we always have a little less, for example 2.7 or 3 volts. And this is the power that is giving us to our LED. This is another way we have to measure the Hall effect sensor. From now on, we will be talking about the other type of fans or fan that inverter equipment has. Up to this point, we had analyzed very well how an AC fan works in an air conditioner, but in inverter we now have different fan models, such as the DC fan and also the latest model that is UVW. In reality, its operation is the same as a DC, but I name it UVW to be able to distinguish it. Finally, we have one more model, which we will later explain, that is a combination of two. So now we are going to move on to the DC blower. The big difference with this fan compared to a common one is that they are 3-phase current fans. They work exactly the same as an inverter compressor. As you can see, they have a large electronic board inside. They are completely computerized. Their connections to the electronic board also imply having some communication signal between the electronic board and the fan. These fans can be found in both the indoor and outdoor units. The one we are looking at is a typical example of a fan in an indoor unit. As you can see, it has 5 connection cables. On the one hand, on one side we have a red cable. On the other hand, we have a black cable. On the other hand, we have a white, yellow, and blue one. Each one fulfills a different function, and we will explain it to understand its operation and also to be able to make the corresponding measurements, of course. One detail that you have to keep in mind and get your mind around is that these fans are 3-phase. That is, if you look inside the fan, you will find 3 points that will say U, V, and W. This is where the fan coils are connected. Pay attention to this detail. Externally, we do not have access to the 3 coils. We can only access them once we open the fan, once we remove the rear protection, and then we can already access the U, V, and W terminals. From the cables that connect to the board, we do not have access to those coils. Who feeds those 3 coils? Well, those 3 coils are fed directly by the IPM that the fan has. The IPM is the one that, after transforming the direct current into 3-phase current, makes this fan work. As you already know, when we talk about inverter compressors, the operation is exactly the same. It is an IPM with 6 igbts or passkeys that are powered by 15 volts and that make the fan rotate at the speed it wants. Of course, it will always receive a notice from the board to know at what speed it has to rotate. Let's go to that. We look at this image. We will go through one by one what is the function of these cables. In the diagram, of course, we have it, but well, we are going to explain it so that it is much clearer. The black cable is always negative. It is the negative power of this fan. The red cable is the positive power of 310 volts, in case you have 220. If not, it will be 155 in case you have 110. The white cable, well, we don't have white color, we'll draw it in gray. In fact, we have it, but it wouldn't be seen. We'll put it gray to be able to identify it and understand it. It is a direct current voltage, also positive, but of 15 volts. It is the voltage that the electronic board of the fan and the IGBTs need to be able to activate. The yellow cable is also a pulse in direct current, but that goes from the board to the fan. It is a 2.5 volt pulse that the board sends to the fan to inform at what speed it has to rotate. And finally, the blue cable is also a pulse in direct current, but the other way around, from the fan to the board. But this pulse oscillates between 14 and 17 volts. So, to understand it again, fan power supply. With the red cable, all the necessary direct current voltage is sent to power the fan directly, 310 volt, 255 or 180, depending on its voltage. This comes directly from the filter capacitor on the board. Black is the negative, which is shared for all positives. White is a power supply that the electronic board gives to the fan of 15 volts that comes out after the switched power supply. With this 15 volt voltage, the fan board can be powered and also the igbts to be able to activate them and create the three-phase current for the fan to rotate. Yellow is communication from the board to the fan through an average of 2.5 volts. And blue, on the other hand, from the fan to the board, is informing a kind of Hall effect to inform at what speed it is rotating. This oscillates between 14 and 17 volts. Understanding all these parameters is how we will be doing the corresponding tests. Of course, as always, the first test we will do will be without voltage. The first test will be to measure the resistance between different points, and that is what we are going to teach now. Let's go to another image. Very well, here we have it. If we want to check the operation of this fan in resistance mode without energizing, obviously with the fan outside, what we will do is measure between black and red in the first instance. The resistance that should give us is approximately 20 megohms. Very high resistance. Another measurement we can do at that point when making the measurement without voltage is to measure in diode position. This is another measurement we can do. If we measure in diode position, the approximate value that it will give us will be a voltage drop of 1.2 volts to one side and to the other side. Oh well. Why does it give us this value? Well, remember that directly from these 2 points to the fan we are entering an IPM. And you remember how the IPM works. Let's see it again. You know that the IPM had, on the input side, that we talked about a positive and a negative. Look that we always find a diode and another diode, a diode and another diode, and a diode and another diode. So, if I inject electrons from here with the multimeter in diode position, and I exit from here, the electrons will be able to pass through these diodes with a voltage drop, but towards this side they will be able to pass. So, from one side injecting electrons from here will mark me approximately 1.2 volts of voltage drop, which is the sum of two diodes, because it has to go through one and then has to go through the other. But on the other side, look that in reverse it will mark us OL, because we have the two diodes in reverse. So, injecting electrons from the positive, they have to pass and a voltage drop has to occur. Injecting electrons from the negative, nothing has to happen. Let's see a video in which I am doing that measurement. Now we can see the fan, we can see it well. This model is from LG. And we can see its label on which it clearly tells us what we were seeing a moment ago. And we are going to do that measurement in diode position. We inject electrons through the red positive and we have a voltage drop of 1.185 volts. With the black multimeter, I inject electrons, and I inject them through the red of the fan, which is the positive, but if I invert the cables, what happens? I have to have OL, and it is perfect. The IPM is in good condition, at least as measured from the outside. So, that is another measurement that I can do on these fans, in diode position and in resistance position, at least between red and black. Very well, now to be able to measure the following points. For example, black and white, at that point, so that you have a reference, the resistance will be approximately of 40 kiloohms. We always take black as a reference, black to white. And now we are going to go from black to yellow. And at this point the resistance will also be high, 200 kiloohms. And finally, between black and blue, and the resistance here will also be much higher because it is an internal sensor, approximately 50 megohms. So, see that from black to red the resistance is high, from black to white also, from black to yellow also, and from black to blue also. In the case of finding values much lower than these that we are going to take as a reference, we could say that some part of the circuit is short-circuited or is in poor condition. These are measurements that we will make from outside the fan. Measurements without voltage are measurements to which you can access with the fan in hand. But of course, there are more measurements to be made, and the other measurements are already on the electronic board and even with the equipment completely energized. In fact, to avoid going around in circles, you have to detect the values, the voltages that indicate here. These are the voltages that you have to be able to measure when the fan is placed on the board in the corresponding socket. We can see a socket on the board of those fans. So, having understood how the fan works on the outside, we are going to mention the following. If we see that it is damaged or any of these numbers or values is wrong, any of these components could be the problem. We can have problems with the IPM. We can have problems with some of the internal low voltage resistors, some of the SMD capacitors. Any of these components could be the problem. My recommendation is not to repair these fans, because when we disassemble them, we usually give them a small blow to the bearings and they never work well. If you detect a failure from outside the fan, I recommend direct replacement. Of course, sometimes you may want to repair and there is no problem. In the folder of manuals and diagrams that we will send you, you will find a Word file that says links to YouTube videos that are videos that I myself saw in which some people make different repairs. For example, there is a video in which the IPM of this fan is replaced. Finally, it is left with a small noise from the fan precisely because of disassembling it and touching it. But well, it can be done. The spare parts are available and it will depend on you. For the cost of the complete fan and the risks, I recommend not to do it, but well, you can see it. Well, an important detail to keep in mind when replacing these fans or looking for a replacement are the following. A very important detail is to see that the voltage is compatible. In this case we have one of 310 volts because in my area I have 220. Another important point is the power in watts. You have to keep in mind that it is as similar as possible. Of course, the revolutions are a detail that previously in conventional equipment we did not take into account, but now that everything is electronic, we have to pay attention to them. And the direction of rotation. In the case of internal fans, we will not take into account the direction of rotation because it is always the same, but external fans do. The direction of rotation goes according to the plastic blade. So, keep in mind that it is for the same direction. So, quickly said, voltage power revolutions direction of rotation technical data sheet. Another important detail that you should not forget is the length of the shaft. Well, in fact, if the length of the shaft does not match, you will realize it over time. It is a detail to keep in mind when going to buy and to avoid unpleasant surprises. Afterwards, I recommend measuring the length of the shaft to be exactly the same as the original fan. Of course, all this in case you are going to buy a replacement and you do not find exactly the original one that the equipment had. Well, very well. Here we have with us an LG board that has a power supply to a DC fan. In the connection socket, we see that there are 7 pins, of which the first is the positive power of 220, then there are 2 blank spaces, and then follows negative 15 volts and the 2 signals. We are going to see then a little of the circuits to understand how they are powered. We always have to go back to tracing the tracks to always orient ourselves in the different areas of the board. We are going to use a multimeter tip to be able to mark. Let's see that here we have line and neutral. With line we cross the fuse. We follow the line. We cross a coil. We follow the track with the neutral. We cross another low-pass filter. Here we have the 2 capacitors, here the 2 filter capacitors, capacitors and coils. We continue the route and what we are going to find is the AC rectifier bridge, AC, DC, DC. Here we have a continuous, positive, and here we cross the 5th diode. And here we have the negative. Both will follow their path to this point. Here we have negative and here positive. Evidently, this large connection at this point is the filter capacitor, larger than the normal ones. Remember that this internal board also has to power a fan through the filter capacitor, so the filter capacitor will be larger than the normal boards. We have a 100 microfarad capacitor. Excellent. From the negative, of course, we will be powering, if we follow the tracks down, the switch, and then we will reach the transformer, which is this one. But also, from those 310, we have to go out to the fan. Here we have the negative of the fan, and from the positive also, here we are going to cross a small inductance, the small filter coil, and we reach the positive of the fan. This shows us that when the board is energized and receives the rectified voltage, it powers the switched mode power supply and powers the capacitor. The 310 to the fan automatically appear. These 310 volts, when we make a measurement with the entire equipment running and measure at these points, between positive and negative, we will find 310 always, whether or not the board is turned on, whether or not the fan is turned on. Better said, the board is on, what is not on is the air conditioner, but those 310 volts enter the fan. But the fan still doesn't work because it first needs 15 volts to power its electronic circuit and then enable the igbts. So let's get to that. Those 15 volts that the fan will receive through this point and this, they are received only when the fan turns on. And how does it do that? Through an optocoupler. The processor informs the optocoupler that it has to turn on and activate the 15 volts to enable the fan. That will only happen when it needs to turn on, that is, when I turn on the equipment. At that moment it will turn on and the 15 volts will be injected into it. This point, which was the information that the microprocessor has to give to the fan to tell it how much it has to turn, will also be given through an optocoupler. And this third point, which is the information that comes from the fan to the microprocessor, will also be given through an optocoupler. Always to keep the zones separate. Of course, a fan can be damaged, short-circuited, or exposed to more dust. We don't want that to affect the microprocessor. That's why optocouplers are used. If you look closely, there are two that have to inform from the micro to the fan, to activate the 15 and to inform how much it has to turn. And there's one that has to inform from the fan to the micro. That's why you're seeing that they are placed in two different positions. There are two on one side and one on the other. 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3. For maybe if we see them from the other side, you will be able to understand them better. You already know where the point of the LED is. Here we have one and here another towards the fan, and here we have one from the fan. We have it marked on the board. Of course, any damage to these optocouplers or the components that surround them, which are all of these, any damage to any of these resistors, capacitors, jumpers, or transistors, which we will be learning how to solder, know its value and replace, any damage to these affects the operation of the fan. Pay attention to that detail. And one more detail, if the switched mode power supply, here we have the switch and here we have the transformer. If 15 volts are not generated from this side for it to work and activate the fan, well, we will not have the 15 volts for that. IGBT then will not work either. So any damage in this area, the fan stops working. That's why, check all of these components very carefully and, of course, follow the tracks. You will see that the tracks are very fine, and believe me, many problems are due to burned or damaged tracks. Well, this is how a fan is energized. Keeping all this in mind, later we will test the voltage with the equipment running and, at that point, you will deduce if the problem is the board or the fan. What is often what we want to know. Or maybe we have a problem in the fan, but we also want to see that the problem is not the board. You also have to know how to understand everything we explain for the measurements we are going to make. Now we are going to talk about the third type of fan that we will find in inverter air conditioners. I call this type of fan U, V, W, because it has three wires, U, V, W. It works the same as the previous one, but the big difference in this one is that only the three-phase coils are located inside the fan. The IPM and all the circuit that controls it is located on the electronic board. Understanding this, there are two details that you will have to keep in mind. In this case, it is located on the external board, outdoor unit, as the external board controls all the details of this fan, speed, rotation, power consumption. It is essential that when you replace this fan it is exactly the same. Attention, that detail has to be exactly the same because the board controls everything. So, any data that the board finds wrong will already mark an error. We are talking about voltage, power, amperage, rotation, and, of course, direction of rotation. It has to be exactly the same. When replacing, we have to get the same model. Another disadvantage of this fan is that when we place a universal inverter board, we will explain how to do this later, we cannot adapt this fan to universal boards. We have to change the fan. This does not adapt to universal boards. Another disadvantage, which I will explain better later. So, how do you measure these fans to see if they are good or bad? It is done only in resistance mode, and the resistance has to be exactly the same in all points, 97 ohms, 97 ohms, and 97 ohms. The resistance has to be the same. It is a three-phase motor. Its phases will be run in time thanks to the IPM. So the coils have to have the same resistance between them. Please observe on the board the IPM of these fans. Here we are seeing a carrier or Myers board. In Mexico, it is known as Myers, and in Argentina or other countries, it is the Carrier model. And in many other countries, this is the same as Medea. In fact, the electronic boards are Medea brand. Whenever a board says KFR, we are talking about Medea boards. Well, this is the IPM of the fan. This one we have here is the IPM of the fan. You will identify it because on the board you will find a heatsink further away from the main heatsink. Sometimes, the IPM of the fan can be next to the IPM of the motor. They tend to be together using the same heatsink. In the case of this board, no. So, what does the Teams microprocessor do? The microprocessor is the one that tells it how fast it has to turn. Through these tracks that we can see here, the microprocessor tells it how fast it has to turn. When we get closer, we can see the tracks. And the IPM also informs it at what speed it is turning and what consumption it is having. There is constant communication between the fan control device and the microprocessor. We will also find the capacitors that maintain the 15 volts of the IPM and nothing else. After that, the only thing we have is the connector that connects the fan and the U, V, W terminals. So, the entire control circuit is directly on the external board. The measurements that you can make are many. Anyway, you know how IPMs work. You just need to know which is the 310 input and the U, V, W output to be able to make the measurements that you already learned in the compressor classes and the three-phase motor class. Exactly the same as to measure all the parameters of an inverter motor. What else can you measure? The capacitors that maintain the 15 volts. And also, please do not forget the communication tracks. They are tracks that we can barely see at first glance. Use a magnifying glass, use a microscope, and observe that no track is cut. Because many times the problem is that sometimes we take the board to an electronic technician and we only see that he connected a small cable and the board already works. Because the tracks are often cut. So don't neglect that detail. Don't think that it can't be damaged. The tracks are damaged very often, please check that. Those are the details of a U, V, W compressor. To keep in mind that we have these fans, we will see some photos. There is another photo of U, V, W. They are very solid, very robust, they are heavy. They have permanent magnets inside. They have good rubber pads to hold them. We can observe it here. And the speed measurement, remember that it is produced through the loose cable. The loose cable produces a voltage drop. The one of the three that remains free produces a voltage drop which informs through the IPM to the processor the direction of rotation, better said, the speed of rotation. So it's like they have an embedded Hall sensor, just as we talked about with inverter compressors. But we have one more model of fans that is similar to this one, and I will go on to explain. As I said before, you will find a certain inverter fan, U, V, W. But what you will also find, here comes a three-phase current created by an IPM, but within this, you can also find one with 6 cables, which has 3 power cables and 3 Hall effect sensor cables. Keep in mind that you can also find these fans, but with 6 cables, since their electronic computer does not have the ability to detect the rotation through the loose coil. So, what do they place? A Hall sensor to be able to make that rotation measurement. Keep in mind that you can find it like this. If you find this format, the Hall sensor measurement is the same as we explained in the previous videos. It is powered and it is seen if there is a return pulse. And the coils, of course, are controlled exactly the same. In this case, the IPM is inside the electronic board. Well, know that this model of fans also exists that you may find at some point. To continue our training, we are going to be changing modules at this time, and we are going to talk about electronic expansion valves. I don't know if you have already come across these valves, but so that you can recognize them visually, they are like this. They are not only solenoid valves that open and close, but they are expansion valves that are constantly varying the flow of refrigerant that they let pass through. So, the errors they present, the measurements we are going to make, how they work, we are going to be analyzing it now. For those who still don't know, they didn't realize, this expansion valve replaces the capillary in conventional equipment. In inverters as well, more conventional or of lower quality, there is still capillary, but in the best ones we already have expansion valves, such as in Carrier or Myers. How does this valve work? Well, but in you who have 6 connection cables to the board, these 6 connection cables are basically as follows. Look, we have 2 cables that are negative 12 volts, and then what we have are 4 more cables that are going to be injecting the positives, and with that they are going to be closing the circuit in the coils. One moment, I'll find you a diagram with which we will understand it perfectly. Basically, they are 4 coils. They are 4 coils that are energized with 12 volts through pulses, and they are going to close circuits. For example, we will be injecting electricity through the brown and red. And when we want to rotate each of these coils, the board will give pulses to the white cable, the orange cable, the blue cable, or the yellow cable. As it gives pulses, it is causing electrons to circulate through one after the other, and after the other. It works like a small stepper motor. It works exactly the same as the air oscillating motors of the previous unit. Do you remember this air oscillating motor? In the same way these expansion valves work, allowing the board to control the exact position in which the rotor is located. These usually had 5, and this is because one of the 2 was shared. Red was also brown. Red and brown were together, which would be the same in the end. But in the valve to have more control yet, it has 1 more, that is 6. How do we understand its operation? Understand that it does it through pulses. That is, the board does not send a constant 12-volt signal, it sends pulses. And when it sends pulses, it makes the motor go around, very fast pulses. That is why, if we inject 12 volts directly and fluids and clean, it may be that this component burns out. If the valve does not work, the first thing we will do is test the electrical or electronic part, which is composed, obviously, of the wires and also of the winding that is placed on the top. If you look closely, it has a way to turn and remove, very similar to how we removed the coil of the hot-cold valve of the 4-way valve. It is removed, and we can remove the electrical or electronic part. This electrical or electronic part has a simple measurement that we can do, and it is through ohms. If we control and measure, for example, between white and red, obviously we are measuring the winding of this coil. Then between white and red it will give us a result of 43 ohms. These ohm results are similar in all valves. They are not exactly like that, but they are very similar. Now, if I control between yellow and blue, look that I am traveling 2 coils. In that case, between yellow and blue, the resistance will be double, 85 ohms. And so with all, between orange and red, between brown and blue, between brown and yellow, and between orange and white. To measure double In all measurements, I will have to have results like these that will be given by the number of coils that I am controlling. Well, this is the main way to be able to measure it, and it is an electrical/electronic way without voltage. Let's watch a short video where it shows us the measurement we did. Here we are seeing how we do that measurement. Look, we have 90.8 or 9 ohms. In another one, there are 45.6 ohms in one of the coils. There is nothing there. We also have to control between the ones that are opposite to know that we do not have any false measurement. That is, the coils may also be short-circuited, so we have to measure between the ones that are separated to see that the travel is open line. In the next measurement, we have another coil. And that's how we keep going through all of them. I am letting you know that the link to these files is in the video description so you can download them. You saw that the values will be approximate. A moment ago, in the measurement we made on that carrier valve, we were talking about having 90 at this point, and here we had 45, approximate to this example. Very well, this with respect to the electrical/electronic part of the expansion valve. But, do we have another part in the valve? Yes, we have the mechanical part that lets in and out the refrigerant, and that is where we have to be more careful, or rather, it is the most complicated to repair, because to replace that valve you have to solder and unsolder. So, let's say that we have a problem or a defect in the mechanical part of that valve, that is, the part that allows the refrigerant to enter and exit. How are we going to detect the problem? Since the equipment will not mark us an error of electronic expansion valve. We will not have that error in the equipment. In reality, detecting this error in an inverter unit depends 100% on your knowledge and understanding of how a unit works. Think that if this valve is staying closed too much, the internal and external pressures will vary, as well as the discharge temperatures of the compressor and the equipment will mark an error, for example, excessive overheating, excessive supercooling, excess compressor discharge temperature. They are rare errors that usually have to do with the refrigerant, up to lack of refrigerant. All of these errors can be indicating a defective expansion valve. Of course, this depends solely and exclusively on us to be able to detect that error. Some errors are excessive overheating, excessive supercooling, excessive compressor temperature, and lack of refrigerant. They are errors if the valve opens or closes too much. But we have a way to test the electronic part of the valve. It would be to disassemble and remove this part of the valve, the electrical part. And inside it, we can place a screwdriver. When placing a screwdriver and allowing the valve to activate by turning on the motor, or with a universal board, that screwdriver will move because it will stick to the different walls of the valve. This is an electronic or electrical way to test it. Energizing the valve, we place the screwdriver inside and it has to stick to the edges. Now, if we see that the entire electrical part works well but still has an error, temperature, or strange pressure, Well, it is time to think that the problem may be here, in the mechanical part. A quick way to see if this turn works or not is when we energize inverter units. In general, the valve makes a complete opening and closes again. So, at the time of energizing, we have to hear the noise of the electronic valve rotating, which would indicate that it is in good condition. We have to hear the noise of the opening and closing. It sounds like a knocking noise, something like that to understand it. If we still notice that there are defects, something that we can do in some cases, it works in others, is with a magnet, with a strong magnet, perhaps those that are used to recover fallen screws. Without the electronic part in place, with that magnet, move it around the valve and see if the valve rotates, activates, or does anything. Move it around the valve to see what happens. Because it is very sensitive to the small magnetization, it rotates or moves. So you have to move it around and see what happens. Sometimes it can open a little and see how the refrigerant pressures vary. Now, if all this still does not work, well, we have to be thinking of replacing the electronic expansion valve. In that case, what we will be doing is applying the following tips. You saw that the valve has the electronic part and the welded part. And you will see here that the space from the weld to the valve is very short. What is the problem? The problem is that in order to solder this valve, we have to completely wrap it, of course, without the electronic part connected because we are going to remove it, but the mechanical part we have to wrap completely with a damp cloth so that it does not overheat. That damp cloth must be made of cotton and be constantly wet. In fact, if you have an assistant who is sprinkling water on it while you are soldering at these points. The problem is that the position of the valve is always like this, standing, and when you wrap it with the cloth, it drips and cools the weld, which makes it take longer to solder and the heat reaches the valve and can damage it. A tip from me is, originally we have it in this position, and at this point we have to solder. And here the air conditioner continues, these pipes will continue and will go around below and go to different parts of the piping. What can you do instead of soldering at these points? Well, when you buy the expansion valve, you can place it on its side where you can wrap it better with a cloth with water and solder some longer pipe sections, and leave your expansion valve with longer pipe sections. So, what will you achieve? Well, when you are going to place it in the equipment, the welding you will do on the equipment will already be much lower, because you will cut the pipes here, because your expansion valve already has longer sections in place. Unfortunately, they come with very short pipes that make it quite difficult for us, but if you take the time to add these sections, you will surely find it much easier to solder because you will be able to wrap it with a damp cloth without problem, and you will be away from the welding area, which is this. A very important detail is that all this is always welded with an atmosphere of extra dry nitrogen. I don't know if you know or not what this is, but all this has to be welded with a certain amount of nitrogen passing through the pipe constantly to prevent the formation of the common slag when we weld. When we weld a pipe, what always happens is that at the weld point, we clearly see that a certain slag or residues are formed that are the fault of the burning of oxygen together with moisture. The same thing happens inside. Now, by sending a constant atmosphere of extra dry nitrogen during welding, we prevent the formation of that slag inside. And so we have a clean weld inside, which then, when the refrigerant is circulating, will not drag those residues inside and clog another component such as the expansion valve itself. So, always with the atmosphere of extra dry nitrogen. Later, I might leave a video explaining this. It is not necessary to explain it in inverter refrigeration because it is not specifically about inverter refrigeration. In reality, it always had to be like this, but in inverter it is more than necessary because we have equipment with 410, with 32 which are more delicate gases of which we have to be careful of all those residues that remain inside the pipe. Well, this is what has to do with electronic expansion valves. I will briefly show on the board how this valve is connected. Here we have a board with a slot for the expansion valve. In fact, it doesn't have the slot, it just has the slot because this model didn't come with it, but look at the following. In this point, we have an electronic expansion valve, which connects to these 6 terminals. And these 6 terminals go to a driver, which is a series of electronic valves that act as communication between the processor and the valve. That is, the processor does not directly control the 12 volts of the valve, but does so through a driver, a series of pass valves. We can say that it is something like a small IPM. And they give the valve pulses as they want. There are several electronic pass valves that allow the 12 volts to pass directly, commanded by a much lower voltage that comes from the microprocessor. In this model we do not have it installed because this model does not have it, so neither the socket to connect the valve nor the driver is installed. But that's how it's controlled. We could measure the pulse emitted by the board with an oscilloscope in case it were the board that brings it, but well, this area does not usually fail. Most of the failures are in the valve itself. And one more detail to keep in mind that I mentioned, and then we will see. To be able to control an expansion valve correctly, you will need a universal board. With a universal board, we also have the possibility of testing electronic expansion valves. So that's where we get to the topic of expansion valves. Next, we will continue talking in this part of the course about temperature sensors. We will be seeing many details about the sensors, their resistance values. We will be understanding how they work in a conventional and inverter system. We will also be understanding how an electronic board can make these be part of the electronic circuit. That is, part of the electronic board influences the operation of temperature sensors. Something that can be damaged in this system is not only the sensors, but also the circuit involved in temperature measurement inside the electronic board. So we will explain all that, but to start we will be seeing or understanding how these temperature sensors work. It is key to understand how they work, and that is what I will apply. These temperature sensors are NTC. That is, their temperature coefficient is negative. What does it mean? That it is exactly the opposite of its operation in resistance. To understand it better, we will make a small graph in which the variable below is the temperature in degrees Celsius, and the vertical variable is the resistance in ohms. As the temperature increases, the resistance decreases. These temperature sensors are small NTC ceramics because their reaction to temperature is to reduce resistance. It has been reached as a kind of agreement between manufacturers, and it has been said that to name a sensor, we will say what value of resistance it maintains at 25 degrees Celsius. To name a certain sensor, we will use as a reference its resistance value at 25 degrees Celsius. So you are finding, for example, 10 kilo ohm sensors on the market. What does it mean? That at 25 degrees, that sensor has a resistance of 10 kilo ohms. What do we mean by resistance? I will do a small measurement to understand and know what it is about. For those who have never done it, we grab the multimeter, put it in resistance position, and simply measure the sensor uninstalled from the electronic board. Well, here we have a 10K sensor. Why do 8K appear at this point? Because evidently we have a temperature greater than 25 degrees here. As its coefficient with the temperature is negative, this sensor evidently, as all sensors, has a graph that looks like this, and we will have 8 kilo ohms when the temperature is a little higher. In this place, it should be about 28 degrees Celsius now, so we have 8K of resistance. Remember the word NTC. This will help us understand that if we increase the temperature, the resistance decreases. It is negative, it is the opposite. Now, PTCs are different. This is only for informational purposes. It is not relevant in the case of inverters. PTCs are ceramics that are used, for example, to start refrigerator motors whose coefficient with the temperature is positive. What does this mean? As the temperature increases, the resistance increases. A PTC, for example those that are used to start refrigerators at 25 degrees, is approximately at 20 ohms. There it is, more or less you can see it. So, when the temperature increases, the resistance increases. The difference between PTCs and NTCs is that they are positive in relation to temperature, that is, they increase and continue to increase. PTCs are often used as starting devices because their line is not predictable. That is, if it heats up faster, the line will be like this. If it heats up slower, the line will be like this. And when it cools down, it will be different. The same ceramic can find in different temperatures several resistance ranges because its working line is not predictable. So it is used as a starting device. The temperature increases, the resistance increases, and the starting coil detaches, as is the case with refrigerators. NTCs are predictable, which is why they are used for precision temperature measurement, and that is why NTCs are the ones we will always find in areas where temperatures need to be measured. Okay, this is how NTC ceramic sensors work. What values do each ceramic have? We can't see it from the outside because it's actually a package. The ceramic is inside. The ceramic looks similar to the one I'm going to show in an image so you know what it looks like inside. And also see why you won't have the value on this component because this is not the sensor. The sensor is inside. Something like this is what these small ceramics look like. An important detail to keep in mind, there are many values. If a manufacturer tells us that this sensor is 10K, here he is indicating that it is 10K at 25 degrees. But you will also find them, as many already know, you will also be finding them, for example, always talking about 25 degrees. The value I say in kilo ohms or less is the reference temperature value at 25 degrees. So far you have found 5K in conventional equipment, 10K, 15K, and 20K. And in refrigerators, for example, the Whirlpool brand has a 2.7K sensor, others also use 5K. Well, what does it mean when a manufacturer or a spare parts seller tells us that this sensor is 15K? Remember that he is telling us that it maintains this value at 25 degrees. It is not that it is always 10K. In fact, we just saw it with this sensor. Right now it has 8 kilo ohms of resistance because we have more than 25 degrees. It reacted to the temperature, which is fine, it is correct. Something else that we also need to understand is that we need different values of sensors depending on where we are going to place them. Let me tell you the following. When we talk about 5, 10K, The letter K represents a multiplication by 1000, so in reality this sensor is 10,000 ohms. Temperature sensors on electronic boards have high resistance values. They are not 10, 100 ohms. No, we are talking about 2,700 ohms, 5,000 or 10,000, 15,000, 20,000. Okay, this is how temperature sensors work. I will explain below their application in air conditioning systems and also in inverter systems. So, in inverter technology, we will be finding different sensor values because we have to measure temperature in different points. In an inverter unit, we will be measuring temperature at points such as the indoor ambient temperature. We found this not only in inverter, but also in conventional. I'll see if we can go down and make a small box to understand it. Indoor ambient temperature. So far we found it in conventional and in inverter. Indoor pipe temperature. As they told you, many overheating temperatures, although it is also subcooling, depending on whether the unit is hot-cold or cold. We'll just call it indoor pipe temperature. In this case, we also have it in conventional and inverter. Outdoor pipe temperature. In this case, in inverter, we will always find it. In conventional, we will find it, but we will put an asterisk. The asterisk will tell us that some will not be found in all conventional units, and I think you know this. In inverter, in addition, we will have outdoor ambient temperature. In this case, we will always find it. Sorry, I made a mistake. We will always find it in inverter. In conventional, we will no longer find it. Finally, compressor discharge temperature. This will not be found in conventional either, and will always be found in inverter. This would be a small box made quickly so that you can visualize and understand what you will find in inverter and conventional. So, when in conventional you will be finding 2 to 3 sensors, in inverter you will find 5. You will always find 5 temperature sensors. All these temperature sensors can have a similar travel value because they are handling temperatures from 4 degrees to 50, 60 approximately within all ambient temperatures. Although, of course, it does not make 60 degrees in many parts of the world, but if they are temperatures close to ambient temperature, then the values of these sensors are usually similar. For example, they usually place 5K or 10K, although some manufacturers vary the values, but approximately they are like this and they are all similar. Now I will explain why in a moment, but the compressor discharge temperature has to have a temperature sensor with a higher value. And that is why in inverter now, additionally, you will find sensors of 38K, 40, 56, or 200K. Yes, in inverter we will find one of the sensors that will have a much higher value. Why does this happen? Don't worry, we'll understand. Let's go back to the graph where we were talking about sensors and their operation. The compressor discharge temperature is a temperature that the equipment measures precisely at the compressor discharge. That is, it has the ability to measure the temperature of the compressor itself, since that sensor is so close to the outlet that the temperature in that pipe is similar or almost equal to that temperature of the compressor itself, and therefore, of the oil and the entire casing. Here we can see it. The outlet of the compressor pipe makes a small turn, and there we already have the temperature sensor. This is the sensor we are talking about. This is going to be measuring temperatures of 80 degrees and more. Why does it have to be more valuable than the rest? Well, because when it is approximately that temperature at 80 degrees Celsius, if we place a sensor of 5K, 15 or 20, it will be in a range of the temperature sensor in a resistance range that will be so low that for the plaquette that measures that temperature, or that value, in reality it measures it with a small voltage of 5 or 1.2 volts, it will be a value so low, for example, of 100 ohms, that it will not be able to understand it. So, in this place where such high values are measured, what does the manufacturer do? Well, the manufacturer places sensors that are now not 10K, but now 200. Not all of them have 200, some 38, 40, depending on the manufacturer of the plaquette, but let's say they use 200, as is the case with some very well-known brands. So, at the point where it reaches 80, 90 degrees, which is the moment when the plaquette wants to know what temperature the compressor is at, there is a value in ohms of, for example, 5 kilo ohms. It is a value in ohms that the plaquette can understand. And that serves us, the plaquette needs it. So that you understand, in places where high temperatures are measured, and I refer to high temperatures as passing quite ambient temperature, such as 80, 90 to 100 degrees, we are going to place sensors of high ohm value, because the value in ohms is always taken as a reference at 25 degrees. Now, in places where low temperatures are measured, we will have low ohms, because when the temperature drops, the resistance will go up, and it will be easier for the plaquette to understand it, such as, for example, in a freezer of certain brands such as Whirlpool. In these freezers of refrigerators we find sensors of low resistance, so that when the temperature drops and is found at a point that the plaquette wants to understand it, the value in ohms is appropriate for that electronic circuit to understand it, perhaps 15 to 20 kilo ohms, approximately. I'm going to erase this and we'll continue with our graph. This would be the case of a freezer, and at this point I'm going to find 20 kilo ohms. These electronic plaquettes always want to understand values from 3 to 20 kilo ohms. That is why, if they want to measure temperatures in places with a lot of heat, they have to put higher sensors, so that when they are in the range that matters to us, the value in ohms or travel is the appropriate one. And the same vice versa, if we want to measure very low temperatures, we put low ohms, so that when the temperature we are interested in is reached, we have the appropriate ohmage so that the plaquette can understand it. For that reason, we are going to find a sensor and inverter that will be of more resistance. But you have to learn where they are, you have to see them visually and understand how they work on the electronic board and what errors they present. And we will see that below. Okay, to understand how a temperature sensor works inside the board, we're going to use a small sample diagram. This is a simple diagram that many boards use, but there are more complex ones, and we'll be seeing some of them live soon. So, how does a temperature sensor work in a diagram? What the microprocessor, actually, the integrated circuit, will feel is a voltage variation depending on the resistance of that sensor. In the sample circuit, this represents the NTC, the thermistor or temperature sensor, or NTC variable resistance. So, as this temperature varies, the resistance varies and the resulting voltage that enters the integrated circuit is different. 5 volts positive are injected directly into the sensor, and the negative is injected. This is the GND, the negative, through a precision resistor. It is not a common resistor. And through it, a voltage of equalization is reached, and the resulting voltage goes to the integrated circuit. As a result, as this resistance varies, the voltage that enters the microprocessor also varies. If we inject 5 volts into the sensor, approximately 2.3 to 2.8 volts will be injected into that integrated circuit, and through this variation, it understands what temperature it is. Of course, it understands it in a much more accurate way, 2.340, 2.565, we talk in the range of millivolts, so the microprocessor understands it. Something that is not drawn in this diagram, which you will generally find, is a capacitor that is placed between the negative and the positive. Any error in the tracks, capacitors, or resistors in the temperature measurement circuit can cause the integrated circuit to mark a sensor error, even if the sensor is in good condition. That is why it is important to pay attention to that detail, as it may be that it shows us a temperature error or a temperature sensor error, but that the problem is not the sensor itself. That is why technicians often replace the sensor, but continue to have problems, because in reality there is another problem inside the board. Of course, for that they need to have a little knowledge of electronics to identify it and solve it. Well, this is a normal circuit. Let's see then this same thing, but on an electronic board. Let's take a look at the temperature sensor circuit on an electronic board right now. Well, let's zoom in a bit on this part of the board where we have the connection to the NTC sensors. At this point, we can already move some components that we will identify as, for example, precision resistors, and we also have a capacitor very close by. Let's turn this board over and let's see what we find on the other side or understand how this board measures temperature. We get closer and we have the following. These are the points where we have the temperature sensor placed. If you look closely, these sensors are being powered by a positive. This is the positive track. There is a capacitor between the positive and the negative. This white track is the negative. And here we have the capacitor we mentioned. Of course, it has to be in good condition for the temperature measurement through these sensors to be working properly. For the integrated circuit to understand, all of these components must be in good condition. If we continue observing a little more, you will see that we find, at the output of each sensor, precision resistors to the negative that are the ones we just saw from the other side. Of course, we have to corroborate its operation. We have to corroborate that they are exactly in the value they have according to their color bands. They are precision resistors, that's why they are green. And if we look from one end of the sensor, from the same one where the precision resistor comes out, we have some very thin tracks. They are these two, the ones for the two sensors. If we follow its path, well, towards the negative it goes back through some small lens-shaped capacitors that must not be in short circuit. We keep going, they were these two, and look that we reach 2 points of the microprocessor. This is where a resulting voltage is delivered which the microprocessor understands and can know what temperature that sensor is at. Very important detail, the microprocessor will only report a sensor error when we see an error message on the equipment's display. This only occurs when the voltage arriving at the microprocessor is 0 volts or 5 volts. Therefore, if the sensor is devalued, if the resistor is devalued, or if there is any other strange problem that is not, for example, a direct track cut, the voltage that will arrive will be strange. The microprocessor will understand that this is a temperature. For example, the microprocessor may understand that the room is 0 degrees due to an error in some value. Then, you turn on the air conditioner and the unit will not turn on, of course, because it thinks it is already cold. Therefore, pay attention to that detail. We do not absolutely trust the errors that the equipment reports. If we see a unit that does not turn on the compressor even though everything is properly configured, there may be a devaluation in the sensors, which causes the microprocessor to misunderstand the temperature. That is why that detail is important. Understand that, if 0 or 5 volts arrive here, the microprocessor will understand that there is an error. For example, a short-circuited sensor, 5 volts, sensor error. A temperature sensor, an open NTC, 0 volts, there is also another problem. Or a cut track, 0 volts, there is also a problem. The microprocessor understands that, but when there is devaluation, the microprocessor does not understand that and will not produce a strange effect, which perhaps will never blame a sensor or the circuit, and it is so the problem. So, pay attention to that detail. Therefore, remember that important data. If we have 0 or 5 volts, we will have the error. When there is an intermediate voltage, it is good, the temperature is being measured, but it may be some problem in some of the devalued components. Very well, how can we know if the components are in good condition? One way is by measuring the voltage that is emitted to the sensor. We will also do this with a powered board. But for now, you can measure the tracks, check them, measure the resistors, and the capacitors. Now we will continue with our topic of sensors. We will see a small track tracing on an electronic board of an LG inverter unit. Here we have the position of the sensors. Please observe the components that work alongside the sensor. In this case, the components are much smaller than the boards we were previously seeing. Well, you have to follow the tracks in a more delicate, patient, and attentive way to be able to observe. Observe, near the temperature sensor we have certain capacitors and resistors, and several tracks that directly lead us to the microprocessor. All of these are components to review in cases of temperature sensor error. To review these components, sometimes you will need to have some kind of magnifying glass or microscope. In this case, I am looking through the camera screen, but if I look with my own eyes, it will even be quite difficult for me. I see it better as you are seeing it through the camera. At a glance, these numbers are illegible. And through the camera, you can see that it has a resistance of 12.1 K. Well, very well, with patience, review these tracks and these temperature sensors. And we will move on to a slightly more complex board. I will show you a board from a unit, as it is commonly called, Chinese. Let's see that the location of the sensors that is at this point also has very close to those delicate components. And the peculiarity of these boards is that they are double-sided, that is, they have printed tracks on both sides. Here we can see some of those components that have a direct relationship with temperature measurement. The microprocessor is a little further away. Let's see what we have on the other side. Look, here we have a track. The tracks of the sensors that use components that are on the other side. Here is the tracking. They cross to the other side through those perforations. And on the other side, we are already almost at the microprocessor. There it is. With patience, we place the tester in continuity and follow the tracks when we have temperature sensor errors. With a lot of patience, the resolutions are achieved. And we do it this way. Very well, we will do more tests, but now measuring voltage in the sensors. We will build a board in the next video. And we will measure some of the voltages we were talking about. Now that we have this board energized, let's test the voltage on the temperature sensors. We will put the multimeter in direct current reading, and we will measure the different points of sensor energization. Let's try. Here we have 5 volts. It is not clear due to the reflection of the light. Let's wait a bit. Now yes, 5 volts. Well, we are powering the sensors with 5 volts. Let's see if this other one also powers with 5 volts. Let's connect the temperature sensor and see what happens to that voltage. Two volts almost, yes, because it is quite hot here, but if we cool it down, if we could lower the temperature, we will see how that voltage increases. Let's heat it up a bit to see how the voltage varies. There it is. I'm heating it up. We are seeing how that voltage drops significantly. If we place a temperature sensor of a resistance that does not correspond, in general we will have very strange voltages. If we place temperature sensors that do not correspond to the resistance that the manufacturer has put on the board, in general the results here will be 0.5 or 4.5 volts. Since we have the correct sensor, the resulting voltage of the 5 volts that are emitted when we connect the sensor, our resulting voltage is between 1.5 and 4. That tells us that we are placing the correct sensor and that it is working well. Voltages of 0.5 or voltages of 4.5 already indicate a devalued sensor or that it is not of the capacity that corresponds to that electronic board. Keep in mind that we can do the same measurement and control which sensor goes in each unit. A detail that I also think you need to keep in mind is that not only do the boards energize the sensors with 5 volts, we have electronic boards that energize with 1.2 volts, the ones that are a bit more computerized, such as the case of the other board that we have as a model here. These electronic boards energize the sensors with a much lower voltage, approximately 1.2 volts. The resulting voltage when connecting the sensor is approximately 0.3 to 1 volt. If we find values very close to 0 or very close to the voltage without the sensor connected, then it may be that we are talking about some error or a sensor that does not correspond to that equipment. Very good. This measurement that we will be doing to see if the circuit on the board is working properly, but this measurement is already with voltage. In this video, we will be talking about the remote control and also the receiver of the same on an electronic board. The remote control works in a very similar way to an optocoupler. An optocoupler has a small LED and a small photodetector inside it. In this case, it is exactly the same, only that the LED is in our hand and the photodetector is located on the electronic board or on the display, or on a small separate board. In this case, we have it together with the display. How does it send the signal? Well, it does it through pulses. These pulses are very fast in time and we only see a light if we look with the camera of a phone, for example how we are going to see now pointing with a phone. And there we can see a slight blinking. Well, let's try with another different control. There we can see just the blinking. This blinking is telling us that the remote control is working properly. In case it is damaged, what we can do is replace this LED. In reality, what breaks the most in remote controls is this LED due to falls. It is rare that it fails for anything other than falls, unless water or dirt gets into it. If you observe inside the control, this LED usually has long wires to connect it to the board. This is to cushion the blows that these devices constantly have. But they also get damaged sometimes. So, we have to replace it. In case this LED fails, it is easily replaced by another infrared LED. But it is not only the only failure we have in remote control and its reception. It is also possible that we have a failure in the receiver of this control. One detail I want to mention is that iPhone phone cameras do not show infrared light. These phones are made in a way that the screen does not show the spectrum that is invisible to the human eye. In this way, they offer a better image quality. Therefore, let's keep that detail in mind. With iPhone phones, we will not be able to see the light of the remote control. We may think that the control is having problems, but it is not because those phones do not show that light spectrum. So, how do we control the receiver? One simple way to do this is to go to the 7805 on the board or to the 5-volt output and make continuity between the negative and any of the 3 pins of the receiver. There it is. There we were able to identify that the middle one appears less than 1 ohm. So, that is the negative power supply of the receiver. In case we have to replace it, we have to look for one of the same type. The main thing is that the terminals match, because if not, we have to make a great adaptation on the board. The main thing is that the terminals match, both the negative and its BCC power supply and its signal output. To see the BCC power supply, what we are going to do is place it on the positive side of the output of the 7805 and also make continuity. It will not be a direct continuity, but it will be a low resistance. Here we have 329 ohms. Here we can identify the input power of this receiver, and on the other side we have the signal output. So, how are we going to do to control its state? We are going to power the receiver along with the entire board. So, to control the operation of the receiver of this control, the first thing we will do, as we saw in the previous video, is to corroborate which is the negative and which is the positive of the sensor. And we were able to identify that already. Next, with the oscilloscope, we will detect between the negative and the output. So, we turn on the oscilloscope, place the test lead in 1x, also informed that we will work with 1x, and only need to set 5 volts, or we can even use 2 volts, since on screen we will have 8 on each side. Then, we place the positive on the signal output and the negative. We will place this one on the negative. Remember that the right one was the positive. Now I am placing it on the left, which is the signal output, and the negative we will place it on the negative, but for that we will take advantage of the other side of the sensor. Very well, carefully not to short circuit. As we see on the screen of the oscilloscope, we see a voltage of 5 volts. This voltage must vary as we illuminate that receiver with any remote control. It doesn't matter if it's not from the air conditioner, all signals are received and transmitted, but not all signals are understood by the microprocessor. So we press the volume button on a TV. The TV volume button gives a constant pulse that, in general, air conditioner keys do not give, since they prefer that we press them one at a time. The TV volume always gives a constant light emission, and there we can see how that pulse is drawn. Let's zoom out and we can see better. There it is, there we can see the pulse. Let's give it less zoom. And see that we can see how it is being drawn. I don't press, I pressed, I hold down, I let go. Now I'm going to press the power button. And the signal is always being received. Depending on what we ask the team, they are not always understood. For example, in this case, the team is showing an error, so even though I raise and lower the temperature, the team does not react and does not raise and lower the temperature. But the receiver of the remote control is receiving the signal. In fact, even if I press the power button on my TV, the signal is still received, and the receiver transmits it to the microprocessor, but the microprocessor does not understand it. But this tells us that the receiver is working well. Remember, between G and D, or negative and S, there the voltage already fell because I disconnected it. So this is how we can test both the remote control and the receiver. Very well, to continue with our training, we are going to touch on a very interesting topic in inverter technology, which is the bidirectional communication signal between indoor and outdoor units. It is a very interesting topic because, in addition to being damaged quite a bit, it is a complex topic for most technicians. It is difficult for them to understand it really, but we are going to give explanations as always simple, clear and sharp so that you can perfectly understand how these communication signal circuits work. As a sample and to be able to explain it and understand it, we have an indoor and an outdoor plaque with its reactor, which it needs to be able to turn on and energize. Here we have the electrical interconnection, line, neutral, and signal. They are the only three cables we have. We don't have the earth placed so as not to confuse us, nor do we even have the display placed. To understand how this works, first of all we are going to do some measurements and then we are going to be explaining in graphs how it works, what it does to be able to communicate from one side to the other. The first thing you will do, when repairing or checking inverter air conditioners, when you have a communication error, is to energize the indoor or outdoor unit, the one that is energized, and to be doing some measurements on the communication cable. How do we do it? With a simple multimeter. We place the multimeter in direct current and measure between the N cable and the S cable, and we will observe what appears on the screen. Preferably, place the black cable in N and the red cable in S or C of communication. Well, now we don't have any voltage. It would be perfect. Let's start the team. Now yes, we have to find the voltages that interest us. Observe, please hear the number I have on the multimeter, 15 volts, 4, 22, 15. 2, 22, 15. 4, 22, 15. 2, 20, 15. 4, 22, 15. That data is important. That variation is important. Do you notice that there is an intermediate voltage? 15 goes down and goes up. It goes to 2, it goes to 22, to 2 and to 22, and goes back to 15. That's how an indoor unit communicates with an outdoor unit. When the voltage drops, one communicates with the other, and when the voltage rises, the other communicates with the first. That's the way they have to communicate with each other. That's exactly what we're going to see with the oscilloscope. There are units that communicate up to 50 volts, so we have to activate 10x. Tell the multimeter that we're going to use 10x and place the negative test lead on N and the positive lead, or the positive test tip on S. We're going to zoom out so we can see what's on the screen. We'll increase the voltage a bit so that 40 volts appear on the screen. Okay, there we have the same thing we saw with the multimeter. It stays at 15, goes down to almost 0, to 22, 24, and goes back to 15, 0, 22, 24, 15, 0, 24, 15. And it's about every 3 or 4 seconds that the communication takes place. Approximately every 3 or 4 seconds, the units communicate to inform each other what is happening in one and the other. Well, that's how they communicate. In fact, if the communication fails, the voltage will not only go up or only go down, which would indicate a failure in one of the two units. And if this variation does not occur directly, it may be a problem with the processor, which is responsible for generating these pulses. What you are seeing here is not arbitrary. Well, yes, it is arbitrary because the manufacturer did it in his own way, but they are not meaningless pulses. The units understand each other, and there are many intermediate pulses that, if you look closely, change over time. That's how they communicate. But how does this communication take place? What parts are involved? What components do we find on the boards that help one communicate with the other? Well, we'll see that next, in the next video. Well, the communication signal from indoor to outdoor unit is produced through opto-couplers. Why? Because we need long cables, which means that they will handle high voltages. And since the communication has to go from one microprocessor to another, to make that communication between high voltages and the processors, we need opto-couplers that divide the area and do not produce any damage in case of a short circuit in the communication cable. That is why you will always find two opto-couplers very close to the communication signal, placed just in the opposite position of each other. Notice that here we have a LED on the right, and on the other side of the opto-coupler we have it on the left. There is always some voltage reduction resistor, diodes to prevent the flow of electrons from returning in the direction we do not want, and some filter capacitors. On this side we also have resistance, capacitor, and another diode. And notice that on the other side of the opto-couplers we already have the tracks that will take us directly to the most complex part of the circuit, which eventually leads us to the microprocessor. The microprocessor communicates with another microprocessor, indoor and outdoor unit, through those opto-couplers. This is the indoor unit. If the communication circuit fails, we have to check these opto-couplers, these diodes, and these resistors, as you already know, and replace them. And the outdoor unit is exactly the same. Only that the outdoor unit is usually a bit more complex. Notice that here we have the pin where the communication cable is placed. We have some diodes, resistors, and on the other side we already have the opto-couplers we were talking about. They are mounted in an SMD way, they are mounted superficially, their terminals do not pass through to the other side. But you can use the same opto-couplers. What you have to do is cut the thinner terminals, and you can place them at these points, replacing the originals if they are damaged. They are a little smaller, but it does not matter. You can place, for example, the PC817. In the case of the diodes, you need to check their value, the resistors too, and the capacitors that are not in a short circuit. Well, this is how we are going to test, measure, and replace the components that are involved in the communication. What else do we have to do? Very important, follow the tracks. We always say the same thing. Follow the tracks, always, no matter how long they are. Look at this case. We cross jumpers. We go around here outside. Look at the turn we are making. And here we will only be reaching the microprocessors. So, go over the tracks, follow the tracks, because they are cut and the communication stops. And we replace components and even want to replace the board, but we forgot to follow the tracks. It is like a cut cable. Please, let's follow the tracks in this part of the circuit. I will also show you another board from another brand so you can see how the components dedicated to communication are. Here we have a slightly more complex board. Here we have the red communication cable, filtering coils, a PTC, which is a small ceramic that opens with excess temperature, which you know, because we were talking in the sensor section, resistor, filtering capacitors, also a polyester capacitor, 2 diodes, and 2 opto-couplers. The same in this case, we also have tracks that go from the opto-couplers to the microprocessor. Let's see the indoor board of the same model. Communication cable, PTC, resistor, 2 diodes, 1 Zener diode, 3 resistors, capacitors, and opto-couplers. Main component, always one on one side and the other on the other. Here we see the mark at point 1 and the mark at point 1. These are the components responsible for communication. If you find any problems, you need to check all of these pieces. I will show you a measurement on a working team as you would do at the customer's home. We will measure with the multimeter between S and N. Directly from the outside, we can see if the communication is working or not. We have the same values that we saw just now on the test bench: 15, 4, 20, 15, 15, 4, 20, 15, and constantly a voltage that goes up and down, up and down. Always test between N and S. Well, these are the components that we will find in the signal communication part. In the next video, I will explain some more technical data and to keep in mind about these communication circuits. For this part, we need to go back to our famous drawings, diagrams. I will explain how this signal cable works. This cable is constantly powered by the line and neutral. We will use colors that we can understand better. We will use the color blue to talk about the neutral. And what else will we find? The famous opto-couplers. We go to the indoor unit. These are a rather rustic diagram, but that's how it works, and that's how you're going to understand it well and know why the data appears as it appears, and also understand how important it is that the parts are in good condition. Now I'll explain what I mean. What we are drawing here are the opto-couplers, with the 4 opto-couplers. 1 LED on one side, 1 receiver on the other. LED receiver, LED receiver. We will write or draw and read the line. Perfect. The electrons will always enter from the neutral side, and we will find diodes that will let us only pass one way, because this is alternating current. Each time I make a voltage derivation through the opto-coupler, that voltage will go away, and this light will turn off. What does that mean? When the microprocessor, the integrated circuit of the outdoor unit, turns on the LED, the electrons go away, and this LED turns off, producing a pulse. Which, on the other side, in the circuit that works with 5V, this is from the indoor unit, the circuit will understand. The outdoor unit turns on the LED, the electrons are derived, the signal cable loses voltage, the LED of the indoor unit turns off, and the receiver receives that pulse, and the microprocessor, integrated circuit, understands it. This is how the outdoor unit communicates with the indoor unit. If we want to communicate the other way, from the indoor unit to the outdoor unit, what does it do? Well, the integrated circuit turns on this LED. The electrons are derived through here. This LED turns off, and from the outdoor unit, with the 5 volts, that pulse is produced and the microprocessor understands it. This happens at different times. First they give time to one, then to another, and wait. One, another, and wait. One, another, and wait. And that is what we saw recently in the voltage that appeared to us over time. One, another, and wait. One, another, and wait. And this is how communication is produced. Units that work with higher voltages, that work between 30 and 50 volts, do so that if the cable is slightly defective, the cable does not cause any problems in communication. If we talk about a voltage of 3, the cable has to be in very good condition to work well. What are the most common causes of communication failures? For example, a cable in poor condition, with splices or joints. The S cable must be in perfect condition. And if you notice that there is an error in the communication, but that voltage variation is present, it may be that even though there is that pulse, the units are not understanding each other. Something you can do is, say this is the S terminal. You can add an extra cable, apart from the signal cable that it already has. And try to do it outside, away from the L and N cables. It is known that this generates a magnetism around the cable due to the high amperage consumed by the compressors. So try to pass a separate cable, a 1.5 mm cable, a section of 1.5 or 2 mm. Do not use coaxial cable, do not use anything strange, only copper cable. Make sure it is in good condition. Use a 1.5 or 2 mm copper cable in section, that is, thickness, square millimeters. This is a great test that solves many communication problems. Replacing or adding that signal cable is sometimes not the easiest thing, because passing a cable from the indoor unit to the outdoor unit is not easy. But sometimes it is the solution. Perfect. This is what has to do with the communication signal. This is how it is checked, how it is solved, how it is tested. Following tracks with patience, making these measurements, and you will detect any of those problems. One more thing to keep in mind, when you find a terminal with F1 and F2 cables, and use 2 cables to communicate, in general these units, which are usually the larger Samsung units, are using a different communication protocol. What does this mean? That communication is through a previously established coding. This means that the integrated circuits are communicating through a protocol, that is, they are communicating through a language established by another person. Different from the signal cable we talked about today, it is designed by each manufacturer with that pulse. In this case it is more complex because if the communication signal fails, it is not usually the cable, because the cable is included. In addition, they are very complex signals, very deep. So it is much more complicated to be able to measure. In case of communication failures in these units, in general, one of the 2 boards is damaged. In that case, they are damaged and no longer work. This is so that you know it exists, take it into account, know that it can appear to you, and do not be in the dark. Very well, this is what has to do with the communication signal. Let's keep moving forward. In this video, we will be explaining everything about the use of portable oscilloscopes in inverter systems. This is a fundamental tool for any technician who wants to diagnose problems in inverter and who knows how to really do it professionally. That he can use it well in front of customers and you will look like a professional. This tool replaces many sample testers, many testers that we may find on YouTube, such as testers with small LEDs or a set of 6 LEDs. This tool replaces that and allows us to give a correct diagnosis. But of course, to use the oscilloscope it is necessary to understand the operation of the parts, as you have already done, for example, when talking about IPM, its operation, its measurements. We need to understand how the system works in order to use this tool. In this video, I want to explain some details about the use of the oscilloscope itself, and not only that, but in the following videos we will be talking about how to acquire it regardless of where in the world you are located. Well, the portable oscilloscope, when we purchase it, comes with its own case. It comes with a fairly hard and firm case that allows us to protect it well. It comes with its instruction manual, which is also in English. I will also be explaining how to use it in this video. Well, the case is very practical. It comes with its charging cable. It is powered by micro USB, its battery is charged by micro USB, and this charge really lasts a lot. Another detail to keep in mind is that it has a silicone case. All of this is included, of course, a completely insulating silicone case that allows us to support it perhaps on the equipment, on the boards, without fear of conduction. On the back, it is well insulated. It has a switch to turn it on, and of course it comes with its measurement cable. This measurement cable has the capacity to measure up to 100 MHz, being sensitive up to that speed, which is the capacity of our oscilloscope, 100 MHz. Okay, if they want to sell you something faster, check the test cable, because they usually come with 100 MHz measurement cables. So if they sell you one with more capacity, check the cable that at the end the limit is 100, usually in these portable oscilloscopes. So, it connects in the following way. We turn the connector until it enters its place. We turn the base pressing a little inwards. It is already connected. This comes loose and we have to insert it when using it. We press well and it stays there. A test tip holds the cable. And it always comes with its 1x10x knob. Whenever we are going to measure voltages of 30 volts or more, we will put it on 10. This activates a resistor so that the full voltage does not reach the oscilloscope and damage it. Whenever we look at much lower voltages, less than 30, we will activate 1x. Of course, if we activate or deactivate the resistor, we also have to inform the oscilloscope. That is why we will press the 1x10x button to be able to inform the oscilloscope that we are using or not using the resistor. So, voltage of more than 30 volts, we activate 10x and we inform the oscilloscope that we are going to use that resistor. So he knows how to do the appropriate calculation to inform us of the measurement. Very well. Other available functions are the variation in the speed on screen, that is, the time that will appear on screen, and the variation in voltage as well. If we are measuring voltages, for example, of 310 volts, as is the case of those of us who use 220 volts, when measuring the output of the IPMs, we will have to increase the voltage to 100. Why? Because each point, each line, each ray we have there, each box will represent 100 volts. 100, 200, 300 and up to 400 gives us the ability to measure. We need a high range. For those who are working with 110 volts, well, they can't go down a little because they only need a limit of 200. 50, 100, 150, 200 is enough for them to put it on 50 volts. Later, the buttons on the side arrows, will change the sampling speed on screen. For example, if we want to see what happens over a second, we will increase the time, 100 microseconds, 200 microseconds, 500 microseconds, 1 millisecond, 2, 5, 10, 20, 50, 100 milliseconds. That means that the oscilloscope on screen will be showing us 100 milliseconds for each box. In total on screen we will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 100 milliseconds, that is, 1.2 seconds on screen. There is a lot of information. In fact, if I measured the alternating current in this way, in reality I would understand little, because in 1.2 seconds there are many sinusoidal waves. I will have to zoom in a little, so to speak, and shrink the time displayed on screen to see the sinusoidal waves better. Anyway, if a measurement appears on the screen that you don't understand, when doing a test with the oscilloscope, press the auto button, and the oscilloscope will automatically adjust the time and speed to clearly show the wave. Another important point, use the DC/AC button. If we are measuring the input of electrons through a single cable, configure in DC. If we are measuring alternating current, please place in AC, so that the oscilloscope knows that it will receive electrons from the two cables, both from the positive, which is the test tip with holder, and the negative, which is in the shape of a crocodile clip. Here we have the battery indicator. We also have some details such as the maximum voltage to which the wave we are measuring reaches, peak-to-peak voltage and RMS voltage or average voltage, effective value to know the average power of that wave we are receiving. Do we have more functions? Yes, we have the possibility to stop. For example, what is on screen? That would stop the wave with the stop button. We have other functions that will allow us to see other measurements of those waves and even calibrate in case it is out of calibration. But well, for all this you can later see the link that I leave you. And keep in mind that all these functions are actually useful, but we are not going to use all these functions always. So, keep in mind that you can see more information in the manual that I am leaving you. You can even change the brightness as well. There we are lowering the brightness on screen to consume less battery, if possible. But many times we will use it in the sun, so it is convenient to have the high brightness activated. It looks great. It really looks like a robust, good quality, with good functions device. And the measurements it produces are really accurate, so it is a good tool. The save function saves the image on screen, takes an image which we can then review. It is stored in the small memory that the oscilloscope has. Well, those are some of its functions and how it is used. To highlight and repeat, the most important thing, it is to activate the resistance at 10x or 1x, because it is injected at high voltage without activating the resistance. In other words, if you leave it at 1x, you may run the risk of burning the device. Although it has internal protections, they may burn it and then you have to disassemble it, which is not going to be the most enjoyable, the most appropriate. So, please keep in mind to activate that resistance. Very well, in the next video I will show you some functions of a slightly different model, but very similar. In this video, I will explain the differences between this oscilloscope and the other one I showed you a while ago, the yellow one. This one has the advantage, as the brand says, of being able to measure up to 110 MHz. And it is true, it has that capability, but the problem is that the measurement tip has a limit of 100. So, as I mentioned a moment ago, in the end we are in the same situation. Its capacity is 100 MHz. This is a different oscilloscope. Personally, I like it less because it is a little slower at marking the wave. The numbers on the screen are not as clear and, in addition, I noticed that the battery lasts a little less. Apart from that, it is very similar. We have here, then, to change the trigger. Well, you can only see in the manual what it is for. It is not something you will use much. Here we have the buttons for time and voltage. Unlike having them on the arrows, here we change the time, you can see it below. And here we have the variation in voltage. We also have the 1x, 10x knob. We have the DC/AC button, you can see the change here. And we have the data on the screen as you are seeing it. It also has the save function that takes a photo of the wave that is appearing on the screen. And it has a button that tells us many more parameters of the wave that is being measured. In this case, it is a millivolt wave, a residual wave. In fact, it is not even connected, but it still indicates parameters of very low voltage. Well, it is exactly the same, only with those differences that I just mentioned. I am more inclined towards the yellow one, but this is a slightly newer model that you will find more on sale. If you have to acquire it because you cannot find the other one, there is no problem, it will serve you perfectly. In fact, when we see and do tests on the equipment in operation, we will use both, so that you can see that both will serve you. Well, in the next video we will be talking about how to acquire them. It is important that you know how you can acquire them internationally, anywhere in the world. Please, an important detail, store them well and take care of them. Do not throw them away without their case in the toolbox. Although it is an economical tool, the problem is that when it is hit, it becomes inaccurate and is no longer useful. So, if you hit it again and in a job it does not give you the exact measurement, well, you will have problems in that job. So, take care of it, store it correctly. Also the cable so that it does not bend or strangle. Notice that we are storing the test tip on its side. And as neatly as possible, store the cable at the top. This tip has to be taken out because otherwise it does not fit in the case. It is too long and that is why we take it out. Here we can store the battery charger cable. It is a normal white cable like those used by cell phones. Very well, try to store it properly. Perfect, let's go to the next video to know how to acquire it or buy it. So, the recommended page to acquire these tools, as well as any other spare parts, is AliExpress. Perhaps many of you have not yet bought things online, or have not yet bought things that are shipped from China. Perhaps it seems a bit strange to us, we may have a little fear of making these purchases. But we assure you that these pages are very safe. It is true, we will not deny that sometimes countries block the shipment of these items, or rather, customs block these items for a time, and sometimes we run the risk of losing them. But those cases are the minority. Most of the time the items arrive perfectly and we can receive them without any inconvenience. So, how to acquire the portable oscilloscope? By AliExpress. I will explain now some details so that you are within all safe that you are buying in a safe place. Although within AliExpress all sellers are usually reliable, there are some more reliable than others. In fact, I recommend that when you make purchases try to buy in official stores. For example, if we are going to be buying the oscilloscope that we have been mentioning, we place in the search engine digital oscilloscope or portable oscilloscope. Notice that the first to appear is precisely the copio threads that we recommend. An important detail is that it shows us that they already sold 2,624, and the ratings of those who bought it reach an average of 4.9 stars. Even you can see what people who bought it think. It comes super well protected, good quality and fast shipping. Opinions from different countries. Everyone agrees that they are of very good quality. In fact, we will show the photos that the people who bought it uploaded. This is how the package arrives. As you are seeing here, This is how the package arrives. It not only comes with the protective case, but the case also comes completely protected. You can see for yourself. There are people who have tested and used it. There it is showing us with a frequency generator the accuracy of the device. Reliable page. It is an important detail to keep in mind. Make sure the seller has a good reputation. We are then seeing that the product has many sales and the SALT and the ratings are very good. You can also go down a bit and look at who is selling it. The seller is the same brand of the device. It is the official store, FNRC. This same seller page has positive ratings of 99.1% and 19,500 people are their followers or have bought items from it. A product like this, with these specifications, or rather, with this rating, we can buy it almost without fear. It is true, it can be blocked from receiving at the customs of your country, but those cases are the least. You can buy without fear. The cost is $70. And as you see here, so, to the United States it has free shipping. Towards Latin America they have perhaps a slightly higher cost and a slightly longer delay. For example, notice that at the time of recording this video it is January 1st and for the United States it would arrive on January 31st. Something you can do when making these purchases is the following. From here, from the country where we are, direct shipments from China to here take quite a long time. What do? We hire companies, or, better said, we have some companies contracted that work to bring the products from the United States to here. I'm going to graph it to understand it. We have products from China. If we ship directly to Latin America, the shipping takes approximately 6 months or maybe a little less. But the shipping takes a long time. There are few flights, you have to make scales anyway. All of these details make it more difficult for a product to arrive from China to Latin America. What can you do depending on the country you are in? Suppose you are in Bolivia. You could find a local company online, a company that does shipping from the United States to Latin America. Better said, a company that gives you a virtual mailbox in a certain sense. That is, suppose your name is Juan Perez, and you have your address in Bolivia. If you order directly from AliExpress, the shipping will take you approximately 6 months. Now, the company you hire will give you an address that is an address of their warehouses that will be from the United States. So, what are you going to do? You will hire the company. The company will give you a name and a box number, for example, Juan Perez, box 2316. You will provide a United States address, for example, in Florida. For the products to arrive, this company gives Juan Perez a fictitious address. In this way, when you buy from AliExpress, you will tell China that your address is such a street in Miami, Florida, and that your name is Juan Perez, box 2316. Then, AliExpress generates the shipment and sends the package to the United States. It usually takes between 1 week and 3 weeks or 4 at most. When the product arrives in the United States, the company you hired will send it to your country within a maximum of 1 week. In this way, you buy from China, telling China that you live in the United States, that your name and address are such. The company provides you with this data. Of course, you have to provide this data to the company, and the company will send it to your country quickly. There are many companies that offer this service. If you are in Paraguay, you can ask us directly in the comments which companies we use. For those who are in other countries, we recommend that you look for this system since it is much faster than waiting 6 months and so you can buy in China. For those who are in Paraguay, I leave here written a company that you can use is Paraguay Courier. Take this detail into account for those who are in Latin America. For those who are in Spain, the shipping is very fast since AliExpress has its own warehouses in Spain. For those who are in the United States, shipping is also fast. Or you can buy from Amazon, which also offers many necessary items. This is the system we use to buy tools and electronics products. New York other component you want to acquire, look for it on AliExpress, as they are very economical. For example, the diodes we use for rectification, 100 pieces cost only 0.59 cents, while shipping from the United States is more expensive. Look for compounds and tools on AliExpress. Having explained this, we will continue with our training with other topics. Perfect. So, in this part of the course, we are going to practice soldering with tin. We will be talking about some details, some tips, so that you can solder in the best way without damaging components on boards and also without wasting time, so that you can do it in a practical and quick way. Well, we are going to use some component that is fixed on this board as a sample. Let's suppose we want to remove some of the resistors that are at these points. Let's take this one. This one seems like we had already taken it out, right? Let's take another one. Let's take out this resistor. So, let's say we have a resistor with an incorrect value and we have to replace it. So, what we are going to do is the following. We are going to apply heat, of course with the tin solder, but to remove any component, it is essential that you apply new tin at that point. It usually happens in most electronic boards that come completely varnished. So, when we try to reheat these points, it is difficult for the tin to melt. So, what do we have to do if it gets complicated in this part when melting the tin? We have to apply new tin. We are going to apply our tin, good and new, of good quality, at the point we want to solder. We heat the area well and apply the tin. Well, we heat well and apply tin. Perfect. Now we are going to use our vacuum desoldering iron or tin sucker. Always with the solder iron well cleaned. And the solder iron can always be cleaned on some kind of sponge, vegetable, or similar. And we suck the tin. Well, this is how we are going to leave the area clean. The tin sucker is going to clean all the tin well for us. As you know, the tip will not overheat or be damaged because it is precisely made to withstand high temperatures. Well, once we do this, what we are going to do is lift the terminals of the component, which are bent so that the component stays more fixed. We will straighten them again. And almost at this point, we should be ready to take it out. Let's look from the other side. Yes, we already have the component almost out. It's this one. There it is, it came out without problems. This is thanks to the fact that we made a good suction of the tin. Remember to use good quality tools, such as the ones we recommend, to be able to solder and desolder in this way. Well, once we have done this, we are going to clean the area again, and we are going to leave it well cleaned and correct to be able to put the new component back in. We will keep cleaning. And once we see that the tin sucker is not sucking anymore, we are going to apply the desoldering mesh. We are going to apply always, remember, the solder iron well cleaned. We heat the mesh and apply it over the area to be cleaned. Very well. And if we wanted to, we could apply isopropyl alcohol for a final cleaning in case it is necessary. I am going to apply it, just to be able to show it well. The area is now clean enough to replace the component. In this case, we would be replacing a new component, of course. But we are going to place the exact same one. So, to replace the resistor, we try to give the terminals the correct shape with some of the pliers we have. And so we have the correct shape. And we place it, of course. Now, what we are going to do is turn the board over and bend the wires so that it is fixed and held in place to be able to solder correctly. To be able to solder, it is important that it is well fixed, because if it moves at the moment of soldering, we run the risk of producing a cold solder. Look how it will look now when I solder it. We are going to heat it up well. The trick and key is to heat up the base and the component well. The base and the terminals of the component must be very hot. Very hot. And at that moment, we apply the new tin. And it has to look like this, a shiny drop of tin. Again, the same thing. We heat up the base and the component, apply tin, and it has to be very shiny. If the component is not well fixed before the moment of soldering, you may run the risk that the component will move just at the moment the tin cools down, and that can produce a cold solder. What does that mean? Well, you saw when we heated the iron, you put it red hot and the molecules expand, and then when it cools down, they come back together. What happens if we heat and cool down suddenly? If we cool down suddenly, the molecules lock up and the iron or steel is tempered. It is a process that is necessary to create tempered steel. If you heat it and cool it down quickly so that the molecules cross, so to speak, they lock up and become much harder. Only that it is no longer flexible. When we try to bend it, it breaks directly. Well, the same thing happens with tin. If when it is cooling down we move the area, the molecules cross and it may be that they do not produce, or it may be that they do not transmit electricity, that they do not allow the passage of electrons. That is why the area has to be well fixed. In this way, at the moment of cooling down, the molecules are arranged correctly and the tin is formed visually when the solder points are shiny. If they are shiny, it is correct. If they are very opaque, do everything again. The key is to heat up the base plate and the component well, and then apply the tin. And, of course, that the component is fixed before soldering. This also applies to copper welding. If you, as refrigeration technicians, weld with copper, remember that the key to all these soft solders is to apply heat first to the equipment parts, and finally apply the soft material that will be welded. That is the key. Heat the areas weld that we need to solder, and, at the end, there is the copper rod, the Harris rod, the tin in this case, and that is how it has to be. Something else you can do is apply silicone. Remember that these areas are well varnished because the air conditioning unit is always exposed to dust and moisture. So if you can apply silicone, let's see if I have the gun turned on. No, it's off. The ideal is to apply silicone to be able to cover and so that it is not exposed to dust and moisture and that a short circuit may occur. Just as it is in this case that we made a jumper, or here that we also made a jumper that we will now do in a moment. Or here that we have also replaced a resistor. In a moment we will apply silicone here. Remember, the silicone has to be. This has to be the heated silicone gun, because this is the silicone that can be applied in electronics. We will apply it here, and when making a jumper we will also apply it to protect the area so that it remains isolated. Very well. We will let it heat up. It was turned off, that's why it's cold and it's heating up slowly. Well, in the meantime, I'll show you how components come when they're new. When you buy resistors or diodes, they come this way. When you buy these components, they come with long wires that give us the possibility of molding them as we need and being able to adapt them or fix them to the board in the position we want. They are very flexible wires that give that possibility. And once you place these components on the other side, if we place it in any of these points, let's see. Let's say we'll place it here. And it's too long. Well, we're going to bend it to be able to fix it to the side where the track continues. Be careful, don't bend it to the other side that could make contact with another point. Bend it to the side where the track continues. Let it be well fixed. Make the weld. Make the weld at this point. We heat it well, apply tin. We make the weld. Let's do it again so it can be understood well. Bend it to the side where the track continues. If we leave it well fixed, we heat it, we produce the weld. And finally, what we are going to do is cut off the remaining wire. Cut off the remaining wire. And then we have the component well fixed. This is as a sample. I only did it as a sample, using a new diode and soldering anywhere on the board. Remember that you have to cut off the excess wire. And that's how it has to be. It has to be well neat and fixed. Well, we go back to the silicone gun and we're going to cover the area. Perfect. And we're going to cover the other resistor that we soldered a moment ago, which is this one. Well, we can apply this silicone without fear because it does not conduct electricity. So then, we have the contacts well covered and they will no longer conduct electricity. Of course, they will not consume electricity if another component touches them here. But they, of course, continue to conduct the electricity from the component to the entire track. Very well, that's how we're going to solder with tin. This is the correct way to use the tin solder and to do it quickly and efficiently. Next, what we are going to do is a bridge simulating that we have a damaged track on our board. So, what we are going to do is damage some of the tracks and make it stop conducting electrons so that we can then repair it. Well, we'll do it slowly, step by step. We're going to use our multimeter. We're going to measure continuity on one of the tracks, which we're then going to damage on purpose to be able to make our repair. We're going to try this track, a track that goes from the microprocessor to the display. We're going to repair this track. I'm heating up to be able to make the measurements correctly since the tracks are varnished, and that's why it's more complicated to measure if we have the varnish covering the conductive part. We're going to go to continuity. Very well, and we're going to go from here to here. Well, we have the track working perfectly. What we're going to do now is damage it. We're going to cut the track, removing the copper that produces the union. Very well, we're almost there. Let's test if it's already done. Yes, and the track no longer conducts electricity, does not conduct more electrons. Well, how are we going to repair it then? Suppose we have a cut track, which is a very common damage in electronic boards. We're going to do the following. We have two possibilities. We can solder a small wire from this point to this, which are the 2 points that are in union, or if the track were too long to not pass a wire through the entire board, what we can do is release points from the same track to the same track, and that's what we're going to do now. The first thing we have to do is, we're going to wear down the track in question a bit and expose the copper. You can see it there, and we're going to do exactly the same on the other side of the track in question without pressing too hard so as not to break the copper or cut it, and again we leave the copper exposed. Once we have this, with a clean soldering iron, what we are going to do is heat the copper area and apply solder. You can see how we apply solder, and we will do the same here, heating well. Once we have done this, we are going to prepare a small cable. In this case, I am using a cable, so you know the thickness is the same thickness as temperature sensors. They are thin cables, and we put solder on them. We always put solder on everything before using in electronics. Do not skip this step because it will be very difficult for you. Always put it on the cables or anything you are going to use before placing it. We heat and apply solder. Well, and the same on the other side. Once we do this, we are now going to use these cables to produce the union in the cut tracks. There is no need to apply more solder because we already have solder on the track and we also have solder on the cable, so we don't have to apply it again. We simply have to support it and heat it. Remember that while it dries, we must not move it at all, and we will do the same here. We try to locate. We can hold it with something. Very well, there we have our jumper connected. Always remember to review these unions to see if they are really producing continuity. We go back to the original points, and we have continuity definitely. And of course, do not forget to apply silicone. We ran out of silicone. We are going to apply new one. Now yes. Very well, we can apply silicone generously so that the area is well isolated. Very well, there we have a track repair done. Keep in mind that tracks break more often than it seems. So, when you make repairs to boards and you may not find the error in the components, check the tracks with patience, because many times they are the problem. Surely it has happened to you that you send electronic boards for repair and the only thing the electronic technician does is connect some cables to the board. It is not that he made a modification or anything out of the ordinary. What he did was place cables in replacement of burned tracks. So take the time to measure tracks, check continuity, and it may be that in many cases you will find the problem in a cut track. Even more so considering the more complicated boards, the inverter type, which are much more complicated, much thinner outer boards at least, the tracks are thin, they are exposed to dust, moisture, and they really cut, they burn. Well, that's it for the jumpers that we will be doing on the tracks. Well, in this video, we are going to explain how to solder surface mount components. We have this board, which is quite delicate, a board very similar to what inverter boards are. We have SMD components, which are found in many inverter boards and need to be replaced when they are damaged. We are going to replace an SMD component, a resistor specifically, but I will teach you how to know the value of these resistors. Well, let's observe one of the resistors we have here. Specifically, let's observe this resistor. Let's do better with this one we have here. This resistor has a value that is indicated by the numbers that are printed on its body. And what are the numbers that are printed? Well, you can't see them because they are too small. I can't see them either. Well, maybe you can see them later with a larger screen, but I can't see them. So, what I'm going to do is use the microscope. By the way, I'll also show you how to use the microscope. We take the board out of the holder, and with the microscope we will try to show the number of that resistor on the screen. It is the one we have here. This resistor. Look, it's a 102 resistor. The number it has printed is 1002. What does it mean? What value is it? Well, you are seeing its value upside down. I'll turn it over and you'll see it right side up. The value is 102. What does this mean? We are talking about 100 and we are going to add 2 zeros. That is what the numbers of these resistors mean. When they are 4 digits, the first 3 numbers tell us the value and the next number tells us how many zeros to add. We are talking about a resistor of 10000, a resistor of 10,000 ohms, 10K. If we find a resistor with only 3 numbers like this one, it is a resistor of 10 plus 2 zeros, or 1000, 1K. But this one that we are going to work with is 10K, and first of all we are going to measure it to see if everything is fine with its values. Let's see. Let's try to show everything on screen. There we have the resistor, there we have the board, and on this side we are going to put the multimeter to be able to see the value. The first thing we are going to do with the soldering iron well cleaned is to reheat the soldering points of the resistor so that the varnish does not affect the measurement. There it is, there we heat it. And now we are going to make the measurement in ohms, and let's see on the multimeter the value it gives us. There it is, we are talking about 10K. Perfect, this resistor is in good condition. But we are going to remove it anyway to be able to practice. There we can see the resistor in the microscope. We are going to remove it and practice soldering on the resistor. The way to remove it is directly with the soldering iron, so let's see if you can see the microscope on the screen. We are going to heat it from one side, we are going to heat it from the other. We are going to heat it from one side, from the other, and we are going to push it with the same soldering iron. If we see that it is difficult to remove, the only thing we have to do is apply new solder a small drop, and in this way it will be much easier to reheat and be able to remove it. We are pushing it, of course. You will remove it when the resistor is no longer useful to us. That is why you can heat without problems. But even in this resistor we are going to remove it and use it again also so that you can see that they do not get damaged either. Well, let's observe the resistor. We have it here, right? This is the resistor. Perfect, we already have it out. Here we have the 10K resistor. So you can see how this resistor is. I'm going to show it to you from the bottom. I'm going to lift it with the tweezers, and I'm going to show you the bottom side. There you can see it. At the ends where they have the contacts. As you can see in the camera, they are very small, and when you buy them, in fact, you can put now in the search of AliExpress, SMD resistor 102, and you will see that they come in a kind of blisters where there are many resistors. Its approximate cost, 50 cents of a dollar for 100 resistors, so they are very economical. So, we were able to remove the resistor, and carefully we will keep it for later to be able to put it back. But what we are going to do now is to clean this area, where we are going to put back the same resistor, but for this we will no longer use the microscope, but we will be using directly the holder of the board and zooming in as much as we can. Very well, let's observe well what we are going to do now, because these steps are very important for working with this type of surface mount components. The key is to clean perfectly the area where the new component is going to be soldered. It has to be perfectly clean, and now you will see how we do it. The main thing is to clean that area well. We are going to use for this, not the vacuum desoldering iron because it could absorb some components since they are so small, but we are going to use the desoldering mesh or the desoldering tape. We will support it well and heat it a lot. And we continue cleaning well. There we have the area quite clean. There it can be seen, and we also use isopropyl alcohol. And so the area of the SMD component has to be left as you are seeing. It has to be impeccable to be able to place the new piece. Let's do a quick measurement now to see if there are any components that are short-circuiting any peripheral components. Let's measure resistance. Well, we don't have any value. Well, we don't have a perfect value. We're ready to put in our new component now, but in our case, we're going to put in the exact same one, so you can see that even though these resistors seem very delicate, they actually hold up quite well and can be desoldered and resoldered. Of course, with a soldering iron that heats up to the right temperature and also not overheating the component, but just the right amount needed. We'll bring the component close, we'll have it very close to the area to place, and we'll put a small drop of tin on one side, but it has to be very little. We bring the component close and then we won't hold it with our hand, but with some tool. I like to take my time so that these components are well arranged, as much as possible. And next to it is indifferent. Well, there we have the resistor placed on one side, and now we'll solder on the other. Perfect. Very well, we try to make it as good as possible, and we'll take a measurement to see that the resistor is correct and that it hasn't been damaged either. We'll take this measurement and the value that it gives us on the screen is 10K. Of course, there's always a little more or a little less because they're not high precision resistors, but it's completely tolerable. Very well, there we have our CMD component placed back in its place. We hope this step-by-step video is helpful for you when you have to do these solders that are delicate but possible. Remember that in inverter boards we have many surface mount components in sensor areas and power zones of the IGBTs in many areas. Remember that if we make several repairs to electronic boards, it is always a good idea to apply a protective layer of silicone. For example, in surface mount components like these, if we make repairs, it would be appropriate to always apply a protective layer of silicone. Why? Remember that originally this comes all varnished, with a special varnish that does not conduct electricity and protects the board. We can apply this silicone and the components will be well covered, both of these components and the diodes if we are also replacing them. The transistors or any other component that we usually use on the board. It would be appropriate to do this and cover them with silicone. Remember, the silicone has to be this one, not the chemical one, the one that dries only in contact with air. Perfect. So, in these videos, what we're going to do today are some tests on an inverter unit, but assuming that the unit is completely installed. That's why we have the indoor unit here and the outdoor unit here, also partially disassembled. Just by removing a few of its protective plates, we find this part of the unit exposed, mainly the board that is here, where we will start to be able to make all the other measurements. So, we are going to control in this part some parameters that we have already been seeing in the training, but we will do it with the board in place to determine several points or possible failures. At this point, I placed 3 small cables and here 2 that are the ones that are in the signal area with the purpose of showing you and making measurements. You can do it directly at the contact points. The problem is that here you will not be able to grab the oscilloscope, and also remember that they come completely varnished. What you have to do without a doubt is reheat or use test joints that are sharp and that stick, and that can make the measurement through the varnish. Very well, then we are going to proceed now to make some measurements on the board to be able to rule out problems, find failures, and you will see that from the board we will be able to reach even to measure the operation of the motor, the reactor, and the fans, all from this point of the board. But of course, it is very important to understand how it works. It is important to know which UVW goes to the motor, important to understand that C and N is the communication measurement, important to understand that L1 and L2 is always the location of a reactor or reactive coil, and you have to understand it to be able to make the correct measurements. Here we have the other opto-couplers, all the pieces that we were seeing in the training, we have them here. And from here we can make those measurements, even as I will show you now. At this point you will see that we have the sensors. Let's do a little zoom. Here we have the location of the sensors. I don't know if it can be seen well, but here it says TH. Here we have that sensor measurement. Here we have the LGB is the port where the sensor is placed, of which more later is explained its operation, an intelligent module to be able to make diagnoses. If we observe well, here we have the switch, an 8-terminal component, which is the switch, I mean this one. There are 1, 2, 3, 4, and here there are 1, 2 that is not always placed, 3, 4. Here we have the transformer, and if we continue advancing a little towards the secondary side of the power supply, we will find a 3-terminal component. Generally it is a 7805. And we will find some checkpoint of 5 volts, it says 5B. Here we have the negative, and here we have a checkpoint of 15 volts. We have a checkpoint of 15 volts also, so we have the whole board in view. If we go back, we have the switch as I mentioned. Remember that the switch enters negative, and if we follow the track, right here we already have the capacitor with thick solders. If we go back a little further, up there, we already have the rectifier. Negative, we turn it around and we have the negative of the rectifier, and on the other side the positive of the capacitor. Here there are jumpers, which will be made in the switched power supply, and here there are jumpers that go towards the positive of the IPM. Here we have the IPM as you can see. If we go back, in the power supply we have a reactor, a PTC, a filter capacitor, low-pass filter, coils, the fuse and varistor. Here we have all the components that we were analyzing in the training. If we go a little further towards here, we have the communication, the involved diodes, and the opto-couplers. We have it all in these inverter boards, and we have it all without completely disassembling the equipment. By disassembling very partially, we already have access to all the measurements we need. So, we are going to proceed to make some in the outdoor unit, and then we will move on to the indoor unit. Very well, we are going to make a measurement on the main tracks that start from the positive and negative voltage input, or rather, line and neutral. Of course, we have a unit without power. The first thing we are going to do is go to the areas where we are given a measurement point without energizing. What we can do is measure the continuity. So we are going to go with the multimeter to the line and neutral. And from there we will make the following measurements. We enable our multimeter. Here is the neutral. Here we have to have 0, 0 if the low-pass filters work well. And we have to reach the bridge rectifier without resistance. So far, so good. From the positive, which is the line, from the fuse we have to be able to pass through all the components and reach with low resistance. We have a fuse, we follow tracks. We have a winding of the low-pass filter. We follow tracks. We pass through a PTC reactor, and finally we reach the positive, to the line, of the bridge rectifier. Why do we have a certain resistance of 40 ohms? Well, that resistance is being caused by the existence of a PTC, which is a ceramic that if the temperature rises it will detach or cut the circuit. That is why a resistance of that amount of ohms is found. That's fine, so far we are. Very well, what else can we control? Well, of course, the bridge rectifier. There we can see in this corner the bridge rectifier. And here the multimeter, but now we are going to place it in diode position. So now we are going to move on to controlling how that bridge rectifier is. Very well, then we are going to position ourselves with the multimeter. With one of the cables we are going to place it in the positive, and with the other end we are going to change from alternating current. Well, here we have two diodes in reverse, thinking from alternating current to direct current. And evidently, we have OL. It's perfect. But if we invert the cables, then we already have to have the diode voltage drop. And there, evidently, they are and they are working well. Now, we do the same, but towards the negative of the direct current. In this case, if it has to give us a drop, I'm going to lift it up a bit. If it has to give us a voltage drop, and if we invert the cables, the diodes are in reverse, and it has to mark OL. There it is. We are measuring the bridge rectifier. Having already knowledge of what is inside, for diodes configured in the way we already know, as a full-wave bridge rectifier. Well, that is how we make a measurement in these bridge rectifiers placed on the board. Very well, we are going to follow the track path. We will get here, to the capacitors, and then we will go to the IPM. And if we have an IPM error, motor error, overcurrent, low voltage, it may be that we have a problem with the IPM. How is it controlled? Well, something very important that you have to control are these resistors that act like fuses. These resistors that go from the negative and enter the IPM have to have a low resistance. You have to control them, and the measurement that has to give us is 0. The two will have the same value, because they are placed in parallel. What else are we going to measure now? Well, in this area where we are measuring the IPM, we also have to control the same IPM, but now in diode position. And you know well that from the positive and negative of the IPM, we then have the outputs through the IGBTs, through U, V, and W. So, in diode position, we will control from the UVW outputs to the negative. Voltage drop of one diode, voltage drop of another diode, and voltage drop of another diode. We are testing the IPM, but we are testing it from the capacitor to the output to the motor. If we invert here, we already have to have OL, open line. There is no voltage drop, that is, the voltage drops completely, it does not have a reach to the other end of the multimeter, and this is fine. We also approve in resistance to see that the IGBTs are not in a short circuit. And it is correct. We occasionally see a measurement in megohms, which is correct. It is very good. In transistors, a measurement of several megohms always appears in case of good operation. Here we measured 3 because we went only from negative, but now we are going to go from positive and measure voltage drop of the 3 diodes in parallel to the igbts. Invert. OL. We also test in resistance. Nothing. Well, for megohms. We invert 18 megohms. Nothing and nothing. 7 megohms. Perfect. We are fine. Until then we have tested this IPM that leads to the motor, which energizes the motor. Of course, as you already know very well. I will show you, in case you did not remember what we just saw. What we just saw a moment ago is the IPM measurement. Remember that this is the IPM we are measuring. We are controlling from the ends P and N towards the outputs UVW, and we are controlling both diodes and transistors. Very well, perfect. Well, other measurement parameters that we can make from the board are the measurement of the reactor, the measurement of the compressor, and the measurement of the fan. We can do everything from the board because that's where it all starts. So pay attention to what we're going to do now. We will work intelligently. Think about what else we can do from here without being invasive with the equipment and having to disassemble it completely. This is what I mean when I talk about intelligent work and training. Let's think so we don't have to waste time, be invasive with the equipment, and not seem unprofessional in front of the customer. How do we know if the motor is good or bad? It's very simple. We know that the motor is connected to the UVW output. It would be strange for someone to have already disconnected it before we arrived. In general, everything is connected and we are the ones who are coming to repair it. So let's check the status of the motor directly from the electronic board. 2.8 ohms, 2.9 ohms, 2.8 ohms. We don't need more than this to be able to measure if a compressor motor is electrically working properly. Can it be blocked? Yes, it can be blocked, with the rotor locked, but it is electrically correct. And what can we say about the reactor? Well, where we find the terminals that are called CL or only L, those are the points where the reactor is placed. And again, we can do it from the board. Reactor resistance 0.4. Perfect. We are measuring the reactor from the board and we are deducing and knowing that it is in good condition. It may be grounded, but the only thing I'm going to do is touch from the reactor to any screw on the unit and it has to keep marking OL, of course. I didn't see the reactor, but I checked it and I know it's in good condition. Remember, intelligent work saves time, wins customers. Well, all of these details that we've been seeing, of course, we can measure them from below. We can measure the compressor from here, the fan, we can measure the reactor from below. But the same measurement can be done on the electronic board. What are we going to do now? Well, next, what we're going to do are voltage tests. So, we're going to energize the unit, turn it on, and we're going to make measurements with the multimeter, but in voltage position and also with the oscilloscope, which will give us many parameters about an inverter unit. We energize. We see the LED on, we hear the startup beep. We turn it on, cold at minimum, and, of course, we wait. And we already have the unit turned on and the compressor also turned on.
Muy bien. Bueno.
Very well. Something we can measure is, for example, the input voltage. It is essential that the input voltage is within the correct ranges. This is the cause of most low voltage errors. The low voltage really. We're going to check it and we see that we have 204. The voltage is down here. If we had 10 volts less, the unit would already give us a low voltage error. What else are we going to measure? DC voltage in the capacitors. With great care, please, these measurements. The voltage is at 250. It is quite low due to the fact that the motor is running quite hard and that I have low voltage at the input. But for the team it is acceptable. It still starts it up and makes it work. What happens if I measure voltage in the IPM area? Well, if I look at the voltage between U, V, W, the values that it is going to give me on the screen are strange values. Let's look. Very strange voltages. 129 millivolts, volts. They are very rare voltages and variations. There is no possibility of measuring with a multimeter in the compressor output area. But we have test and measurement points in the low voltage areas. What does this mean? A plaquette that is not working. We are going to go and blame the zone of the source. Of course, because if the 5 volts, the 15 are prepared, the plaquette at least has to make the startup beep. What will we do then? We will make measurements in the power supply area in case the plaquette does not turn on. Let's take a closer look. See that we have output from the 7805. In fact, the plate itself gives us checkpoint. Look here. We have 5 volts and G and D, and there we have 15. In those points we have to have those voltages from the moment the equipment started. If those voltages are not there, the problem will be a part of the power supply. Another interesting and important parameter to measure is the capacitors that feed the igbts. These capacitors are found on these boards at this point in these areas. It is true that on some electronic boards they are not visible and their measurement is much more complicated, but at least on this one it can be done. So we are going to measure voltage there on these capacitors. We have a multimeter and it looks much better there. We look at that point, and we still don't have the voltage. We have millivolts because the capacitors are not activated since the compressor is not turned on. We will wait a moment until the compressor turns on and then we will be measuring the 15-volt voltage. We will continue waiting. We wait a few more seconds. Now the compressor has turned on and we can now control that voltage. There we have the 15 volts perfectly maintained. These capacitors are fine and we will not blame them in case the IPM does not activate. Of course, in this case the equipment is working. But with a unit in which its IPM does not activate, or we have errors on the startup sequence of the compressor or of the compressor itself, we can blame these capacitors, and we have to do that control. At the moment it has to turn on, there must be 15 volts exactly. If there are less and you suspect that they are the problem, you have to remove them and control these capacitors outside. Remember that, on some electronic boards, as we have already explained, these capacitors are not there. They are in areas that are more difficult to control. Keep that detail in mind. Very well, another measurement area that we will have is the signal area. In this case, I have two test pins where I can test the signal by measuring a DC voltage. Point N and point C. There is also the possibility of doing this same measurement, but doing it on the terminal block of the unit, where the interconnections between the indoor and outdoor units are connected. We will measure there. And there we have the variable voltage. 6, 45, 36, 35, 10, 6, 35, 10, 6. It always stays at that point. The signal is correct. But I'm also going to measure in this area. I'm going to measure here, where the interconnection terminal block is, at this point. Let's see if we can see it. There we have the interconnection terminals that you know very well. Let's see if we can illuminate a little. Now yes. We will place between N and between C. And there we have the variable voltage. It is with the minus sign because the cables are placed backwards. But if I connect the multimeter measurement cables the other way, then we have the values without the minus sign. Very well, there we have a correct measurement. This shows well what is really happening with the communication signal through the opto-couplers. Another important detail that we can measure in the case of an inverter unit is the UVW output with an oscilloscope. In this case, we see that we have the measurement tip in 10x, as we had explained. I am using one of the test cables that I have connected to this board to be able to make these measurements. Perhaps if you don't have those small cables, it will be a bit complicated. But they will help you to diagnose a faulty compressor that has not affected the board. Well, here we have 10x, 100 volts. Let's do a little zoom to see a little more of the wave. Let's do each time more 1. And there we are seeing better how the speed wave is moving. That is the pulsing voltage that is simulating a sinusoidal, and that is how the compressor motor works. I can change points. Instead of testing UV, I can test UW. With great care. We don't want to burn anything or damage myself. It's a bit difficult with the camera and the unit energized. Now yes. Let's test the one we are missing, which is V and W. Now everything is working perfectly. We will do tests to be able to know what measurement we have to get in case the compressor is not there, and to be able to know that the IPM is working well. If we vary the speed of the unit, for example, if we raise the temperature, the unit has to lower its revolutions. And it has to be clearly seen how those waves move away, simulating a lower frequency. Better said, creating a lower frequency so that the compressor works slower. We now place the unit at 28 degrees. We are going to place it at 29 and wait. We will wait to see how the compressor lowers its revolutions. Now we have a low ampere consumption. And look, the compressor turned off. This debunks the theory that the inverter never turns off. In reality, when the inverter feels that it is much colder in the environment than the customer is demanding, the inverter also turns off. It is true that there are brands that try to regulate the speed a little more and wait a while so as not to have to turn off the unit. But LG is a bit of a rustic brand. It feels a lower temperature and directly turns off the compressor. What did I do to make it turn off? Well, I configured it at 29 degrees. It felt that the temperature in the environment was much lower than the required temperature, so it assumed that the compressor had to be turned off. Very well. These are some of the tests we are doing on inverter units. In this next test, we are going to disconnect the compressor and see how the IPM reacts, in order to deduce if the IPM is in good condition. When a motor is not, when the motor is blocked, we no longer have it and we want to make sure that the board is working properly. Well, we are going to do the following. We are going to disconnect the compressor, which is what we just did. Now, we are going to lower the temperature so that the compressor tries to turn on, or rather, so that the board tries to turn on the compressor. We are going to see what reaction appears on our oscilloscope, which will tell us that it is working properly. We can lower the voltage a bit. We can go down to 50 and see what happens. So, again, what we are going to do is wait the necessary time for the compressor to start up, or rather, for the board to try to start up the compressor that we disconnected. We are going to wait. Maybe we are going to heat up the sensor a bit. Look! We had an output of approximately 100 volts for a very brief period of time. And there we have it back, and there it is cut off. This is indicating to us that the IPM is working properly. Look, there it is. What happens is that those lines go to one side only because the electrons go, but they cannot return because they do not have the compressor installed. This will be enough for the board to understand that the compressor is not on. Now, it is throwing us an error code. The error code that it is throwing is through an LED. It informs us of a number. Pay attention, please. Let's wait for it to stop. Now it has stopped. 1, 2, number 2, 1, 2, 3, 4, 5, 6. Error code 26. The compressor is not connected or is electrically damaged. It is the same thing that we just did. We have to do it with the other two combinations. That is, we just did it with a UV, W. And now we have to do it with a UW and then with a U and V. The same test 3 times to know that the IPMs are working and that the problem is not in the board, but only in the compressor. But for that we have to turn off the unit and disconnect it so that the error code is prescribed. We disconnect it for a minute, reconnect it, turn it on and wait for it to indicate the same parameter on the oscilloscope with the 3 different combinations. Remember that this test is essential to know that the equipment has its board in good condition. And remember also to do, in fact, in total 6 tests. We will test U, V, and then VU. We will invert the cables. In this way, the electrons will enter from the other side. The oscilloscope will think that the electrons enter from the other side. Let's always do those 6 tests to determine with certainty that the board is working properly. Very well, don't forget that you can also measure the operation of the sensors. Here we have the unit de-energized, and here we are disconnecting one of the sensors. The one we are going to disconnect is the discharge sensor, so we can see its different value from the rest. Here we can measure it in ohms or resistance. We have a sensor that is now showing us 68K. It's a bit hot here, so it could easily be a 100K sensor. And remember that we can also measure with voltage at the points where the sensor is powered. This way, we corroborate that the circuit is working properly and that the problem is not the circuit that controls the sensor. To do this, we have to put it in the volts position, always direct current, energize the unit, and without turning it on, we already have to have the voltage at the output of the sensor. We have 4 volts. We are fine. Let's test another sensor, 1.9 volts, perfect. 2.0 volts, perfect. We have values between 1 and 4, between 1 and 4.5. We are fine to say that the sensors and the sensor circuits are working properly. Here we have the indoor unit of an LG unit. We see that it is partially disassembled. We will also do some measurements and observe some points that the board presents us to be able to control. If we bring the board closer, we can see that it is placed exactly upside down from the outdoor board. So, that means that there are things that we can no longer control. We no longer have the green part of the board, but we do have some details or points to be able to make some measurements. Can we measure how the capacitor is doing? Yes, we can, but not from below the capacitor, but we can actually do it from the fan output. Remember that these fans are powered directly with 310 volts that are the ones that come directly from the capacitors. So, if we can measure between the black and red point of these fans, we will have a measurement of the direct current voltage of the capacitors. But for this we need some tricks, because they are very fine points and it is difficult to insert the test leads. Something that I usually do is the following. We will use a multimeter, but we will put different tips on it. In this case, what I did was to peel off a little or burn a little the rubber of this output to be able to place this test lead here. These multimeter test leads are sold separately. They are very economical, similar to those of the oscilloscope, and they are used to leave fixed measurement points. For example, we are placing it on the negative, and from there I will place with this tip also a special thin tip. We will place it inside to measure and find the capacitor voltage. So, we are going to energize the unit. We are going to wait. And we are going to verify if those voltages are there. Well, 306 volts, we are fine so far. 306 volts, the capacitor voltage is correct. Here we have the rectifier bridge, but it is a bit complicated to measure. Everything else that is there is complicated, although it is there and we can understand it. Switch. Ferrite transformer. Look that we have the Schottky diodes of half-wave rectification here. The final filtering capacitors. In this board we have 7,805 here behind this plastic. These are some parameters that they present us. We could also measure even the receiver of the remote control. As already taught, that point is exposed to us. We could measure the sensors and their voltages. There are many things that we can do with a little knowledge of electronics without having to disassemble the entire unit. And that is better, because with the unit assembled it allows us to have the entire unit in operation, the entire unit assembled, and we will arrive better at the resolution of the problem. On the fan, what we are going to check is that the voltages exist. To do this, we are going to place the measurement at this point, and we are going to check first that 310 volts are sent to it. We already said that we were fine. Then we have to test that 15 volts and the final sending and return voltage are sent. Now it is not there because the unit is turned off, but if we turn it on, as we are going to do now, we are going to turn it on in ventilation mode so that only the fan turns on. I'm going to show that we turned it on in ventilation mode, and we're going to test that 300 is there. Between black and white 15. Between black and blue 7 volts, which is the warning from the fan to the board, and between black and yellow, the warning from the board to the fan. In case the fan does not turn on, well, you have to check all these parameters. If the board does not give the start command with the yellow cable, the fan will not turn on. But what could be the cause? It could be some of the 3 opto-couplers that are the ones that activate the 15 volts. The second is the signal from the fan to the micro, and the third is from the microprocessor to the fan to start. So if the fan does not start, you have to check the board. If the board does not send voltage, you have to check the opto-couplers and the tracks involved in this process. Now, how do we do it if we do not have the fan connected? How do we do it to verify that the board is working well? Or if the fan does not work, how to verify that the board is working well? In the next video we will see it. To do this, what we are going to do is directly disconnect the fan. We continue connecting the negative to the black. And we will test that 310 volts are sent. This is correct. Of course, the 15 volts are not there because the unit is turned off, but we will turn it on in ventilation mode and we will see that those 15 volts are being sent. 15 volts are sent. There are 15 in the signal that is not derived, that is, the fan is not giving notice. And the yellow is giving a high voltage to try to turn on the fan at maximum. Pay attention to these parameters. The yellow tries to turn on the fan at maximum, and it does not respond. The blue does not receive a response, and the white continues to send the 15 volts to turn on the fan, the electronic board. This is going to do it for a few seconds, until at some point this is going to disconnect and an error of fan is going to appear to us. Let's observe. It is still waiting for a return signal and it does not find it. So, the fan is definitely not there. That's what the team says. The team will stop sending the 15 volts, it will stop sending the life signal and the return signal. And now yes, it will be marking the error, as we are seeing there of the fan, CH10. But we know that the board works well and that the problem is the fan, in case the fan does not work. A very important detail, to finish with these tests of the installed equipment, is that when we are going to repair an equipment whose PCBs do not turn on, the first thing to check is the voltage in alternating current, neutral, and line. Many times the PCBs arrive at the electronics technician, and the technician says that they do nothing wrong, they work perfectly. Of course, this is in the case that your electronics technician is honest. But remember to first test that there is voltage between line and neutral. That is where you energize it. I just energized it, and there we see that the voltage enters. If not, it will happen to you that many times the electronics technician tells you that the solution is to check the power cable. And in reality, he did nothing. He deduced that the problem was the power cable. So always test the alternating current voltage input to see if it really enters the voltage that the PCB needs. The beep has to be done always, and the voltage of the PCB always enters, whether the equipment is turned on or off. The software of the microprocessor is always in operation while the equipment is energized, of course, waiting for the order to be able to start it through the remote control. At this point in the course, I want to teach you a diagnostic system that LG has for all LG brand equipment, preferably those that are inverter. They are bringing a label that indicates Smart Diagnosis. Whenever we have this printed, notice this is one of the covers of the indoor unit equipment. We can make a diagnosis through our cell phone. This is very good because it makes us very professional in front of the client, and I am going to teach you how to use it. We are going to take advantage of the fact that this equipment is marking us CH10 because the fan is not connected, and we are going to learn to use the LG ThinQ application. This application is the one that will be able to give us a diagnosis of the operation of the equipment. How does it work? Well, what we have to do is first link the device by adding a device. You can scan the QR that is printed on the equipment or select a device yourself. In this case, I already did it, so I already have it there, sample equipment. Once you add it, you enter it and we are going to read what it says. Smart Diagnosis can detect problems early and help you solve them. Start. Check the power supply of the air conditioner. Well, in this case we have it energized. Place the phone's microphone near the air conditioner. It wants us to place it like this. Now we are going to see what for, and now you are going to understand why. After pressing the Start Diagnosis button, hold down the Diagnosis 5S button on the remote control for 5 seconds. That is, after pressing the next button, we see that the microphone is being activated. The application asks for permission to use the microphone in case it is the first time, and it starts to detect something. What does it start to detect? We are going to look for the diagnosis key on the remote control. In this case, it is the router key that, when pressed for 5 seconds, enters the diagnosis mode, and we are going to keep it pressed for 5 seconds with the phone nearby. Well, through that melody, the application understood what the error of the CH10 indoor unit fan operation error equipment is. So, there's an error in the indoor unit fan. It's good because, in addition to indicating the error code as the equipment does, it also tells us what the problem is. That is, it shows us what such an error code means. Remember that this application exists and that it works through audio. Through that melody, the application determines what the equipment error is. So learn to use it, familiarize yourself, and remember that this can be done with all modern LG appliances. It is very useful, very practical, and I am going to show you with which devices it is possible to make this diagnosis. Notice, washers, dryers, TV, stealers, refrigerator, microwave, dishwasher, air conditioner, heat pump. That is, it has a lot of devices in itself that serve with the smart diagnosis. So learn to use it and use it. Well, in this short video we're going to explain some details about the smart module for LG equipment. These devices, or rather, most LG devices, have the ability to diagnose themselves through different methods. Some are more in-depth and others less so. Take a look at this model here. We have an LG advertising video. And notice that this model has, for example, a button, which is the power button, which we can use to diagnose by pressing and holding it. There are other models that have the button inside. As you can see, inside the ventilation fin is the automatic on-off button, but it also serves as a diagnostic button. So, what we're going to do is hold it down and activate the diagnostic mode through the remote control. After doing this, through the LG Smart Diagnosis app and through Bluetooth, it will connect to our phone and show us the different parameters of the device. Is there any malfunction? In this case, the system is working normally. Pipe temperatures, air temperatures, the energy it is currently consuming, the motor is off, all the details of the equipment are indicated here. If there is any error, it will indicate it at this point and will indicate the error code and, in addition, will show us what the error code means. Very well, we have another system that is a bit more in-depth, which is the LG SIMS 2.0 module. This module, which connects through the JIG cable, allows us to perform more in-depth diagnostics, but, well, in this case you need to buy the device. In this case, I justify the purchase of the device if we had to work with many LG devices. For example, if we are servicing a building that has perhaps 20, 30 LG devices, in that case connecting this module to the outdoor unit is good because it gives us many parameters and, in addition, allows us to see what happened or what is happening while we are not there. That is, see now what possibilities this module gives us that also connects to the cell phone through an app and through Bluetooth. When you connect the module, it turns on and, through the specific application, you can see that we have parameters of the equipment. We are talking about having main information, temperature of all sensors, fan speed, pipe temperatures, and what error the equipment is found. In this case, none, and what pulse is the expansion valve located, and here we have the outdoor unit details, the fan speed, the voltage that is on the line, the voltage that we also have in the alternating current and in the continuous after being rectified. And if we continue advancing, you can see that in the indoor unit, we have for several indoor units. For example, in the case that they were multiple, of how much capacity it is, and what operating mode it is located. Well, different points about each indoor unit in case it is a multi-split. In addition, information in the graph, we have what happens over time. We can leave the device connected and, over time, it tells us what the motor does, turns on, turns off, runs fast, runs slow, what the fans do, what happens to the temperatures. We can have all this along a graph. It's good, the device costs approximately $200. So, well, know that it exists and that this possibility exists. All LG inverter equipment has the possibility of connecting them through the outdoor unit, regardless of whether they are smart Wi-Fi or not. That is aside, that is a topic to be able to operate it. For diagnosis, LGs have the connection for the module in LG SIMS 2.0. Well, these are some details of the LG brand. It's not that we promote this brand, we simply know that many of you repair them daily. So, we explain it to you, we show you that you have this possibility in these equipment. Knowing these things and using them is very professional on our part, so it's good to familiarize ourselves. They are lightweight applications. They don't weigh much, so it would be good if we had them installed on our phones to be prepared when it's time to diagnose or repair this type of equipment. The purpose of this video is to teach and show you how pressures work in an inverter system. It is a system with our 410 that has 850 grams, which we will be starting in cold mode, and we will observe how the pressures are maintained. This is very important in order to later explain matters about gas charges in these systems. Please observe and notice that the pressure decreases as in any system since the compressor starts to compress. And we are measuring in the suction pipe. We have turned on the unit at 100%, that is, we have placed the unit at a set temperature of 18 degrees. Approximately, in this environment we are having 25 or 26 degrees. So the unit will try to turn on at maximum to be able to reach the desired temperature quickly. Observe also that the pressure remains at 150 psi. Remember that inverter units are constantly controlling all temperatures: indoor, outdoor, overheating, cooling, and compressor discharge temperature. What they will constantly do is try to regulate the pressures by varying the motor speed to cool in a comfortable way, not too strong, nor too slow or too fast. What does all this mean, or what do I want to tell you with all this? Well, we cannot trust the pressures to make gas charges in inverter units. We cannot trust the pressures. If we try to charge by pressure, what we will achieve is that the unit will constantly change its configuration as we add gas, because it will be trying to level those pressures. And we, adding gas, will reach a point at which we will definitely exceed, because we will try to find a fixed pressure and this unit does not have them. You are seeing that the pressure is being maintained at 140 psi. Perhaps we will charge up to 120 or 118 if we compare it to a conventional unit. But in this case, a unit with the full load does not reach the pressure of 120. It remains at 140. In fact, each unit works with different pressures, depending on what the manufacturer wanted to do or depending on what the manufacturer wanted to program in the software for it to work in a certain way. Well, later we will give more explanation about this, but in the next video we will be seeing how to compress the gas or accumulate gas in the outdoor unit to be able to uninstall an inverter unit. Well, very well. Regarding gas charging in inverter equipment, you could see in the video that the pressure remained at 140 psi. Of course, the inverter equipment, by controlling all temperatures in 5 points, in addition to having the ability to control the compressor and the electronic expansion valve, will maintain pressures according to the need of the moment. What does this mean? When the equipment lacks gas, it will try to control all this until it finally realizes that it lacks gas. What does this mean? That I cannot charge by pressure. If I try to charge by pressure, as I approach the 100% charge, I will be going up and increasing the charge. The equipment will be constantly varying all this to be able to see what is happening and try to understand. Therefore, charging an inverter equipment by pressure is very complicated. Inverter equipment, approximately, will be maintained between 115 to 175 psi, of course, in cold mode. How? According to what the manufacturer indicated that it has to do according to such temperature, close valve, open the compressor faster, slower. It does it in different ways. It is true that when the motor is set to maximum, the pressure usually drops more, but we do not know exactly at what point it is. That is why we cancel all this way of thinking of wanting to charge by pressure. What we will do is always charge by weight. an inverter, it is essential that we have a scale, which in fact, for our 410, it has always been necessary to charge by weight. Our 410 is a zeotropic mixture that changes its composition when it loses gas because the state changes, gaseous or liquid. Therefore, if we charge by pressure, we always alter the mixture. Therefore, whenever we have 410, we had to charge by weight, and now in inverter we have no other option. In the R32 training, he explained much more how refrigerants work, what things can be done, what things cannot be done. This training is very in-depth, focusing on refrigerants, zeotropic mixture, azeotrope, pure mixtures, although it focuses on flammable R32. We also focused a lot on explaining how gases work and what things can be done, and that not with respect to gas charges. Well, very well then, inverter always is charged by weight. Well, in this video, then, we are going to compress the gas in the outdoor unit. We will close the fine pipe as usual, and we will let the gas be absorbed by the suction pipe, the gas pipe. We close the liquid pipe. This is not high or low pressure. This is liquid and gas. We close the liquid pipe. We wait for the gas to be compressed and we close. Perfect. Now we are ready to turn off the equipment. So, the gas compression is done as in any conventional equipment, only that you do not let the compressor work for a long time with the pipes closed, because remember that all this overheats the IPM, so pay attention to that detail no more. But after that, the compression is the same as in any system. Very well, then, in this class we are going to be talking about the necessary tools to work with inverter equipment. Whenever we are going to work on electronic boards, we are going to need some specific components or tools. Speaking about the soldering iron, we are going to be buying a Goot brand soldering iron, as we can see here, a 40-watt Goot brand soldering iron. There are many on the market, but these tools that I show you are proven tools that we use, that work well, of good quality, at a good price, and not investing more than necessary. There are those electronic kits, electronic tool kits, that sometimes we do not use most of those pieces. I am going to indicate precise tools that will serve you exactly for what you are going to have to do. We start talking about a 40-watt Goot soldering iron. What else? Well, we also need a desoldering tool. As we saw in the soldering class, we are going to need a vacuum desoldering tool. In this case, the model I recommend is the Goot GS108, which I am going to show you. This is the one we recommend. A very good quality tool, which requires constant maintenance. You have to open it and remove the tin that accumulates inside. If possible, also clean the sealing rubbers well, that is, the internal part. And once we do the cleaning well, we reassemble and continue using. In case we see that it gets a bit hard or does not seal well, what we can do is apply a little graphite grease. These types of sealing greases are ideal for that. Very well, there we have our vacuum desoldering tool. Remember Goot model GS108. Very well, we continue advancing and we are going to talk about supports for boards. This type of board supports are sold for a very economical price, for $18 to $17 on Amazon. It is highly recommended. Firm safe. The metal, this plastic part better because it is insulating and it will serve you to work with inverter boards just as you will find it on Amazon or AliExpress. Support for electronic card. Very well, another tool that you are going to need is the microscope. Here I am showing you the microscope. Notice that it is a very simple model that is really economical. It costs $35. This microscope, despite being very economical, is of very good quality. It works very well and is more than appropriate for what you are going to use. Notice that you can see the microfiber. It has the option to take photos. You can add a memory card. You can connect it to the computer and the computer recognizes it as a webcam. The battery lasts a lot. So a microscope of this type is the one we recommend. You will always need some kind of magnifying glass, perhaps with light, to enlarge and be able to see components that cannot be seen with the microscope. A very important detail, when you buy the tin soldering iron, do not forget to also buy a stand because since we are starting with electronics, we are new and sometimes we do not know that the soldering iron can cause damage to us or burn something. So always buy a soldering iron stand and in that way you will work much safer. These types of sponges also serve to clean the soldering iron. They must be wetted with distilled water and every time we use the soldering iron, we pass it through here and there we keep it clean for the next soldering. In this way, of course, once it is hot, if you cannot get this sponge, you can get these vegetable type sponges that are used for makeup at pharmacies. Well, speaking of tin, since we are in tin soldering, in this case, what I recommend is to buy good quality tin. The problem is that if we buy a tin with the characteristics we need but of poor quality, the internal resin is the one that is usually of poor quality. So, the problem is that when soldering, the solder never applies well in the hot area because the internal resin that acts as flux is of poor quality. So whenever you buy tin, please buy a good quality one, which is a little more expensive but lasts a long time. If you are not going to dedicate yourself exclusively to electronics, a quarter kilo, 250-gram tin roll will last you a very long time. The measures you need are as follows: tin lead composition 60:40 and filament diameter 0.7 millimeters. For those who are in Argentina, you can get this brand. For those who are in other parts of the world, you can commonly buy the Goot brand. Desolderer or desoldering Maya, we always recommend the Goot brand. The thickness of the tape can be between 3 mm and 3.5. The length depends on what you buy. In this case, it comes 1.5 meters. But this is the thickness that we are going to need for the SMD components with which we have been working in the course. You also need tweezers that can hold, cut components, cut wires, prepare little cables to be able to make bridges. So you always need these tweezers that are going to be exclusively for electronics. Notice that they are small. An important detail: do not use these tweezers to install air conditioners because they will not last long. Have your exclusive toolbox for electronics. Silicone. After soldering boards, it is important to cover them so that they are again isolated. So a silicone gun is essential for that. We talk about this silicone, the silicone that is applied, which is hard, and when heated it melts, it goes energized. We cannot apply clinical silicone. This has to be the one we can apply on boards, knowing that it does not produce continuity between contacts. It is available in bookstores. Heatsink compound. We are going to need it because we have many heat sinks on inverter electronic boards. This heatsink compound can also be purchased from the Good brand or a good quality one that you may find in stores where they sell computer supplies, and it is the paste that goes between the component and its aluminum heatsink. Of course, in this case you are seeing it wet because in the previous course I applied it and this component was not used. But when we disassemble a component that has been working, this paste is completely dry. So you disassemble, change the component, and before reassembling it, you have to apply new heatsink compound. This is essential so that the component does not burn instantly when you apply it. There is what the heatsink compound does is fill the cracks that remain between the component and the heatsink and transmit the heat better so that the heatsink can dissipate it. So you have to have heatsink compound when working in electronics. Don't forget the isopropyl alcohol for board cleaning. We are always going to be using high purity isopropyl alcohol. We are always going to apply it with a brush. Are there components that clean better? Yes, such as, for example, paint thinner, but they are corrosive and harmful to certain components on the board. What we are going to use to clean electronic boards is high-purity isopropyl alcohol that contains a purity of 99.8%, and we are going to apply it with this brush. We moisten the brush and we can clean without fear, obviously with the board disconnected. Very well, another tool that will also be very useful is the multimeter. UT brand multimeter. This model that you can buy that brings the capacitor and everything you are going to need is the UT61A. There are many UT brand multimeters, but this is enough. Can you buy a better one? Yes. Can you buy a worse one? Yes. But if you buy a worse one, there are measurements that you will not be able to make, and if you buy a better one, you will have functions that make the device very expensive, and you need to carry it, climb stairs, climb roofs, so buy this UT61A, which has all the functions we need. For example, the UT61E model has a computer connection, I don't remember well, but who is going to use it connected to the computer? I think that is air conditioning technicians. We are not going to do that. So it seems better to buy one that has the functions we need. This one has the capacity to measure capacitors up to 200 millifarads. We are talking about 200,000 microfarads, more than enough for our boards. Alright, in this video we will be explaining how to connect to the home Wi-Fi network on smart Wi-Fi devices. As an example, we have the manual that comes with Carrier brand devices, and in this manual, you will be able to see step-by-step instructions on how to directly connect these smart devices to Wi-Fi. The idea is for you to be able to offer an additional service to customers and for you as technicians to understand how this connection from air conditioners to the Wi-Fi network works so that the customer can later manage them with their own phone. Each brand has its process, each brand has its application. For example, Carrier has this brand, Carrier air conditioner for iPhone and Android, but the installation process is similar across all brands, and you need to understand how a device links to the Wi-Fi network to be able to manage it. In fact, this explanation will also be useful for surveillance cameras. It will also be useful to know how to connect the new switches that are managed through the phone, washing machines, and any appliance or device that connects to the Wi-Fi network and does not have its own screen and keyboard. Connecting a cell phone or a computer to the Wi-Fi network is very easy, because the device already has its screen where it shows us the available networks and we can enter the password. But since these devices, the cameras, the switches, the washing machines do not have a screen and keyboard, we need to do an additional process. This is simple. What the phone will ask you within the application is that if you do it via Bluetooth, it does it directly, but if it is via Wi-Fi, how it is going to connect to the device, it will ask you to disconnect from the home Wi-Fi. Then your phone, through the application of each brand, will connect via Wi-Fi to the air conditioner, and when you connect, you act as the screen and keyboard of the device. This is the initial and only process that needs to be done to finally link the device to the Wi-Fi network. The device cannot connect because we have no way of loading the Wi-Fi key into it, nor can we see what networks are available. So the first thing it asks us for is a connection like this between the phone and the air conditioner, or between the phone and the washing machine, or between the phone and the camera, and once I am inside the application connected to the device, the appliance to be more precise, what I do is search for the home Wi-Fi network and load the password. It will ask me for the password, and maybe I wonder why it asks me for the password if I already have the Wi-Fi password, but now I am representing the device and the device does not have the password saved. So we enter the device, look for the Wi-Fi network and load the password, and once we do this I can disconnect from the device and the device is already connected to the Wi-Fi network, and there I can manage it through any phone that connects to this Wi-Fi network. Remember that then the first time is a bit strange because what I do is with the cell phone I represent the screen of the device, the screen that it does not have, and that is the process that each brand asks us to do. Remember, it is very simple, you just have to read the manuals well, download the appropriate applications for each device for each model, and I do this initial process. I can do this with my own phone as a technician. And then I disconnect and leave the home. It is not necessary for this phone to be connected afterwards. After anyone who is connected with their phone will be able to manage the air conditioner, I can do the initial process and then I disconnect. Well, this is the explanation of the process of this manual. As a demonstration, you already have this explanation to provide a better service to customers. Sometimes, customers who buy a smart Wi-Fi device want the technician to also program it. This way, they know how to do it. So, from now on we are going to explain which universal electronic board for inverter air conditioning units we are going to be recommending. The model that we recommend is the Kunda QD82+. This model has quite a few possibilities for adaptation with most of the inverter units that we are going to be using. However, we do not recommend the installation of universal boards for a reason. When we install an inverter air conditioning unit, this unit consumes 70% of energy compared to the 100% that a conventional unit of the same capacity would consume. When we install a universal board, we are only saving 2% of energy and the unit goes on to consume 98% compared to a conventional one, which we could say that the unit becomes almost like a conventional one. Why does this happen? Well, because the electronic board does not regulate the speed of the motor. The inverter electronic board does just like a conventional one. It turns it on, turns it off, turns it on, turns it off, turns it on, turns it off. It's true, it doesn't have the startup peak of a conventional one, and that's why there is some energy saving, but in reality during operation it's the same. The inverter unit will start at maximum, it will cool down, and when the room is cold it will turn off, working in the same way as a conventional one does. For this reason, we do not recommend the installation of these boards, and also because of their cost. Their cost is between $150 and $200, a high cost considering that it also does not leave the unit working correctly. But if the universal electronic board is going to serve us as a tool, and now I'm going to explain how. We are going to start this video explaining about the indoor board and explaining step by step how it is connected. Here we have an indoor board of an inverter air conditioning unit, a universal board of the Kunda model that we had mentioned. How are we going to be connecting it? Well, let's pay attention to the details. At this point, we have here the connection of the negative. Here is where we are going to connect, or rather, instead of the negative, the neutral of the 220, 110 volt or 127 supply. On the other hand, at this point, we are going to be placing the line. At this point, the line is connected. They are boards with switched sources. Here it has its transformer that has a switch 7805. They have their fuse, their varistor. They are switched sources. Here they have the encapsulated rectifier here. Well, we power the indoor board. These boards have the capacity to handle units of up to 24,000 BTU or 6,000 frigaries, but they are always powered by the indoor unit, not the outdoor one. Which way are we going to go outside? We are going to go outside from the outdoor fan. From the four-way valve. Notice here we have outdoor fan, four-way valve, and finally through this cable that is going to turn on the compressor. Here we have fan, valve, and compressor, just like a conventional one. In an inverter, remember that all this is managed directly from the outside, but in this one, just like a conventional one, the outdoor fan, the four-way valve, and the compressor are energized directly from the inside. There is no communication signal. It sends a direct voltage and alternating current and turns on the outdoor components. Of course, the outdoor board to turn on the compressor will have an IPM, but that will be on the outdoor board. The IPM itself is intelligent, but it will not have a microprocessor that exclusively controls it on the outdoor board. When it is powered with 220 through the interior, directly the motor outside is going to turn on. Alright, what else do we have here? We have the connection for the DC fan. This is a possibility that this board has that others do not have, other universals do not have. We have the display connection, DC fan when it comes with a narrow plug, a thicker plug. We have the display connection, we have the pipe sensor connection and the room sensor. And here we have the connection of the stepper motor that directs the direction of the air. If you don't know how to connect them, don't worry, test the connections until it works. This one is 6 in the motor, only have 5. You test one side and the other until it works, it won't burn. And on the other hand, here we have the connection for the indoor fan in case it is a fan PG or an AC fan as we studied in the training. And at this point, here is where the capacitor for this AC fan is connected. This board doesn't care about the speed at which the fan rotates, that is, the Hall effect sensor is left unconnected. The board also brings a connection for the fan and on the other hand brings the connection for the capacitor. But in case a DC fan arrives, it is connected directly there. Well, very well, these are the connections of the indoor board. Now the question is, how are we going to go outside, or what cables have to go outside? Well, we are going to go outside with a cable for the fan, another for the four-way valve, another for the compressor, and a fourth cable for the neutral. The neutral of the 220 or 110 enters here and comes out through another of the plugs and goes outside, and of course we need the ground cable. The problem that this board presents, perhaps some of you are already realizing. In an inverter unit we are going to have neutral, line, and communication, and then we had the ground. Maybe in inverter we are missing a cable when we want to connect the universal board. If we have a fan that is powered outside at 220 AC, we are going to need one more cable to connect it. We have to place it somehow. And if we have a four-way valve, well, we have to use the communication or signal cable as if it were the four-way valve, the original one that is no longer going to be used anymore. Now, what could be done is if you need a cable for the funk, use the ground as a cable for fan and place the ground directly outside. You have to think about it. You have to evaluate it. Keep in mind that this can happen, that when placing a universal board a cable is missing, so the work increases the time and effort of course. But there can also be the case in which you don't have a fan because the fan is DC and is powered directly with the outdoor board, as we will explain later, and that the unit is cold only, as happens in the case of Central America, that the units are cold only. In this case, instead of missing a cable will be left over, the communication cable we are not going to use for anything. Well, these are things that can happen to us with universal boards. Keep in mind all those details because they make the job much more difficult if it gets complicated. So keep this in mind when giving estimates. Very well, let's move on to the outdoor board. Well, speaking about the external board, of course, the manual includes all the details on how to install it, but we will also explain step by step. On one hand, we have a connection that says N where we will be placing the neutral that comes from inside. And on the other hand, a connection that says comp where we will place the cable that comes to turn on the compressor. And this is where the external board serves us as a tool. If we energize with 220 volts, 110 or 127 depending on the external board we bought, this board without receiving a signal turns on the compressor to the maximum. Not only does it turn on the compressor through these points U, V, W, we are going to put a color that is more visible. Not only does it turn on through U, V, W, but also through this contact it turns on a DC fan. Notice that here we have to turn on a DC, injecting 310 directly. Here we have the negative. Here we have the voltage of 15, and here the two signals. This board is energized and automatically turns on the fan and the motor, which gives us the possibility to use it as a tool. And it also moves the expansion valve to an intermediate and correct position for the operation of a maximum inverter. So it serves us as a tool to test all these elements: fans, motors, and expansion valves. Pay attention to that detail. It serves as a tool. Well, what else do we have here? Well, we have the U, V, W outputs that connect to the motors. We are going to find two more plugs that are clearly indicated with less and more, in which I will have to place the external board dedicated to the capacitors. It comes in two separate boards to connect the capacitors. Here we have the electronic expansion valve in case it has it. If it has a capillary, there is nothing to connect. And up here we have the connection of the only sensor that this board brings, which is the discharge sensor. There is no outdoor temperature sensor or pipe sensor. And here we have a switcher that we have to leave 2, 3, and 4 in the place where it is. There is no need to set it comes from the factory. And number 1 we are going to select in DC because most of the inverter motors are DC. Previously there was another operating system called AC, but it was used very little. These boards allow us that because it is the first inverter, but we are always going to configure in DC inverter. Very important and fundamental detail. At this point and at this, we have to place the original heatsink. Somehow we have to adapt the original heatsink and anchor it to these ovals. Remember that if you do not place the heatsink, the motor will run for a few seconds and the IPM will burn. So pay attention to that very important detail, and that also adds to the work because placing a heatsink is complicated. You have to make holes. The screws do not fit in the exact place. It takes work, so also pay attention to that point. Another important detail, also why I do not recommend inverter boards. Notice that we have no possibility to connect fan motor type U, V, W. Remember the U, V, W that the IPM had on the board. Well, with this universal board, or with none, there is no way to connect that fan, which needs a dedicated IPM on the board. If we touch that case, we also have to change the fan and place a DC or an AC. Well, these are some details about universal boards. This is how they are installed. This is how they work. They serve more as a tool than as a replacement. Know that it exists, that it is there, and this is the model that we recommend to you. All the details come in the instruction manual. Of course, it is not as aesthetic as always, but well, it exists. It is there, and this is the model that will serve you in case you want to make these connections. Here we have the detailed diagram that is included in the board. Very well, an application that I want to teach you to use is the following: Electrodroid. This application gives us several options to perform tests or electronic calculations. There are many functions that you can learn to use on your own: battery life calculation, capacitor combination, resistance combination. This application allows you to make many calculations: SMD resistance code and normal resistance color code. One of the ones you are going to use the most are precisely these SMD resistance codes. If you come across some of these SMD resistances, remember that they have a number placed and that you will know their value depending on the number that is printed there. So, what we are going to do is just put the number, and here it already indicates what type of reference it refers to. It's very easy to use. It is even very useful when thinking about the colors that resistances have. If we find perhaps brown, black, brown, gold, it is a 100 ohm resistance, for example. It's very easy to use. It will be very useful for measuring resistances, and also, if you want to research and learn and use for other things, well, this application is good. It's free too. Remember the Electrodroid, which is the tool that we recommend for this. Remember that resistances, to know their value, we have to observe the colors. So we memorize them, we use an application. It's great to have it downloaded on your phone.